All right, let's get started. Yeah, sorry for just a little bit of delay because of the little bit of a hassle setting up hybrid, which is has always been a hassle, but we made it to work. So yeah, very happy to have people. We have in-person audience and the people on Zoom showing up for our very exciting third workshop and challenge on computer vision in the built environment for the design and the construction and operation of buildings. This has been the third version of that workshop. The first one was held virtually. CVPR 21 was actually having pretty good attendance for a virtual workshop. We had more than 70 people at the peak. And then late 2022, we had it hybrid, and today we have it hybrid as well. So let me start. So I will start with an introduction, which will take until 9:30, and then we have invited speakers. You want to, we need to do what, start recording?
No, I want to remove the hide video panel.
Okay, that's okay. All right, yeah, so I will start with some introduction of the workshop and the challenge, and then invited speakers will start to talk at 9:30 Pacific Daylight Time. So really my session is just for people to flock in gradually. So my session is not very important. I will be talking a bit about the workshop itself and then the challenge we are hosting as well for the third time. So the background of the workshop, why we started it, was because like 3D vision has been really hot in computer vision in the last few years. So I actually recently updated this slide yesterday, and I realized PointNet has already been cited more than 10,000 times, which was crazy, given that it was just published in 2017. And then, of course, 3D point clouds have always been a crucial data input in the AEC community as well. But then there is quite a bit of disconnect between these two communities. Like computer vision, we were working on data sets such as ScanNet and stuff. And then these are good data sets, but they are not necessarily suitable for the need of the AEC community. And then there have been, for example, there have been some use cases for computer vision in homes as well. Zillow's 3D Home was pretty good, powered by Matterport. It was a commercial product. Everybody who actually have been trying to buy a home in North America might have used something like that. And then Apple has also released a room plan last year, and this year they have a new update. They can actually detect objects and walls and floors in your house as well. So there's been some products putting computer vision in homes as well. But still, I mean, in terms of civil engineering applications, there is still a lot of things that are missing, like, for example, 3D building models, right? How can we actually get to civil engineering level 3D building models? Computer vision, we tend to focus on certain metrics that are okay, like good for us, but not necessarily good enough for civil engineering applications. So the goal of this workshop has been to try to bring these two communities together. Computer vision has a lot of algorithms. I hope they are powerful. Previous workshops kind of suggested that maybe they weren't that powerful just yet. But hopefully if we work on it together, we can try to develop them so that it becomes actually more suitable for the needs of like real life construction applications and civil engineering applications. And we also wanted to look into the problems that the AEC community can bring to the computer vision community, and then we can work together to just solve better real life problems. So we have an exciting set of invited speakers today. And so this is a list. We have Avidai Zahor, Pingbo Tang, Memo Chandrakar, Mani Gopawar-Vard, Despoina Pashatlido, and Fernanda Leiter, who is with us right now already. And so basically half of the speakers are from computer vision and half of them from the AEC community. We deliberately made this choice so that we try to bring people together. And then, yeah, half of them would be delivering the talk in person and half of them online. So it's actually a perfect split either way. We also are hosting the third Scan to Beam challenge, and the goal of that challenge is to combine strengths of both disciplines and basically trying to bring the computer vision mentality of data-driven research and the metric-driven research into AEC. So we wanted to collect a good amount of training and testing data, and we want to have standard metrics to measure the performance and improvement over the years of research advances. And then we want to measure realistic metrics that are relevant to the AEC community. So that's also a very important goal. And then as I go through the metrics, you can see that we actually spent a really good amount of time to develop them. So that's, yeah, people are happy. At least the organizers are happy on both sides, from the computer vision and AEC sides. And of course, we are also always welcome to new suggestions as I go through the metrics. You can feel free to post your comments on new suggestions. Yeah, in terms of data, we are very fortunate to have Dr. Paul Platosz from the Oregon Department of Administrative Services to gladly support us with 31 public buildings from the state of Oregon. And so these buildings are scanned with a BLK360 laser, and we have 91 floors of point cloud released. They have very complicated layouts. They are very different from regular other kind of data in consumer homes because they are public buildings. They are actually a lot of office buildings and different kind of floor types. For example, we have office buildings with many rooms in the office. We have like labs, so we have garage, facilities, parking lots, different things. We feather realistic scanning noises. Every year we had participants complaining that we actually get some points that are actually outside the building, but we decided never to change the input because those are things that people have to deal with when they are dealing with realistic point clouds, that the scanner sometimes do go outside the window and capture points that are not inside the building. So have to deal with that. And then in terms of the challenge, we have two challenge problems. The first is 2D CAD model reconstruction. So this was like 2D wireframe, a wireframe as built CAD model. So not as these, well, we actually hope it is exactly as built, but as you may imagine that even if those CAD models were created after the building was built, there might be still slight differences between them and the real point cloud, which is a problem in the annotation that we don't really have a good way to fix at this moment. But some data, imperfect data, may still be better than no data at all. So that's what we think. We did spend quite a bit of time trying to align those CAD models with point clouds, and we did manage to export them into a public format, because initially they were in the AutoCAD format, and that was not good for making it publicly available data, because the software is you need to pay for the software. So we did actually create our own data format to make it public, make it available, so that everybody can just use some Python script to open that data. And so we also have a lot of 3D building models annotated, not all the floors, but a pretty good amount of the floors. We have 3D BIM models annotated, modeled in Revit by architects, and we put a lot of those models available as training, validation, and testing set. And this is thanks to Dr. Yasu Furukawa's and his student. They put together a whole pipeline of making architects to annotate those data. There has been a great process. Most of them was done in the first 2 years to develop those metrics that we evaluate in the challenge. The goal is to build realistic metrics that are useful to AEC community. So we have mostly between our organizers from both the computer vision side and the AEC side, we were kind of talking together, trying to come up with those metrics. So we came up with all these different points, area metrics, and topological metrics as well. So we hope that will be useful in the end. So the first metrics we came up. So I'll talk about 2D first, and then I'll move to 3D. 3D is in the end a little similar, but there's a little bit more nuances in the 3D metric. So I'll first start with 2D. So this is the simplest metric which a lot of people use, is just endpoints. So usually the endpoint of a wall, the corner between two walls, the endpoint of a door, and things like that. So we capture all the endpoints. And so these are the ground truths. And then users would, algorithms would predict some endpoints as well. And then we will do a Hungarian matching between the predicted endpoints and the ground truth endpoints. Yeah, sorry. Oh, okay. This one over. We can predict something between these two sets of endpoints, and then we will consider match if the predicted endpoints fall within a certain range from the ground truth endpoint. And then the final metric, we compute precision and recall precision as in those formula. And then we also compute F1 score, which is multiplication between precision and recall and average over that. So that's, and then we choose different radii. So this was one important thing, that we choose different radii between the ground truth and the predicted endpoints. We decided to use 3 different radii for both the 2D and 3D challenges, which is 5 centimeters, 10 centimeters, and 20 centimeters. It turns out that computer vision algorithms do better on 20 centimeters radii, and then a little less as well on the 5 centimeter, or like the first year of the challenge, we even tried 2 centimeters, but nobody was actually able to do that. So we moved to 5, so which is still, it seems like it's still considered acceptable from AEC community for certain applications. So yeah, so we have 5, 10, and 20 centimeters radii here right now. And then another 2D metric is room IOU, because in a 2D wireframe CAD model, we cannot really have objects that, a lot of the objects are not actually occupying space. If you think about windows in a 2D wireframe, it's just a line. So it's not really a line, but it's really seen as a box. So we decided to just compute the intersection over union on the room itself. And here there is the ground truth room, and then there is the predicted room. And the IOU metric, which is very commonly used in computer vision, is just the area of overlap between these two divided by the area of their union. So that's the IOU metric. A little more complicated are the topological metrics. So let me see if I still remember how to present this. But the point here is that this is a warping error. And the point here is that you will want to, so this is your ground truth. And then this is A, and this is B. So A and B actually has the same pixel error. And then in the computation of this warping error, we try to change B 1 pixel at a time, change B 1 pixel at a time to the ground truth by making topologically equivalent changes. For example, we can add 1 pixel here, and that will be a topologically equivalent change. And then we make it, and then also we can remove 1 pixel here, and as that doesn't change topology. So after we made all the topologically equivalent changes, we will see whether B would be similar to the ground truth. For example, in this case, we can topologically equivalently grow and shrink this region so that they exactly match the ground truth, and hence you would have no warping error in this case. And A instead will not be able to do that, because this blue region, you cannot really move it over there. And so A would still have warping error. So yeah, the computation is a bit more complicated, which we will hopefully show in the paper that we want to write after this workshop. Another topological metric is called Betti number error. So Betti number in topology is the number of connected components in a manifold, let's say. So in this case, we computed it locally because like a global Betti error would be not enough to actually capture all the nuances in the building. So what we do is we actually sample 500 different local patches, and then we check how many connected components each patch has between the ground truth and the predicted. Like if the ground truth, if we sample this little patch, for example, we can count how many connected components are here. This may be 1, 2, 3, 4, 5, and something like that. And then we check the predicted, and we check if they have the same number of connected components. And then we average this over 500 different random selections of the patches. So yeah, we think that's an interesting metric as well for estimating topology. And in this particular case, obviously, it will do pretty poorly on the Betti error because they fail to close a lot of the rooms, and that would definitely show in the metric. And so these are the set of 2D metrics as I just described. So we have endpoint precision recall, 5 centimeter, 10 and 20 centimeter thresholds, room IOU, topological metrics, and then the final ranking is determined by the average of all the 3 sets. So like we first average within the endpoint, then we average within the IOU. Actually, this one does not need an average, and then we have topological metrics average between these 2, and then we finally average between all the 3. Feel free to stop me with questions at any time if you have any, by the way. So this is 2D. We also, so the first year we didn't have enough time to develop 3D evaluation metrics, which we did actually in the second year. We met for a long time, like it was a lot of meetings that we had a lot of hand drawings to actually decide those 3D evaluation metrics. And yeah, there are different cases that are subtle but important in AEC that as a computer vision person, I would have never realized those subtleties. For example, we have representation of walls with 4 wall elements and 8 wall elements, and the difference is how you actually represent this corner, here. Yeah, so we decided there are too many items in 3D. We have endpoints, lines, surfaces, volumes. We decided to still go back after a lot of meetings. We actually really wanted to do lines and surfaces, but we ended up deciding just to do endpoints and volumes in the end because of these difficulties from those junctions, especially in the case of the lines. And in the end, maybe you will feel like we settled on something that's pretty standard, but it wasn't without a lot of discussion. So yeah, in the end, we still have these endpoint metrics, which are almost the same as in 2D. Yeah, so I don't think I need to talk about that again. And then we also have the 3D IOU metrics. And this time, because we can have a few more categories, we are computing them on different categories. So we have the 3D IOUs on walls, on columns, and doors separately, and then finally we average them. We still didn't get to do windows because we have some trouble kind of dealing with the annotation over there. So yeah, there's still a lot of things that can be improved. Yeah, and then the final 3D metric would be an average between the average F1 and the average 3D IOU. So what is new this year about the challenge is that we got a lot more 3D ground truth data. So last year, I think we had only 11 point clouds annotated in 3D. And then this year we had about double that amount. So we have a lot more annotated in 3D. So this is the this is the general kind of process we have for the 3D annotation. We have point cloud architect models get to a Revit model, And then we have developed a custom plugin in Revit to actually export it out of the Revit, so that participants, they don't have to have Revit to use this data. And how we dealt with corners, we followed Revit and then just use the center line locations to define corners, so that we don't have to deal with the 4-wall element or the 8-wall element, and then we can just put it around the center line, and then we define the thickness by the thickness, like by the distance around the center line, so that we can make a volume, so that each wall is a volume in 3D. And yeah, so each column is also a volume in 3D. We had also this verification process that we've done on the 3D ground truth data. We have an export from Revit to DXF, and then 3D ground truth data. We have a Python script, and then we look into both of this to compare, so that we make sure that it actually works. Yeah, so those are all the data pre-processing and how we actually get those things set up. We hope this will be valuable in the very end. So in this year, we have 4 teams after deduplication. We have 4 teams participating in the 3D challenge, and then they achieve different amounts of success. And as you can see, our top 2 teams are actually getting very similar scores across the board. One of them is better on the IOU side of things, and then the other one is better on the endpoints. So we will hear later today about both of these teams and see how they achieve their results. As a note, we have our winner last year has an IOU of only 31% versus 43%, although it is not directly comparable, because we have do we have actually the same test set? Actually, maybe this is wrong. We didn't change the test set, maybe. Yeah, so this one, get rid of this line. So we actually didn't change the test set. I was confused. So it is comparable. And then we got, I think over the board, we can see solid progress from previous year to this year. Yeah, sorry, I was confused last night. I was doing this. And then on 2D, we also got a little better. Last year, we actually had a better IOU last year, but our endpoint recall was really bad last year. And this year, people definitely improved on the endpoint recall at a little bit of expense of the IOU, but altogether, they still get a little better than last year. Yeah. So we will hear what they did later today in the workshop. So we would like to thank the team that's actually worked on the challenge itself. Of course, we also have all the workshop organizers, but there's also more people that actually worked on the challenges, and especially Sayan has been running the challenge this year, and he helped a lot. Wei Lian kind of helped a lot on the 3D annotation, did most of the working with architects and then fixing all the 3D annotations. And Anton did a lot on the evaluation metrics. So, and then I will go through briefly of the schedule of the rest of the workshop. And we are right now close to 9:30, and we hope to start at 9:30 with the first invited talk from Aviday Zakor from UC Berkeley. And then we will have Dr. Pingbo Tang from CMU giving the second invited talk, and then coffee break. And then we'll have winner presentations from the 2 winners from the 2D floor plan reconstruction task. And then 2 more invited talks from Dr. Chandrakar and Dr. Mani Mani Gopawar Fard. And then we will have a lunch break after that. After the lunch break, we will have 3 winner presentations from the 3D building reconstruction task. And then we will have a community engagement session where the community can feel free to engage, to talk about topics that are having joint interest between the computer vision and the AEC community. Then we have 2 more invited talks by Dr. Despoina Pascalidou and Dr. Fernanda Leite. And then we have another coffee break. and panel. We will try to have a panel discussion. We will see. We'll try to. We will hope that all our invited speakers can remain at this point, so that we can have a panel discussion on some very interesting topics put together by my fellow workshop organizers. And finally, we'll make some conclusion remarks and be done before 6, hopefully. Just a final slide about the community engagement session, which is a little bit unusual for a computer vision workshop. And so we are hoping to have a breakout discussion so that everybody can participate in the discussion during that session. And hopefully we can talk about 2 topics. And the first would be about evaluation on scan to beam. And then the second is going to be about the opportunities that come with the explosion of AI. For example, ChatGPT, like everybody wants to talk about ChatGPT, for example, hopefully. And then we'll try to break out into small groups and have an open discussion between the groups. And then finally, we will try to have people to present what their discussion has led to, like some of the conclusions from the small group discussions. And hopefully that will be fun. And with that, I will conclude this introduction part, and we will try to move to our first speaker. Okay. So let me stop sharing and try to see. All right. In terms of her. Yes. Yeah. So Dr. Zakor, can you test your audio and screen sharing, please?
Yes. Can you hear me?
Oh, that's 1 sec. I thought that was. Give me 1 sec. I can hear you, but
can you also see my screen?
Okay,
yes.
Go ahead.
Yes. Hi, good morning. I'm Yasu Furukawa, one of the organizers from Simon Fraser local. So welcome to Vancouver, first of all. And sorry for the online audience who couldn't make it. It's a beautiful city. I want to follow Fushin to mention the importance of the workshop on 2 fronts. The first of all, workshop is the highlight of a conference, not the main conference, which has been the case for me for years, because you get to talk with the material you care about, with the people who cares about the same thing in a dense circle. And second of all, this is a rare workshop touching the interdisciplinary.
Like, oh yeah, so sorry, we were muted. I don't know who muted the oh, there was echoing. Okay, sorry. Sorry people didn't get to hear Yasu. So we will need to see how this working. 1 sec. So we are still working on the audio that comes from Zoom. I don't know if this is on.
Can you hear me? I'm just testing.
I don't know how this one working. 1 sec. So I don't really. You think that's the solution?
Well, a solution.
Okay.
I will bring speakers.
Wait. So actually, I had it on that right now.
Okay.
So
Dr.
now
Zacher, I can hear you, but the audience in the room can't hear you. They are trying to figure it out.
Okay, thank you.
Oh wait, this is not very high. Okay, can someone on Zoom try
No
one more
problem.
on Zoom, please?
Can you hear now?
Okay, this
Yes.
is better. Yeah. Okay. Yeah, so yes, I think this is much better than last time. So we'll just use this setup then. Okay, feel free to start anytime.
Okay. Good morning, everyone. I'm Avide Zokor, and today I'm going to be talking about robots and drones for building energy efficiency applications. So I want to acknowledge my collaborators in this project, a list of students, postdocs, and other colleagues. So roughly speaking, I'm going to talk about robots for cleaning and air sealing attics, drones for thermal analysis and verification, robots for thermal mapping, drones for 3D indoor modeling, and last but not least, if time permits, incremental learning for asset detection. So let me start by talking about attics. So about 30% of total US greenhouse gas emission is from buildings. And according to EPA, Environmental Protection Agency, homeowners can save a lot of money if they air seal their homes. Then there are about 83 million single-family residential homes in the US that could result potentially in $40 billion per year of savings. So how can people air seal their homes? What are the ABCs of what's called envelope retrofit? Well, the ABCs stand for attic, basement, and crawl space. And attic, by far, as you can see in this picture, is the biggest source of energy loss in American homes. Let's talk a little bit about anatomy of an attic retrofit. So there's 3 parts to it. The first part is to clean it up, because there's usually existing insulation, dead animals, feces, garbage, all kinds of hazardous stuff that needs to be vacuum cleaned. Then after that, you have to air seal between these joints to prevent the airflow from the main compartment of the house to the attic. And the last part has to do with blowing insulation. Now, attics, generally speaking, are extremely unhealthy, hazardous, unsafe spots to work. They're very hot. Moreover, they have these joists that are equally spaced, usually 6 or 8 inches tall, but 16 inches apart. And you're supposed to, when you work in an attic, you're supposed to step on those joists. Otherwise, you're going to fall through the sheetrock and hurt yourself. And generally speaking, they're very tight and inaccessible places. If you look at the picture on the lower left, these are the feet of a guy underneath this structure trying to air seal an attic. So because of these issues, there's a shortage of attic professionals. And because attics are kind of hazardous, tight, inaccessible places, they're perfect for robot automation. So my team participated in an e-robot competition sponsored by Department of Energy the last 2 years. I'm just going to go over some of the solutions we proposed. And we actually won the 2 prizes in that, but I'm just going to describe the solutions we proposed. So we came up with 2 baseline off-the-shelf robots, platforms. One is a tracked robot that has these arms that enables us to successfully traversed over joists, as you'll see in a minute. The other one is a hexapod robot with 6 legs that can climb over joists. And then we have 2 different payloads. One is an air sealing payload. The other one is a vacuum payload. And you'll see that in a minute. So technically, we can mix and match these payloads with each other. But practically speaking, we use the tracked robot to do the vacuuming, as you'll see in a minute, and the hexapod robot to do the air sealing. So let me speak a little bit about the tracked robot and the vacuum payload. So here's a picture of the tracked robot on the lower left. We got inspired by the nose of an elephant, and so we have a hose here, and this is the tracked robot on top of joist. And now the tip of this hose can retract in and out, right and left, and up and down. And to enable it to do that, we use servo motors. So up here in this picture, you see a typical, so the 3 servo motors are here, here, and on the other side of this hose, okay? And so there's a tendon the servo motor has a pulley, and then there's an eyelet here, and so we pass a tendon through the pulley that passes through the eyelet, and that tendon traverses along the nose or the hose here, and on the other side. And so by producing tension on that tendon, we can do the desired movements of making it go in and out, right and left, and up and down. And for the competition, we used a remote flush key that's shown here, to do those 3 motions. There's also an ESP32 that processes the signals coming from this flasky remote control to enable the robot to do its movements. So just to give you an idea of how this works, here's a robot in an actual attic. Vacuuming so it's being controlled by a plastic. So there's also a 50-foot hose connected to the back of it that goes back to the arm enabling it to move. It's very hard to video that. And it's so fun. Close-up of the robot showing how it uses the hose. I think you get an idea of what's going on. Next, I'm going to talk about the air sealing payload. It consists of 3 parts: a lower assembly, an upper turret assembly, and then an end effector assembly. And on the right, you see the various motors that control this. First and foremost, we have a motor that controls the pinch valve to open and close the flow of foam. This is the material. So the material we air seal with is liquid, but as it comes out of the hose, this little hose, it mixes with the air and it becomes a foam. That's what we use for air sealing. So there's a motor to tilt to turret. There's a rack and pinion motor for turret extension in and out. And then there's a gear turntable for turret rotation, which is shown here. So a bunch of motors, and all these motors, again, are controlled using ROS from an onboard Raspberry Pi that's sitting on top of this hexapod. Again, so this is a picture of the whole robot after it's been assembled. This thing is a big, strong LED light, and these 2 are also LED lights because attics are typically dark. And here's a cylinder contains the fluid that goes through this 30-foot long hose that comes eventually to the robot and then comes out of it at the other end. The reason we have all these cylinder and hose kind of methodology is because traditionally we could have put like a canister that has 8 ounces of fluid in it, but if you do that, the robot is in the middle of the attic, you have to keep changing the canisters and it's not easy to do it. So that's why we come up with this long hose kind of mechanism. And finally, here is the hexapod robot actually traversing inside an actual attic in Sonoma County, California. You can see that it moves its leg as it gets to this joist and it can do the proper movements. Now, everything I showed so far, there was a human operator making the leg movements. Now we came up with a methodology using reinforcement learning to teach the robot that's shown here, the hexapod robot, to climb over joists automatically. So I'm going to play this.
We present our work Perceptive Hexapod Legged Locomotion for Climbing Joist Environments. Joist environments, or attics, are key to energy efficiency in homes and must be air sealed and insulated. These tasks are hazardous for human workers, but hexapod robots can be taught to navigate the joist arrays of attics. We train our method using low-cost hexapods with no joint feedback, a single computer, and a depth camera. We use a 2-phase student-teacher learning approach. In the first phase, we train a policy with privileged information from the simulation, namely joint angle feedback and an elevation map. In the second phase, we distill this policy into a student model using depth images only to recover the same encodings and actions as the teacher model. Our proposed method's success rate is higher than a similar blind policy. It also climbs twice as fast as the blind policy, indicating the need for perception. Similarly, the manufacturer controller fails to climb any of the joists.
Okay, so just to give you a little bit of an insight as to how this system works, these are the state elements. So as you can see, the most important thing to notice is that the joint positions are not available from the real robot, but during the process of training the teacher, we make it available, and then The same thing with elevation maps. However, when the policy is being transferred to the students, we don't have joint positions on elevation map. Instead, we just use a depth map to help the robot navigate. And also notice that the demos you saw, they're running on a Raspberry Pi enabled robot. There's no Jetson NVIDIA, there's no fancy CPU or GPU going on. So everything is extremely low complexity, and it's a cheap robot that does not provide us with joint positions. Here's the list of the elements inside the reward function of reinforcement learning. What to note here is that most of the time we're encouraging the robot to go in a straight line, the direction it's heading at. And also we're also adding some terms to prevent it to have violent, rapid or extravagant leg motion, because that burns out the motors of the robot very quickly. So these are the terms like action rate and action magnitude to keep it perform nicely and without burning out motors. A few other caveats here. The legs, when we do sim to real transfer, which works very well. We have in the simulation, there's no legs in the view of the robot because the camera is top down looking in front of the robot. But when you have a depth map on the robot looking forward, the legs show up. So we have to use this leg mask to prevent, to make the sim real transfer to happen more smoothly. So these are some quantitative performances. So if you have perceptive reinforcement learning, of the 8 joists, we can climb 7.8 out of 8. We did a bunch of trials, and the average time is 3.4 seconds. But if you have just a blind policy, you can only climb about 2 joints. So this shows the need for perception. And of course, if you use the original robot manufacturer's controller, it just can't climb over any joists. I'm going to switch gears and talk a little bit about drone survey for 3D thermal modeling of buildings. So when people want to today inspect buildings for thermal leaks, there's a human operator with a handheld thermal camera, walks on the ground, looks up, points the camera on the building. Then when he or she sees an anomaly, freezes the picture, makes an annotation, and has to specify where that anomaly is. And of course, this process is error-prone because the user could have trouble exactly understanding where the problems are, but also the user has to real-time diagnose the images that are coming. So if they get tired, they could mess up and miss thermal leaks. And also, if you're on the ground and looking up, the camera gives a very low resolution images of the higher floors. So we developed this workflow also for the eRobot competition, where a drone captures images. So here's a big area in Alameda, California, where we had 2 large circular green pads of flying with a drone that has both thermal and also RGB cameras. Then we pass it through commercially available Pix4D software to get a nice 3D point cloud. Then we pass it through our developed 3D modeling algorithm that shows here. This is a very simple 3D model with only 4 kilobytes worth of data. And then we take the thermal camera pictures and we map it over the model. And so the user will have a 3D model that's texture mapped. You click on a point on the building and it shows you the thermal pictures. And hopefully now you have everything in front of the user and they can rotate, annotate, interact with this 3D model and examine the thermal pictures everywhere on the building. And they're not going to get tired. If they get tired, they can come back and multiple people can look at the images instead of just one person, etc. You can build on top of that system to do thermal drone survey for what's called measurement and verification. So generally speaking, when you retrofit buildings, you wait 1 or 2 years to accumulate utility bills to compare the post-retrofit utility bills against the pre-retrofit bills in order to figure out whether the retrofit worked or not. Now, you can use this system that I just talked about to look at the pre and post-retrofit very easily. Now, if in case you don't want to generate the whole 3D model and go through the trouble of computations that's needed, and also in case building science experts are not willing to interact with 3D models because that's not what they're trained to do, that it's also possible to just generate panoramas. So this is a trailer, a DOE, Department of Energy trailer in New Mexico that's used for testing purposes. It's a weatherization lab trailer, and we can insert and remove insulation from it at will. So the idea here is we we try to create a panorama. The picture that you see up here is an RGB panorama of this trailer. And so the idea is that we want the user just simply click on a point on the panorama, which is a lot easier to generate than a full-blown 3D model, and then look at the thermal picture associated with that. So in this example, we removed insulation from this portion of the trailer, and this is the thermal picture that we see beforehand. And then we fly again by putting the insulation back in, which simulates after retrofit, and this is the thermal picture you see. So you can compare before and after very nicely. Now, one caveat in this system is that when you're creating the RGB panorama, to make the model making easier, you kind of have to capture the RGB pictures from far away. However, when you capture the thermal pictures, you need to be up close in order to have high resolution thermal images. So there's some tricks we played, but which I won't have time to go over it, in order to enable both registration between the double capture that you do. The first capture from far away, just with RGB, and the second capture much closer with thermal images. You can also, if you're taking thermal images of buildings, you can also use it for stud detection. So studs are important in buildings because if you, for example, if you're panelizing building with insulation panels, which is one of the projects we're involved with, you need to know where the support structure in the building is to hang heavy panels off of, and usually you can hang it off of where the studs are. Now, it's easy to detect studs from interior of the building, but translating that to the exterior is very difficult. So while you're at it, if you have a drone and you take thermal pictures of it, you can take individual thermal pictures of a building, which are pretty distorted, and you go through the following 3 steps. So you first undistort them, then you stitch them, and you do perspective correction. And when you do that, you get and you stitch them together, and you get something that looks like this. And as you can see in these pictures, the studs are very visible. So then you go by, a human being goes by hand and clicks on these things, and there you can figure out where the studs are. You can also use thermal imagery to determine the locations of windows in tall buildings, and that's very important in estimating what's called window to wall ratio, which enables you to do energy modelings of building, which is also an important element in any retrofit. I'm going to play a quick video here, just show you an example. Everything I showed so far, there was a human controlling the drones. Now here's an example of a robot that automatically
we present 2 demos of the robot autonomously mapping and inspecting 2 buildings. In the first segment, we demonstrate autonomous mapping of part of a commercial building. On the left is a floor plan that the robot is creating real-time autonomously, and on the right is a robot exploring the space autonomously. Notice that the robot is not controlled or guided by a human, rather it is mapping autonomously. In the second segment, we demonstrate autonomous mapping and thermal inspection of parts of a residential building. In addition to the floor plan and the robot, we also show the thermal camera feed in the process. Note the studs in the walls and the lack of insulation.
We have designed this intuitive user interface to help building inspectors visualize all the useful information in one place and save them from the hassle of labeling data by hand. The orange dots represent the obstacles, or the walls. The blue dots represents the path the robot was traversing. If you click on it, it gives you a side-by-side comparison of the RGB image, the thermal image, and the potential thermal anomaly detected by our computer vision-based algorithm.
Oh yeah, and I'm going to stop here in the interest of time and move on to the next part of my talk. So next I'm going to talk about drones traversing inside buildings and creating models, 3D models of the building. So here's kind of the workflow for this work. So we're doing 3D indoor modeling with using drones and applying some nerve-based techniques, neural surface reconstruction. So here's our drone flying inside 2 floors of Corey Hall in UC Berkeley. We capture RGB images. We pass those images into structure from motion algorithms. Typically classical ones would do the job. We also pass it through this 2D CNN segmentation. The output of both of those goes to this box that does neural surface reconstruction. Now, because we're interested in modeling very large areas, we can't really apply neural surface reconstruction to the entire data at once. So we do that on a block by block basis. And we, of course, we process the boundary between the blocks to have some sort of a smoothness. So what comes out of this neural, so the input to this neural surface reconstruction is the structure from motion and also the 2D segmentation, in a sense saying where the floors, walls, and ceilings are. That's the kind of segmentation we're doing. And what comes out of it is a sign distance function and color, as well as a semantic logic as to which part of an image corresponds to floors, ceilings, and walls. And then we pass that information to geometry extraction model in order to create point clouds, mesh model, surface reconstruction models, and also apply a polygonal surface fitting to get a model of the building. So here's two arbitrary views synthesized using this new approach and using traditional cold map approach. As you can see, this method produces much nicer looking view reconstructions. And here's an example of cold map versus our model in terms of the 3D texture map model. And I'm going to play this video just to give you an idea of a little bit more the fly through of the building with the reconstruction images, comparing our method against cold map. As you can see on the right, cold map has quite a bit of error, and on the right, our method is quite a bit smoother. So in the interest of time, I'll pass through this. Okay, the last part of my talk has to do with incremental learning for automatic asset detection. So consider the following problem. We want to detect all the important assets, let's say sprinklers, electricity outlets, or various other fire extinguishers that are important in facilities management. So here's one of my students, kind of like walking around in my lab. And the first thing she does is she clicks on the corners using the AR application on a smartphone to create a geometry of the room. And then she points the phone at a particular asset, and you can easily imagine how one can train recognition algorithms to recognize that asset. Now, of course, the recognition algorithm doesn't work perfectly, so we have a human in the loop. If the recognition algorithm screws up and gives the wrong label, then the human fixes it. And then as the day goes on, at the end of the day, all those errors that the recognition engine made are used to retrain whatever system that you had used, that whatever deep learning method that you'd used to classify things at the outset. Now, the problem with this is that as you're having misclassification, the system can learn real time. It can do online learning. So how do we accomplish that? So one of the methods that we came up with is use memory augmented neural networks to learn incrementally. So here's a kind of like overall block diagram of this. So there's inputs coming in. There's a controller LSTM that does the deep learning stuff, and then there's this external memory that we pass information to LSTM back and forth. So this external memory really is used to adapt quickly to new instances. So if you switch to a new building and your system no longer recognizes the kind of Wi-Fi routers in the new building, as you correct it, the external memory helps you to learn it. And then on the other hand, at the end of the day, when you're all done and you've collected all the mistakes, you can do traditional updating of the weights of the to this LSTM model, and this is the long-term memory aspect of it. And so in a way, it resembles the way the human mind operates things. You have a portion of your mind that learns quickly, and then when you sleep at night, that data gets transferred from that portion to the hippocampus, where it stores things in a more permanent basis. I won't go into the details of it, but this basically shows the same process. So there's an external memory for fast adaptation and internal LSTM for slow adaptation. So basically the overall flow of the system is like this. You at the beginning of the day, you load your model weights onto the phone for a new session, a new building. You've trained the best you can the night before, for example. And then during the day, you collect data, and we use external memory to, as their system makes mistakes, we use the external memory to quickly learn those mistakes so that the user doesn't have to continuously fix the same mistake over and over. And then as we do that, the performance improves. And then finally, when you're all done, this newly collected data in this session is used overnight, for example, to train the long-term memory weights, the LSTM. and we go back to step one. So how does this system perform, this incremental learning? It fantastically. So here's an experiment where we did from day 1 to day 2, day 3, day 4, etc. This is the traditional scheme using just the SSD, and this is the online incremental learning I just talked about. So as you can see, as we move from SDH to each day we do a different building. So SDH stands for Sutardja Dye Hall, and EH stands for Echeverry Hall in Berkeley. So in the traditional method, as we move in day 3 from Sutardja Dye building to Echeverry, there's a huge performance drop, whereas that's avoided when we do this incremental learning. So that's really nice. Furthermore, we can collapse this incremental learning method that we have into TensorFlow Lite, and with very little performance drop. And finally, the offline training has been reduced from about 22 hours to 4 hours. This is the overnight training that we do. So it's one of those situations that's win-win-win. We improved performance, we improved speed, and speed both to the offline training as well as the online inference time, which is shown on the right-hand side. Okay, I'm going to wrap up real quickly here. So I talked about how robots and drones can play an important role in evaluating and verifying building energy efficiency and fixing it, actually retrofitting it. All of these systems, so we've begun to explore the tip of the iceberg as far as using machine learning and deep learning to help with autonomy, navigation, manipulation, and recognition. And so future work involves automating all of what I just talked about. I'm going to stop now to answer any questions.
Right. Thanks a lot, Dr. Avid, to deliver an exciting talk. Any questions? Yes. Well, yeah. Either you can come or I can read. Yeah, you can probably come. It's a small room.
What's my question?
It's you can just speak to it, I think.
Thanks for the great talk. Sorry, fairly simple question. The second item you presented with the RGB and thermal image registration using the drone, do you have any details about roughly how expensive those drones are, and whether there's any cost difference or hardware differences in the 3D and 2D modeling you demonstrated, or whether it's exactly the same hardware, it's just different post-processing? Thank you.
Yeah, that's a very good question. So for both methods, you can use once a drone that just does RGB, and then another drone that just does thermal. But as it happens, we had purchased, and I think I mentioned it here, we have purchased the DJI Mavic 2 Enterprise Advanced, which captures RGB and thermal both at the same time. And the cost of this at the time we purchased it, if I remember correctly, somewhere between $8,000 and $9,000. Now, the difference between this system where we have panorama versus this system where we create a complete 3D model is that the complete 3D model, you have to make sure that you fly, the building from all angles, you capture every angle, you do a point cloud generation, then you do this modeling, which could need some human intervention. So at the end of the day, this pipeline, in terms of capture, the two systems are nearly identical. They're not that different. They both needed, one round of RGB capture and one round of thermal capture. But in terms of processing, this processing pipeline is much faster. And it turns out that the building science people really prefer this method over using this kind of an interactive system over panorama over the complete 3D model. Did I answer your question?
We have time for one quick question. Yes, please. Yeah.
Yeah, I have one question on your asset detection part of the talk. And when you look to your practical experience, how do you deal with, let's say, incompetent humans making errors? Because when you then update your model in the evening.
You're talking about this part of the talk, is that right?
Yeah, exactly. Because if a student does it, I believe they're doing it diligently and well. When you do it in the wild, you will have people doing it quickly and very sloppy.
Yeah, I think the main thing we're trying to do here is in this example, I didn't explain it very thoroughly, but we have 10 classes of objects that are mostly related to safety of buildings, like fire extinguishers, sprinklers, Wi-Fi routers, electricity outlets, etc. So, you know, it's at the moment anyway, the experiments we did, the classes were not very large. But you're right, if the labels that the human generates are erroneous, I guess it affects the learning in an adverse way, but hopefully those mislabels are a lot fewer than correct labels by humans. That's kind of what we want, why we want to have humans in the loop. And my point is that, I mean, the humans could have an easy time recognizing things, but if they clicked on the wrong button, you're right, they could make errors. But yeah, it does introduce inaccuracies in the mislabeling.
Just, you know, because I work for a company with 120 million cloud-connected lighting nodes, and you would be surprised on how sloppy things are commissioned and labeled. Just as a, yeah, I mean, it's unbelievable. Yeah.
Yes, that's a very good point. You know, we always tend to think of humans as being perfect, although even though in the middle of my talk I did say humans are error prone. But you're correct in this example, is that if the human mislabels it, it could throw off the system. That's very good. That's very correct.
All right, thank you again, Dr. Abideh. And so let's move to our next speaker, which is Dr. Pingbo Tang, who is an associate professor in civil engineering from Carnegie Mellon University.
Hello, everyone. Could you hear me okay?
Yeah, can hear you fine. And we
Yes.
see your screen, although it's, yeah, now we see the presentation. Yep.
Great.
Yeah.
Yes. So should I start? Okay.
Feel free to start. Yes.
Okay, great. Thank you, everyone. Thank you for the workshop organizer inviting me. I feel very honored to provide some what I learned in the past few years about how computer vision could be useful, and what are the computer vision roles in civil engineering application. In this case, it's a safe and efficient operation of our civil infrastructure, such as airport and a nuclear power plant. Let's move. Dr. Zakko already gave us a very, very good view about robotics for civil engineering application, and we are trying to move it to a direction a little bit more on the AI and the human. So let's take a look at this decision-making scenario. When we try to look at a nuclear power plant in the United States, many of them, they are built 50 years ago. And a lot of them, when they're getting old and older, like a human, they become old and old and become less efficient and wasting some energy. Also, we are also have concerns about their safety for like radiation leakage and those things. We need to have a maintenance for those nuclear power plants. So they have those 20 to 30 days of outage, which means they refuel the nuclear power plant. At the same time, they do maintenance for the mechanical system and the structure system, such as the cooling tower. Then for such like a large kind of assistance, the challenge for finish the maintenance in 20 to 30 days, it's pretty difficult because there are 2,000 more refueling activity, and there are 2,000 workers at the same time. They are working on different parts of the job site. Then it's a highly dynamic working environment. There are safety concerns, and many workers, they might work collaboratively and causing troubles for each other. And sometimes they have a control room and they have a field operation, and people in the control room, they look at the data collected from multiple sites and try to make a decision to coordinate the activity and make sure there is nothing going to cause trouble for any worker. Then there's safety concerns. It's everybody follow the safe procedures. This is not a fixed procedure because the environmental keep changing and everybody is doing their job. It's a dynamic environment. And the efficiency is a big problem because if we think about Phoenix as a big city, they only have one nuclear power plant and we lose the nuclear power plant for 1 day. That costs 1.5 million. And we need to finish everything efficiently and safely. The human in this process plays two types of roles. Number one, in the cyberspace, in the control room, and the people look at the different data sets, including like an analog control room, they look at real sensor measurement. In the digital control room, they look at touch screen. Then they look at all those things they can see from their dashboard and make decisions. And another group of people, they are called field operator. And those people, they because a lot of those information could not be captured by the sensors, and people have to look at it and they have to make sure that everything is okay. Just like Dr. Zarko has presented, those robots can moving around in the building and use computer vision algorithm to identify something which might not be directly measured by a sensor. Then if we look at this, it's a remote action and a field observation collaboration. And the multiple group of people, they work in the control room and in the physical space, they're collaborating to drive a big machine. And that big machine is nuclear power plant. It's a very, very dynamic system. So when we look at this dynamics of a human cyber physical infrastructure systems, and on the right side, it's the time needed for people to finish their job. And on the left side is the algorithm, sensors, and to collect enough data to find out what are the time allowed for people to do things. Because this is a highly dynamic environment that we want to make sure that we get the real-time information and estimate what are the time available for people to carry out their task execution. Then when we look at this whole system dynamics, then we look at the different interaction. The interaction could be between human and the physical infrastructure, and could also between human and human, and could also between human and computer. Then HP, HH, HC on the right side, we are talking about different type of interaction. Then when we look at the vertical axis on the right side, it's a decision-making process. Recognize things, make a decision, and execute their task. Across this different type of interaction, we have a different reliability issue. For example, people might not follow the instruction exactly, and sometimes people might feel difficult to make a decision when the context changed. Then we also look at the digital control reliability. If we go remotely, and you might not get enough information from all the sensors because some observation can only be made in the field. Then once we take a closer look at the computer vision, and of course, we need to get the information from the site. And we also need to connect in the site better with the control room. Then what we can do, and I'm talking about virtual labels in videos and real-time views of workers to get the predictive and the secured control. And from this left side, we can see that the field worker, when they are doing recognition, they need to recognize the correct things they should observe and the correct verb they should operate. And for the larger scale, they would also need like a virtual labels to find out at the system level, what's the progress of the construction process and the maintenance process, and to make sure that different tasks is not going to cause inconsistency and cause a safety concern. On the right side, it's more about the decision makers. When they see the virtual labels and highlighting critical things, they should pay attention. For example, if we sit in a big room and which have maybe 100 screens and maybe 1,000 sensors, then a very experienced person know where to look at, but not everybody know where to look at. Then the computer might help human to identify what are the critical screens that should pay more attention and which sensor are more critical and more vulnerable right now. Then this kind of a problem could be extensible and could be applicable to different decision-making scenario. And we'll talk about the nuclear power plant outage control. And the similar control room and the field operation also happens in other cases. For example, airport operation, which also has a big control room, has a group of people who are observing multiple screens. And which also has a very dynamic environment, the aircraft landing and the departure. And the right side, you can see it's an example, Pudong Airport runway incursion. And actually, in the United States, in January and February this year, there is a bunch of runway incursion in New York Airport and in some other airport. And FAA is also discussing about how to improve the safety of airport operation. Then once we look at this, and we talk about all kinds of human interaction, human physical interaction, human cyber interaction, I would like to give you a few examples to illustrate how computer vision could be helping us. I mean, all of you are much better than me. I'm not a computer vision expert. I'm more of a from a civil engineering systems point of view, and to pose a few questions, and which could be useful maybe for you. And I would also benefit from you and from your expertise about computer vision to find out, is there anything we can do better for civil infrastructure systems? So let's take a look at this human physical interaction problem. And I'm going to use a nuclear power plant operation safety as an example. And I'm also going to introduce air traffic control for control room example. And the human interaction is a much larger area than what I think before. And I could not cover in today's talk. So for field operation, then we have a connection between remote room and the field. Then once we look at this, the information could be collected from the nuclear plant field to the sensors and captured by sensors. Then the control room might send back the control signal to say, okay, based on the sensor signal, what you should do. Sometimes if some sensor has a fault or it's out of battery, and it's going to have trouble to get enough information to support reasonable and reliable decision-making for the control algorithm. So we need human. When we look at a field operator, the field operator is going to get the command from the control room. They're going to say, this is the procedure, and this is the task. Please go to the site and double check a few things. And they're going to give you give them the field operator a few information, say you need to double check a few things. Then the field operator is going to say, okay, I'm going to collect the information, then report back to the control room, because a very experienced person, they got a lot of experience that they know where to look at that. And based on the instruction, they're going to find out what's really happening in the field beyond the sensor network has been captured. Then the control room is going to close the control loop and make the decision. However, a few things might happen because of human mistake. For example, the control room operator might miss a few to-do lists, critical to-do lists for the field worker to follow. And the field worker, they might miss critical information when they are even in the field, or like people who lack of training, and they might miss critical information from the site. Then how we could improve this? We are thinking about maybe we should combine human and machine. And the machine part should be from the control history. And we could use control history to generating a list of things. The computer is not very sure, and the computer want to use those information as a starting point and ask human to check the critical things in the field, which has a high uncertainty and also has a strong safety consequences. Then we can help people to make a good data collection through human, check a few things computer is not very sure. Then once we do this, we want the computer system to give the human some instructions about where they want to go, and what are the critical things they should check, and how computer can simulate what if they do this, and what are the uncertainties about the things is going to happen, such as how the flow loop is going to change. In a nuclear power plant, multiple flow loops are the critical part the field operator should be care about, and the control room people need to be responsible for coordinating multiple flow loops. Then the computer vision is going to play a very critical connection between the field and the control room. The information collected from the field, such as the field operator, the carrier camera, and they go to the site, but at the same time, they also connected to the control room because the control room has all the sensor network data. Then once they're matching those information, the worker is going to have augmented reality glasses to find out what are the critical things they should pay attention to. Then this is the overall framework as part of the vision. We look at how real-time environmental videos combined with a building information model. Then the computer system has a reasoning process to identify what are the critical objects and what are the location people should go, and what are the risks and what are the compliance of safety compliance of the people's current working process. Then I highlighted the computer vision on the left side because that's the part we get the real-time information from the site. We also capture the reasoning algorithm because the semantic information in human brain and also in digital models such as the building information model could help us to guiding the decision making. So this needs multiple sources of data. It's not just video. It's not just image. We have a computer vision algorithm work together with multiple things and to support context-aware safety information display. And I put the objectives of such kind of system. This system should integrate the real-time information, the field of view of the worker, and to visualize the critical object we call smart virtual labeling to allow the worker to find out what are the things they should check in the field. Then the first data source is called sensor log. In this case, we look at the sensor network data. This is a simulation. We use the Rancor. It's a simulator created by Idaho National Lab to simulate the nuclear power plant operation process. And we simulate the fault of different sensors. And we also try to use computer algorithm to analyze those sensor logs and to predict if we have a certain sensor data collected, what are the likelihood people should taking a particular action? For instance, when I look at the core temperature, the cooling flow data based on the job history, and we can have this successful and not so successful control history to allow the computer algorithm to learn. If I see this kind of sensor data, should I wait or should I turn on the valve A at what time? So actually, this type of work, it's right now is still in the infancy, and we find out the F1 score is not very high. And we try to understand how the system dynamics could be leveraged to predict the best timing of control action, the control action including the best timing to observing a sensor measurement and the best timing of taking actions. Then the second part, it's we go back and we say, okay, computer, just look at the sensor network and we train the model, and maybe the model should be improved. But on the other side, we may want to look at a human experience. And we do survey and interview and ask people a few questions about what are the critical information they should pay attention to, and in what stage of the task execution in the field. Then those questions we formulate into surveys, and we use the survey to get a lot of opinion about what are the critical factors influence people's decision-making about where they look at and what they should do at what time. Then to prevent the human mistakes. Well, briefly, the main findings is that with those survey results, we find out we use an algorithm called used by social scientists called factor analysis to identify what are the group of factors that could be emphasized or de-emphasized by the domain professionals in different situations. So in this case, we ask people, say, in what stage, planning stage, execution stage, and reaction stage, what are the most important information? And they categorize those information into three. These three categories not defined by us. It's based on the semantic analysis based on their responses collected by the survey and the interviews. And the factor analysis reduce the dimensions of those semantic meanings and grouping them into three groups of information needed by people. So those are workspace dynamics, and the workflow prognostics, and the hazard. So those are emerged from the interview results. And use those three emerged categories of information. And we also did an interview with those people, say, okay, in different stages, are those three categories of information have a different importance level. Then this is the major findings. We find out from the left side to the right side is from the planning to the execution and to response implementation. Response implementation means when they find something, they are going to implement like a modified plan in the field to deal with the discovery in the field. Then what we find out is that the safety and the productivity, if we emphasize different things, and the people has a slightly different emphasis for different category of factors. For example, the workspace dynamics, it's emphasized in all stages if we emphasize safety, but when people are walking from their current location to their work location, so they are not going to emphasize dynamics workspace dynamics very much, but they are going to pay attention to the hazards because they need to make sure that they are going to detour those critical area which has a radiation. Now, but on the right side, if we look at the productivity, if we emphasize productivity, the workspace dynamics is not going to be that critical, but the hazard becomes like a critical for the productivity category. So more details are in a recent in a paper we're going to publish very soon. And if you're interested in those survey results, please let me know. We look at another data sources like a meaningful and explaining what are the critical information people are looking for on site. We use the manuals, operation procedure manual from the nuclear power plant and define the ontology to support natural language processing algorithm to identify the potential events and associated actions from the operation manual. And then matching that information with the real-time sensor data readings and to find out, to explain what is the best timing for people to carry out action based on the procedure defined in the manual and the real-time information produced from the sensors. Then we come to the computer vision. Then the computer vision algorithm could use multiple sources of data, such as IMU. I think robotics research is much better than me to explain this. We try to localize the where this worker is based on the floor plan, IMU data, and the field of view of the worker to decide where they are. Then depends on where they are, depends on the destination of their task. It's a navigation process. Then during that process of navigation, they should avoid the hazard. Finally, when they arrive the job site, they should pay attention to certain critical objects and make decisions about what to pay more attention and what they should do in a sequence to complete the task. So for this one, we need to do a lot of critical object detection. And this is the navigation algorithm developed by our collaborator at Ohio State University, Dr. Yermas. They are using those IMU sensor data and the real-time on-suit camera of the worker to generating the trajectory of the worker when they are traversed from one location to another location to ensure that indoor navigation without Wi-Fi, without anything, is going to produce a precise location of the worker. Then the other one is when we know where they are, we need to label some of those like a critical object. And we have been developing virtual labeling of critical objects. And one critical research we have been looking at is that how we could detecting critical objects across different workspaces in sequential learning tasks. So what is sequential learning? Means once the computer vision algorithm learn from one data set, are we able to collect another data set which might have a slightly different labels? For example, in this data set, they label as worker, and on the other one, they label them as a people. Then we try to develop an open construction taxonomy to semantically unify multiple data sets. And we also develop an algorithm to understand if a computer vision algorithm learns sequentially from one data set, then incrementally to learn from another data set with some kind of a semantic interpretation and unification to make the computer vision algorithm learn something new without forgetting the previous scenario. So this is a very, very preliminary study, because if we know everything ahead of time, we got the other data set, we train it, then the overall performance is going to be very good. On the right side, you can see the joint training. If we know collect all three data sets and train the algorithm, the performance is pretty good. But if we're assuming we only have a data set A, then we learn from data set B. And we want to make sure that when we learn data set B, we're not going to forget what we learned from data set A. Then our algorithm actually performs better than the other approach, which has been doing this incremental learning from different data sets. Then we also look at the safety knowledge combined with a human skeleton detection. Then for the sake of time, I'm going to skip this. Then we also look at the label issues with some of those safety violation detection from construction site. And for the answer of the question from the previous presentation, actually we're looking at how people making mistakes when they're creating labels. Then we use a Bayesian network approach to automatically grouping the labels from different people, possibly contain mistakes, and try to estimate the reliability of those labels. And our approach shows a pretty significant improvement compared with the majority vote. So I'm going to skip this one. And we combine this thing together, and we want to make sure that we have a real-time context-aware safety display for civil engineer. Then I will give a very, very brief introduction about the air traffic control room for predicting control failures. In this case, it's a control room people. We look at their behavior in the room, and we look at the traffic scenario, and we do experiment and to use human behaviors together with the traffic data to predict what's the likelihood people are going to make mistake. Then we model those traffic complexity, human behavior, and to predict the human workload, and to estimate what are their workload and how likely they are going to make mistakes. Then use an LSTM algorithm. We try to predict what's the likelihood in the next 5 seconds, 10 seconds, 25 seconds, people are going to have a mistake happening in the sky and causing troubles. And what we find is that using multiple features together, we can achieve a pretty good 50 seconds ahead of time, 80% plus prediction of those separation errors. I will stop here because I think I'm out of time, and I think I should leave time for some discussion. Thank you.
All right, so thanks, Dr. Tang, for a great talk. Any questions from the audience? Yes, you can actually try to talk here. I think it's not really.
Yeah, thank you for the great talk. I have a question about the AR goggle usages. I want to ask, what do you complain about the current pose estimation system when you use AR goggle? For example, we have no complaints. Vision is awesome, or you have some complaints, say the failure rate, say 10% of the time the pose are completely off, or latency, some delays in how people see, that some people may complain, or how about energy? The current device doesn't last for say 4 hours. So what do you complain the most about the AR goggle pose estimation system?
Oh, you mean pose estimation for the worker, right?
Yes. Do you have any complaints? What do people complain the most for this like pose estimation piece?
I'm not very familiar with those. You mean the computer vision based approach for skeleton detection, or you mean those IMU based system? I'm not very familiar with that term.
Anything when you use AR goggle, pose has to be correct to overlay
Oh,
proper
I see.
information.
Oh, augmented
People usually
reality
not
glasses, right?
understand.
Augmented glasses, right? So I think the major thing I see from here is that the AR goggle, I finally know the term. AR goggle is that it lacks the intelligence for context-aware labeling. So what I mean context-aware labeling is that just because of the semantics of describing what is safe, what is not safe, how different object form a risky relationship, and as people need to pay attention to. And the AR goggle may need to integrate those kind of like intelligent virtual labels to support the field worker to understand where they should pay more attention. And right now, the AR goggle is overlaying some of those information on top of the physical field of view, which is useful, but it's a little bit overwhelming. They don't need to see everything, right? They may just need to see the safety, efficiency, critical object for that moment. They do not have to get like a 100 object overlay with the site and when they already have a very heavy mental workload. I think that's my major. Am I answering your question?
So it sounds like the pose. So the say HoloLens has a bunch of sensors. They estimate where the device is. So that part seems to be very solid. You have no complaints. More like you plug in.
I think the real time thing is already from our side, for our research purpose at least, it already satisfied the our needs, I think.
Yeah, thank you very much.
Yeah, no problem.
Any other questions? You can also just talk from Zoom if you have any questions on the Zoom side. Any other questions from the audience here? All right, thanks a lot to Dr. Chang for your great talk. And then now we are going to have a coffee break for about 15 minutes, and then we will come back at 10:50 for the winner presentations of the 2D challenge. Right, thank you, and then we'll see you in 15 minutes, in about 15 minutes. I was wondering, no, I was gonna stay there. I was just wondering if I say something from here, can you hear it in Zoom fine? So that's fine. Well, yeah. So maybe people don't really have to go there. Yeah. Hello. Yeah. Yeah. Okay. So this is we have just people here then. Yeah.
Hello.
Yeah, I can hear you. Can you hear me?
Okay.
Yeah, maybe try to share screen, just testing. Can you try to share your screen or?
I will try to share my screen.
Yes,
Okay.
just for testing. Yeah,
Just for testing. Okay.
sure.
Could you see the
Make-
screen?
Yeah, this works. Yes.
Okay.
Right.
I just stop it.
It's fine. Yeah. Who is going to present? What's the
It
person?
should begin on 10:50, 55, I think.
Sure, we can tell them that will be 5 minutes late.
Okay.
Yeah. And then who would be presenting? What's the name of the person who would be presenting?
I'm Chen Peng. I'm Chen Peng
Okay.
from
Okay.
Tsinghua.
Sounds good. Yeah. Thank you. I
Okay.
think we are all set now. maybe we can have you start sharing. So I think your talk is gonna be in 2 minutes. So Pam, maybe you can start unmuting yourself and start sharing your screen. Yeah, just start sharing. Yeah, I think it's already 54, so feel free to start almost. Yeah, just start sharing. I'll briefly introduce you, and then you can start presenting. Yeah, so maybe present the slides.
Okay.
Good.
Okay. I'm Chen Peng from Tsinghua University. We are in the school. We are in the school of software.
Okay.
This is our. Okay.
Maybe I can briefly introduce you first. Yeah. So sorry to interrupt. But so now we are back to our workshop, and oops, I think this coffee break needs to go. 1 sec. Now we are back. Yeah, so now we are back to our workshop. We will start our presentations from the challenge winners, and we will start with the 2D challenge. And our first presentation would be delivered by the winner entry of the 2D challenge, which is from BIM research group from Tsinghua University. And Cheng Pan would give the talk, and let's welcome him. Yeah, now you can feel free to start.
Okay, thank you. Okay, we are the CBIM team from the Tsinghua University. We are led by Dr. Ge Gao and Dr. Gu Ming in the School of Software. Actually, we attended this workshop last year, and we also made a presentation. Our method is quite similar to our last year, so I will do it quickly. Firstly, I will give an overview of our method. Then there are data processing and semantic segmentation, and finally the work extraction and optimization, and finally some conclusion and discussion. For the input point cloud, we firstly do data cleaning and denoising, and then we will do the semantic segmentation. This semantic segmentation, and then we will fitting the walls, fitting the columns, fitting the doors for the scene. Finally, we will output our results. This pipeline is the same for the 2D task and the 3D task. We use the same program to output the results for the 2D challenge task and the 3D task. For the 2D task, we focus on the wall, generalization and optimization. For input data side, firstly, we will do denoising. This means we will clip the outer points and do cleaning. And then we will do semantic segmentation. This is done by point transformer and some other deep learning models. And then we will do plane fitting. Plane fitting is done by using the whole point cloud scene. Next, we will fitting the doors, fitting the columns and walls in the scene, and will organize and optimize the walls to generate a good layout. Finally, we will realize our results and upload it to the website. The data processing pipeline is more detailed at here. For point cloud, we firstly remove the outliers by the XY planes, and we detecting the ceilings and the floors by the proportion of points in the Z axis, and then computation the normals for the point cloud we will do downsample and normal computation firstly, and then we will do the semantic segmentation. Here we will do classification, the point after classification, the point clouds in the data set will have these labels, binary words, columns, doors, and others. This classification is the binary classification that we have a model that just classify words and a model just classify columns and doors. For some data, some data sets in the 2D task, like two basements, we found that our point transformer couldn't provide a good segmentation results. So we used DODA, another deep learning model, to do semantic segmentation on the two basements and some garage data sets. With these deep learning-based models, our generated segmentation results is just like the ground truth we are provided. The next step is detect and to generate a wall layout from the data sets. Here we have two kinds of methods that can complete this problem. The first one is do it on the 2D image or 2D grids, like the methods displayed in these two figures. The first one, they use the least square methods to detect the outline lines in this point cloud, and then use some regularization to make it in some organized lines. And the second one, this method get a clean slice from the whole thing, and in this slice point cloud, the fitted lines to make it in clean layout of the whole thing. But this method on the 2D image or grid have some shortcomings. Firstly, they usually need a good slice of the scene, which will lack our automation. And second, they need some regularization methods to make these lines very clean. But this sometimes this is difficult. And third, if we do this problem on 2D, we will lack of some 3D information or point clouds, like the height of some wall. Height of some wall are very important to select and fitting them in our pipeline. Instead, we choose to detect the wall shape on the 3D point cloud data. Our data input is the whole thing, not the just semantic wall results. Last year, we only used the semantic wall results to detect the wall shapes, but we found that there are many missing walls if we only use the semantic wall results. This is the whole point cloud. After to visualization, we clip the floor and ceiling. This is the fitted wall planes. They are in alpha shape forms, and then we will use these alpha shapes combined with our semantic segmentation to generate a good wall layout. Here, the first one is our semantic segmentation results, and the second one is our fitted alpha shapes. We will combine these two results to select some candidates, wall candidates. The select criterion are the dimensions of alpha shapes. If the alpha shape is the length or height is bigger enough, we will it will have high probability to be selected, and the proportion of wall points on the each plane. If the proportion of wall points on each plane is very high, we will select it as a wall candidate. Next, we will use the selected wall candidates to generate a wall layout. Here are two kinds of methods that can do this problem. The first one is do global optimization, like the method used in polyfit or in KSR. They are they are organizing the detector planes and then do global optimization. It means that they extend each wall, extend each plane, and then let each plane will cross with all other planes, and then they will find a good layout by some optimization functions. This will lead to very high time complexity, at least n square, and this usually lead to some over-optimized results with some overextended walls. Meanwhile, we found that this is not necessary for the building point cloud sinks. In many cases, for the building cloud sinks, they are usually very large, and we can just do it locally. So our final method is that we just do the wall layout section with some locally optimization operators. It means that our each wall is only updated by its nearby walls. For this wall, it may be only updated by this wall and this wall to adjust its ending points. So each wall is only updated by its nearby walls. We can do it very fast. We here use a modified binary search to search the wall endpoints and their corresponding walls on the 2D grids. It is very fast, and we can process each wall very quickly. We do iteration for each walls to group them, to merge them, to connect them, so we can finally find a good layout. Here we have 4 operators to update each walls, and the adjusting steps used in the operators, they are grouping until we find a good wall layout. We will stop our iteration to finally output it. This method is very time convenient because in the ideal situation, it is just nearly linear speed for each wall is only updated by its nearby walls, and the nearby walls of each wall is in a constant level, and we can avoid many overextended walls because we don't extend them globally. The four operators used in our program is as follows. The first one is extend. We have 2 walls. They are nearly they are on the same line, and then though they are not connected, we will make them into one wall by extend them. And next step is the next operator is merge. If 2 walls are parallel and their distance in this direction is very low, we will merge them in one wall and change the weights of these 2 walls. The weights of the new wall will be the distance of the 2 original walls in their normal direction. And for this case, we will trim this first walls. It means that we will put this endpoint on the line of the second wall to do alignment, make it more organized, make it more clean. The final operator is connection. It means that we have 2 walls. They are like so, and their endpoints are very close. We will make this endpoint into one endpoint so that we will connect them. We do this for operators iteratively, use the growing steps, and then finally to generate a good results. There are 4 examples. This is the extend example. We need to extend this plane so that it could connect with the second plane. And for these 2 walls, we will merge them into one walls, and their weights will be this distance. And for this blue wall, we will trim it by the pink wall. And for these 2 walls, we will connect them. Our final result is as follows. For some testing data sets, this is the mid office, and tall office, short office. Here we can see that this is a big word, but it is merged from from many small words. Each small word is merged, so that we could finally get a very big word, and its width is the distance of this small words in their normal direction. We found that the results is that we found that the semantic segmentation play an important role in filtering candidate word planes and in generating the word layout. Local optimization is computational convenient than the global optimization. And meanwhile, they can avoid the over-optimization results. Our method could provide good results, good word layout for most things under the same thresholds, while the results could be better if we tune them for each type of data. And here are some discussions. We found that the LU score computation for testing data may need some updates. Here are example for this thing. I will generate layout the right one, but the right one nearly always gets the 0 LU in the score. We think that it might have some problem in the LU computation. Some information like the word weights of some external words, they couldn't be computed. They couldn't be derived or computed from the input point cloud data. Here we just set them as a default value. There are still some thresholds in our program that we need to adjust them for different kinds of input data, so that we can generate the better results for each data. We want to reduce this thresholds later. We are still thinking a robust and highly automatic algorithm that could generate high quality word layout for different kinds of building things, which is our direction of optimization later. Okay, this is our presentation. Thank you.
All right, thank you. Yeah, sorry, I muted a little slower, so you missed the clapping in the room. Yeah, any questions for the presenter for this team? Any questions on Zoom? Feel free to just unmute and ask the question if you're on Zoom, please. I have a question. So you mentioned a lot of kind of trying to connect and trim different walls. Do you do the same thing for curved walls, or how do you handle curved walls?
Curved, you mean curved walls?
Yes.
Okay. We just found one data set in the 2D 2D data set. We have one example. For this curved data set, we just do plane fitting without much optimization steps. We just fitting it by the some small alpha shapes. We use small steps to try to make our alpha shape to try to make them make sure that they are as close to the original curves as possible. Yeah, and we haven't done many adjustment or optimization steps for that data. We just do plane fitting with small steps and organize these faces and upload our results for that curve thing. But we think that for the curve thing, we actually need to detect curves. It means that we need to detect circles instead of planes for that data. We can detect two circles from that data set, and we can extend these two circles in the direction, and they are the two mean words in that scene.
All right, thanks a lot. Great presentation. All right. Any other questions? Okay. All right, so let me. Our next presentation will have a pre-recorded presentation, and I will play it from my computer. And just give me 1 sec. Oh, could you actually stop your sharing, Chen?
Okay. Okay.
Yeah.
Thank you.
Okay. So yes. Oh. Right. So.
On the scan to floor plan challenge. The title of our method is floor layer based kernels and pillars of points ++. In short, is FLKPP++. There are 4 members in our team. And Shouhan Chen, Qianwen Zhou, and Dr. Frank.
Sorry. I think there was some issue with the audio sharing, but let me play this again. So this is, before I start, this is from the team from University of Hong Kong who won the 2nd place of the 2D challenge. And then this is from Yijie Wu, Sohan Chen, Chen Yun Zhou, and Dr. Fan Xue. So I'll start playing the video.
Good morning, everyone. Today, we are very excited to share our work on the scan to floor plan challenge. The title of our method is floor layer based kernels and pillars of points ++. In short, is FLKPP++. There are 4 members in our team. I am Yijie Wu, and Shouhan Chen, Qianwen Zhou, and Dr. Frank Xue. We are from Faculty of Architecture, the University of Hong Kong. We are doing research on building reconstruction from point clouds, interactive digital twin buildings, and building design optimization, another optimization for the field of architecture, engineering, construction, and operation. Today's agenda includes 3 parts. The first part is background. We will briefly introduce why we participate in this challenge. The second part is the method, and the third part is results. Automatic scan to BIM is now highly desirable in the AECO field to facilitate the whole life cycle of buildings, from planning to construction to maintenance to demolition. And especially for the Hong Kong case, actually Hong Kong have a large number of aged buildings, and the housing issue is very prominent in Hong Kong. Despite in these high density and high rise cities, the inside buildings could be also very complex and very dense and very different from their design version. So you really need an automatic tool to scan these things into building information models automatically to help to do the decision making in the following renovation and demolition. For the task of scan to floor plan still is the mostly commonly used media to present the indoor layouts and other engineering details in the AECO industry. And actually, there are a great number of archive floor plans in the field. That means we could use relative low cost to collect a large number of floor plans to drive the supervised learning of scan to floor plan. So we also very appreciate the efforts taken by the workshop organizers to construct this benchmark for us to develop automatic solution of scan to floor plan and scan to 3D BIM. And this is the framework of our method. Actually, this is the third year we participate in this challenging, and the framework is developed based on the previous 2 years experience. And there are 3 steps of our framework. The first step is the pre-processing. We perform the room clustering and clutter removal in the pre-processing to get a relative clean point clouds. And after that, we project this point clouds onto a 2D horizontal plane to generate the image data. And then we feed this image into a light prediction neural network to predict the lights. However, the lights predicted by the neural network contain a lot of topological issues. So we design some post-processing steps to repair the lights and then output our final floor plans. The first step, pre-processing. The aims of pre-processing is to do the room clustering and then remove the noise and clutter inside each room. So we first label the space voxel into different types, including the voxels that are very close to the edges and some are very close to the ceiling or close to the walls. And then we will remove these voxels and then cluster other voxels as rooms. After that, we could remove the furniture and some other clutter inside the room. And then have a clean point cloud. Once we have this clean point clouds, we then project the clouds into a 2D grid. And then we have 3 channel images. The first channel is the point distribution of 1 meter layer above the head level. And the second channel is the 1 meter layer below the head level. And the third one is angle homogeneity in the point normals. After we have this imagery, we feed the images into a convolutional network to predict the corners and edges. And we use LCN to perform this task to output the floor plan. However, the LCN prediction could contain a lot of topological issues. So we then use some simple rules to connect the orthogonal lines. And after the line connection, our IOU increases by almost 10%. Yeah, so it's very helpful to improve the IOU. However, even though the IOU increases significantly, due to we create too many lines for the samples. For example, in this example, there are more than 10,000 lines in this case. So this resulting in a relative low precision, although the recall could be relative high. So we then merge the lines that are parallel and close to each other. And then we reduce the number of lines from more than 10,000 to about several hundreds. Then the precision increases slightly, while the recall decreases significantly. So we then consider to break the lines into different categories, such as we break the lines belongs to the doors and some wall lines and some other components. So we do this by 3D semantic segmentation based on the point contrast. And we separate the lines that there are some points attached to the lines that belong to different categories. And after that, the precision increases slightly, and then the recall increases significantly, and the IOU keep at the same level. So this is all the steps of our this year's method. We now present some results. We present the good results firstly, and then some bad results. And we noticed that actually there are 2 main scenarios in the data set. One is the office and the other is car park. So we will organize the following result presentation in these 2 categories. So for the office case, we have 3 cases achieve the IOU higher than 80%. So we can see in these 3 figures, we already found most lines of the floor plans. And you may see in the 3rd case, there are some lines missing in the top left part. This is because there are some large windows in this region. So right now, our method still cannot robustly handle this large window surface. Besides, there are still some unwanted lines in the results right now. And for the car park case, actually we found if we bound the region tightly, and the IOU should be not bad. Even though the precision recall is still not very high in the car park case. We found it's actually not easy to match the ends of segment precisely, so our precisions keep at a low level of all the samples, and we try a lot of methods, but the precision still cannot increase significantly. And the following is the bad results. This is the results with the IOU lower than 20%. So for the office case, we have 2 cases that have very low IOU, and the one is of circular shape. So circular shape is rarely seen in the training data. So both the LCN and our post-processing cannot handle this case well. And the other case is we can already find anything special in this case. And we also think we already bound the rooms quite well in this case, but at the same time, the precision of and the recall of this case is relatively higher than other cases, but the IOU is still lower than other cases. So we are also very confused of this situation. And for the case of car park, we have 2 cases. The result is really bad. This is because these 2 cases contain, the point clouds of these 2 cases contain a very large part of the environment. So our reconstructed floor plan contains many lines that are actually belong to the environment. So the matrix still keep low. And this is that's all. And thank you for your listening.
All right, let's thank the speaker. Well, I think the speakers are actually around on the Zoom. So if you have any questions, feel free to raise your hand and ask them. Or if people on Zoom have any questions, feel free to just unmute yourself and ask. All right, yeah, so it seems like both people have mentioned that there are occasional cases where the IOU might seem to be a little weird, and we will look into that. We'll work with you and look into that.
Thank you.
All right, thank you. So our next, okay, so we are actually, okay. Yeah, we'll just go ahead and then is there last call for questions? Any questions for Yijie Wu? Okay, so with that, we'll just go towards our next session. Our next talk is going to be an invited talk by Dr. Manmohan Chandrakar, and we'll get him to from the CSC department, who is an associate professor from the CSC department from University of California at San Diego. And he works a lot on computer vision, virtual reality, and computer graphics. just click yes. All right. Okay. All right. Thank you, Fukshan. And all right, so it's a pleasure to talk about photorealism in indoor digital twins. And so this talk is going to be on a slightly different topic compared to the 3D reconstruction and floor plan reconstruction that we have seen. And once this thing works, we will, I know it's just my thing. Okay, so it's all right. So what I'm going to be talking about is photorealism for indoor architecture and construction applications. And in particular, I'm going to talk about photorealism that we can get with even mobile phone images. Can you show also your video? That will be okay. A little better. Can you? Here. Okay. Okay. All right, so I hope folks on Zoom can see me. All right, so we will talk about photorealism with a perspective on some applications. For example, it might arise in interior design, where you might take a mobile phone image of an indoor scene, and in this case, you want to replace the kitchen countertop that was granite in the input image on the top right with a different material, let's say wood. But you want to do this in a way that preserves all the highlights, shadows, distant interactions that lighting is creating with material and geometry here. Now, you could have other applications. For example, you might take an image of an indoor scene and you might want to insert furniture or other objects in the scene in a way that is photorealistic, as we are doing here. So this is a problem that clearly is challenging because there are lots and lots of types of image formation factors of variation that we need to care about. If we are inserting an object in the scene, then it will cast shadows on other objects in the scene. We have to account for the lighting, the shadows that other objects are casting on this object. We have to account for things like specular highlights, variations in lighting, variations in geometry all across the scene. So there's a problem that's incredibly hard because in indoor scenes, we have lots and lots of variations in layouts and geometry. We have objects of all type. We have light sources that can be windows or indoor illumination of this sort. And all of these things interact with each other in a complex way through interreflections, shadows, highlights, specularities, and so on. So what I'll also argue is that many applications require us to not just be able to reconstruct things, but also be able to reconstruct them in a way that's editable and relightable. So for example, if we are taking augmented reality applications where we want to insert an object in the scene, then we need to care about the interreflections that the reflections the inserted object is casting on other surfaces in the scene, the shadows it is casting. If we want to edit the material properties like paints in indoor scenes, then we need to care about how color bleeding effects happen across different walls. If we want to figure out where to put a window in an indoor scene, then we need to care about how light shafts from directional illumination from sunlight is going to appear in this indoor scene. So to be able to do such editing and relighting, my fundamental argument is that we need to essentially solve this problem of inverse rendering, where given images as input, we want to be able to estimate the entirety of the geometry in the scene, for example, expressed through depths and normals, material properties, for example, both diffuse and specular properties of the scene, and also very importantly, the light sources and the lighting that they're casting on the indoor scene. So, so to be able to get really photorealistic outputs, we essentially need to solve canonical problems in inverse rendering, where given single or sparse images of the input scene, we want to estimate unknown geometry, spatially varying material properties, spatially varying and discrete light sources with a high degree of photorealism. And we want to do this in completely unconstrained scenes with images that we have acquired with just mobile phone cameras. So inverse rendering by itself is a problem that's as old as computer vision. We have had lots and lots of approaches. In the early days of computer vision, we have had physics-based approaches to inverse rendering, where physical models are created, which tend to work well for the environments that they are designed in, but face limitations because the type of variations that we face in indoor scenes can be really vast. We have had very high quality results that we can get from measurement-based approaches. All the Hollywood movies that we see with CGI, essentially we create effects through light stages of this form, which can cost millions of dollars to create. Our argument is that we want to be able to leverage the power of machine learning while also incorporating insights from what we know about the physics and geometry of image formation to be able to get greater insights and at the same time, get a high amount of photorealism. Okay, so the approaches that we're going to talk about, they rest essentially on three pillars. The first thing is physically motivated networks. We work with deep neural networks where we have figured out ways in which we can inject the inductive bias of image formation through our knowledge of the physics and geometry of the scenes. We devise meaningful scene representations in the form of representations for geometry, material, and lighting that make the entire learning problem more tractable. And we work with large-scale synthetic data sets of shape, material, and lighting that are at a scale and at a degree of realism that allow good generalization to real world images. Okay, so so we can just quickly work through a few of the steps that we need if we want to solve this problem, and we'll focus on a couple of these. Now, fundamentally, besides geometry, the first thing that we need to care about is the material properties in the scene. Walls and carpets behave very differently in terms of properties, and we need to be able to estimate that, which we encode through what is called a bidirectional reflectance distribution function, which we can think of as composed of a few elements. One is the microgeometry of materials represented through surface normals, roughness, which essentially indicates the shininess or the glossiness of a material, and albedo, which captures diffuse reflection properties of a material. So we can solve these problems pretty well through some of our early works. And what I'm showing here is a comparison between a ground truth acquisition of a material and what we can render after having done our estimation. Now, the next thing from materials is to also estimate shapes and materials together. So every object that we see in a scene around us is some complex shape with spatially varying material on it. And we need to estimate both of these together. We could have some materials which are diffuse and glossy. We could have extreme materials such as transparent objects, as I'm showing on the right here. And using the sort of methods that we are going to talk about, we can handle both of these types of cases. But fundamentally, once we move to indoor scenes, then we need to start caring a lot about the lighting that we have in the scene, because essentially you would have lots and lots of interreflections. If we think of the majority of the illumination or the appearance in a scene, most of the light energy really comes from interactions between different parts of the scene. But to be able to create editable, relightable digital twins of indoor scenes, we need to go beyond just estimating the lighting to be able to estimate the actual light sources in the scene. What if our applications require us to figure out how we can how the scene appears when we turn a light source on or off? If I say turn off the lights here and open a window out there, then how would this room appear? And that requires us to estimate discrete light sources. And finally, to be able to do all of this, we need large-scale training data. And if we think about it, because we're talking about complex light transport effects here, real training data is going to be hard to come by. We are going to have to rely on synthetic training data, and we'll talk a little bit about how we can create such data sets. All right, so before we get there, let's talk briefly about being able to do high quality inverse rendering in indoor scenes with an eye towards applications that require us to edit these indoor scenes. So we are not going to talk too much about geometry and material estimation. Essentially, all of this is based on deep neural networks. We have encoder-decoder architectures that give us per pixel predictions for depths, surface normals, spatially varying diffuse albedo and roughness, which capture the material properties. But fundamentally, what we need in these type of methods is the ability to recombine all of the estimated geometry, material, and lighting properties, and thereby recreate the input image so that we can impose a reconstruction loss between the rendered image and the observed input image. Right. So this requires us to create lighting subnetworks that take predicted geometry material as input, predict the lighting, use the predicted lighting to perform rendering, recreate the input image, impose a loss, and as in all sorts of dense estimation problems, doing a cascaded refinement helps. So once we have the ability to render our input image back, we can compute errors and do cascading. All right, so the first thing that we need for something like this to work, because lighting is inherently extremely high dimensional, we need to have compact and effective physical representations for lighting. So think of it this way: the lighting that we really want to estimate is if we place a mirror ball at every point in the scene, that mirror ball will reflect the entire environment that is being observed at that particular spatial location. And that is the lighting or the environment map that we have at that particular location. Right. So one lighting representation that we can work with is essentially this per pixel environment map, where we imagine we have these mirror balls placed everywhere in the world. And that is something which can be really high dimensional. So what we are really seeing out here for every pixel, every location here is a full-blown environment map out there. Right. So now, while this is a very dense representation of lighting, it's also very expensive. So we would need to work with some sort of a parametric approximation to this. And for lighting and environment maps, we have very good basis representations that can capture a lot of high frequency variations. Now, spherical harmonics are a common choice that is used out here. One of the key observations that we had a few years ago was that some of the less popular representations like spherical Gaussians actually tend to capture more of the high frequency variations. So for example, with a similar number of parameters for spherical harmonics and spherical Gaussians, we can capture a lot more of the high frequency details of the lighting, as you see in the middle column. So if we are using this to insert virtual objects into the scene, then we are able to capture more of the specular highlights as compared to a spherical harmonics representation. So, so essentially then what our lighting estimation would, or lighting prediction would really do is take input images, take predicted geometry and material, and predict the spherical Gaussian parameters for per pixel environment maps. So that's what I'm showing out here. And finally, a key advantage of working with a lighting representation as this per pixel environment map is that the rendering process essentially becomes just a linear operation. So we can, because we have a per pixel representation of the lighting, to be able to determine what is the pixel intensity at a certain location, we can just have a linear operation that's multiplying out the BRDF or the material properties with the lighting that we have observed at that particular point. Right. So this rendering layer then gets very simple to implement. And this then allows us to start doing all sorts of interesting AR applications where we can do things like material editing, where we have replaced the material of the kitchen countertop out there from granite to wood out here while preserving highlights and other such interactions with lighting. Out here, we have replaced the material to the left of the hallway from paint to wood. And while we have done that, we can preserve things like spatially varying highlights that the lights are casting on the material. We can do things like object insertion, where given an input image of the scene, we can insert these virtual balls. They don't have to be balls, they can be bunnies, or they can be any shape that we really want to insert here. And the representations that we are learning do capture a lot of the high dynamic range effects that we want an effective lighting representation to capture. So essentially in a scene like this, we are able to represent both shadowed regions as well as sharp highlights that we have from directional illumination from the sunlight through the window. So to evaluate all of this, besides quantitative studies, one can also do user studies, because finally, for interior design or augmented reality applications, we want users to be comfortable with whatever we are doing here. So to be able to do this, essentially, we have data where we have measured the ground truth lighting at certain locations in the scene. And at these measured positions, we can insert a virtual bunny with respect to the ground truth lighting. We can insert a virtual bunny with respect to the predicted lighting. And we can ask a user to determine which of these looks more realistic, right? So a perfect lighting estimation, or like inverse rendering estimation, we are estimating all of geometry, material, and lighting. A perfect inverse rendering would have a 50% chance then. So a user would be perfectly confused between what we estimate and what is the real ground truth. So, so we have a few comparisons with methods out there. On the far right, methods which are statistical but not based on physical properties. Methods in the middle out there do not account for spatially varying lighting that prevails in indoor scenes. Out here is what we just talked about, and on the far left is a ground truth. So, so we reach about 38–39% here, which is significantly better than what previous works can do. Okay, so now to be able to do all of this, we don't really impose any spatial coherence between the per pixel environment maps that we are producing, but our estimates are good enough that we can create videos like this, where we are inserting the object at various spots in the scene, and we don't really have too many flickering artifacts and so on. In an upcoming work, we also have video-based versions of these, where we take video inputs and produce more consistent outputs. Okay, so now, of course, we can do better by, for example, improving the backbones that we are working with. So instead of CNN backbones, we can switch to transformer backbones. And the argument would be that such inverse rendering problems in indoor scenes are actually killer applications for things like transformer architectures, because these are the things that really require global attention. You have things like large ambiguities in material and lighting that you need to look at the whole image to reason about. You have distant interactions between different parts of the scene. A light source that you turn on in one part of the scene will illuminate a distant part and get reflected to another part out there. So, so having transformer-based architectures does help. For example, in AR applications, we can get better detail, such as the shadows that we are recovering here are more accurate. We also essentially get state-of-the-art results on all the tasks that are involved in inverse rendering. So, for example, on the IAW benchmark for intrinsic decomposition, that is albedo estimation, we get results which are significantly better than prior works and significantly better than our previous CNN-based backbones. Okay, now I did argue in the beginning that we need to talk about discrete light sources and not just lighting, because once we start talking about doing real applications, we need to account for how inserted objects are interacting with the lighting and so on. So to be able to do that, we take the next step to go beyond the geometry and material and lighting prediction to actually predict discrete light sources. And if we think about it, the light sources that arise in indoor scenes can be really varied. You can have things like lamps, you can have things like windows, very different properties. And these light sources can be visible or invisible. You might not observe a light source in the image, but you observe all its effects in the appearance of the image, right? So, so we need to estimate essentially lamps and windows, visible and invisible. So now a critical bit to be able to do this estimation beyond the learning backbones is to be able to recreate the input images back, because this then provides us the real inductive bias for how material and lighting, for example, should be disambiguated, because these are really, really ill-posed problems. So we need ways to be able to figure out what is physically realistic. And to be able to do that, we essentially have a physically motivated neural renderer that in network in a differentiable way is able to take this challenging problem of light, material, and shape, recombining to form the input image. So now, not only does this allow us to do better estimation, this is actually something that can allow us to do better editing also, because now, once we have such a physically motivated neural renderer, we can do editing through this neural renderer rather than having a physical renderer, which can be very expensive to run. We can have a single forward pass of our network, and that can then create all these editing effects like light source, inserting objects, inserting light sources, and so on. Right. So now one key observation here was that it really matters how we are representing lighting here, because the type of light sources that exist in our world around us, they tend to create very, very sharp or high frequency effects. So because light sources have distinct boundaries, they have distinct semantic properties, they need to be estimated quite well. So standard things that we do for, let's say, 3D object detection, where we have bounding boxes for objects, don't quite work well for light sources. We need to estimate the physical extent of light sources accurately. So, so we have methods where we model the geometry of light sources and we estimate them. Similarly, for windows, although the geometry of windows might be easy enough, it's a flat plane, but the illumination that the windows are casting on the scene can be complex. In particular, what we find is that it's not sufficient to work with a single environment map. Rather, we need to account for what is the contribution of the sky, what's the contribution of the ground, and what's the contribution of directional sources like the sun. Right. So, and for each of those, then we have 3 separate spherical Gaussian lobes. So now the important bit is now to be able to take all of these shape, material, and lighting representations and to be able to recombine them to form the input image. Now, in this case, remember what we are working with is an extreme case of even a single image as the input. And we are never going to have complete observations of the world, whereas images that we observe, they are created by interactions with even unseen parts of the world. So we need to decompose this problem into what is directly observable and what is indirect. The directly observable parts, which are comprised of direct illumination and direct shadowing, are things that physical rendering is really good at. So we are able to essentially have an in-network Monte Carlo ray tracer that can determine what is the contribution of direct shading for all the individual light sources in the scene. We also have a direct shadow renderer, again, a Monte Carlo ray tracer in this case for shadowing, but shadows are things that depend in really sharp ways on the geometry. So small, remember, we are working with estimated depths. Small errors in depths can lead to big discrete changes in whether shadowing happens or not. And for that, we then need to use a neural component to upgrade the physically rendered shadow maps to shadow maps which have less artifacts around boundaries. So having the direct shading and having the direct shadowing, we can just combine them, just do a dot product to get the direct shading. Now, this direct shading is only direct contributions from each of the light sources. This is not something that has accounted for global illumination. And fundamentally, for a problem like this, we cannot have a physical accounting for global illumination because we don't see the unseen parts of the scene, things which are behind our camera. And even the depth estimations that we are working with, they are incomplete depth estimations. They are depth estimations with holes. They are not actually reconstructing full 3D extents of objects that we are working with. So to be able to get these global illuminations, then we need to have a neural component. And neural networks are then good at essentially hallucinating or performing a more heuristic upgrade to a globally illuminated shading and the per pixel lighting maps that we have talked about. So So we then put all of this together. We have, going from the left to right, we have the input images. We estimate the geometry, geometry and material. That goes to our light source prediction networks. They predict the discrete light sources, visible and invisible lamps and windows. These go to the physical components of our renderer, where we are rendering the direct shading and shadowing. Goes to the neural components, where we upgrade with the global illumination. We put them all together to finally recreate the input image. And we can now impose a loss between the recreated image and the input one. So, so all of this then, besides the estimations that we do, can also enable us to do interesting editings. Remember, in this just one forward pass of the network, we have the ability to now to render the whole image. So we can now make a tweak to the input geometry to insert an object and see what its effect would be. We can insert a light source and see what its effect would be. We could turn off a light source and see what its effect could be. So, and we could do these together. We could insert an object and a light source together, and all of these distinct non-local interactions that we have can be accurately captured. So now the final bit that I want to talk about here is also how we get data for these things. And different from problems where of geometry estimation, or even problems of material estimation, when we are working with entire indoor scenes, fundamentally, we cannot have ground truth for all the complex interactions that we have in terms of shadows, interreflections, and all these things. So to be able to get high quality ground truth, we then work with synthetic data sets. And so our ambition here is essentially to have a democratized approach to this, where users can essentially take videos of their own indoor environments, and we provide all of the tools that are required to upgrade these to synthetic photorealistic digital twins. So, so everything that we see in this workshop with floor plan creation, layout estimation, geometry creation is something that we use to process our point clouds. We put in CAD models corresponding to furniture. We do a mapping of the closest material types and lighting to create essentially digital counterparts of the videos that that we are working with. So, so this is an example on the ScanNet data set, where on the right we have a video sequence from the ScanNet data set. On the left we have essentially what we are creating with as our digital twin. So this is something that can also allow us a lot of interesting things. For example, now that we have synthetic data, we can visualize the same scene under different material types. We can visualize the same scene under different lighting conditions and so on. So all of this code and data is publicly available at our, including things like the renderers and all the tools that we use are publicly available on our website. Now, what you would have noticed with the open rooms videos that I showed was that the appearances don't quite match although they are realistic, they don't match the input image. That's what we address in the photos, what we call the photo scene version of open rooms, where we are able to take input images of the type that you see here and create digital twins which have appearances that closely match. And essentially what gets us to work is we use all of the inverse rendering methods that I've talked about. We apply them on the input image. We combine it with a differentiable material prior. We push that through a differentiable renderer, render the image, and compare the difference between the rendered image and the input one, and iterate through this process to refine our material, lighting, and geometry such that we are able to material and lighting. In this case, we assume geometry is known. Refine the material and geometry so that we are able to mimic the input image as closely as possible. So, so in this case, now we are able to obtain reconstructions of indoor scenes that are closer in appearance to what we have observed. Now, still, it's not perfect, largely because we don't have CAD models for everything that we see in our input images. But once that geometry problem is solved, what I'd like us to notice is that material and lighting are handled really well out here. So, so this data set, I'll encourage all of you to try it out. It has lots of comprehensive ground truth for all sorts of indoor scenes. especially ground truth for things like material and lighting, which are usually not common in 3D data sets. Okay, so so that's it. I think I'll stop here. We have what we have seen is inverse rendering in complex scenes from single or few images. This can help us to solve lots of interesting problems in indoor scenes around applications in architecture and construction. We can do things like interior design and augmented reality pretty well. With this, there are lots of challenges that remain. How do we work with more dynamic scenes? How do we account for more complex light transport effects? And they are subjects of our ongoing work. So finally, I'd like to acknowledge all of my students who have worked on this and collaborators across industry and at UCSD. All right, thank you, everyone. Happy to take questions.
All right, so any questions for me? You can just come to the podium at the top of. Your microphone is still on, right?
Yes.
Yeah, then yeah, people also can hear. We are testing.
One quick question: the scene where you have the more than
this one?
Yeah. Can you explain a bit more about what is your recommendation there? Will it still be perfect for light roads and is that happening?
No, so the representation is actually the discrete light sources. So every light source that we are seeing out here, we estimate the geometric extent of it, and we estimate the spherical harmonic coefficients that correspond to that particular light source. So so the argument here is that essentially, if we want to do really well on these applications where we had that big ball that needs to interact with the light source, then we need to capture the geometry of the light source, we need to capture its semantics, we need to capture its directional properties. And for those, yeah.
My question is more about how do you
Yeah. So essentially the physical neural renderer that I talked about, that is the one that's generating these outputs. So
you're able to update whatever.
Yeah, exactly, right? So we can essentially what we have out here is a estimated geometry. We can just edit that geometry offline to say that, okay, now I put a big ball here, right? So, and now into the renderer, we can see that edited geometry instead of the geometry that we estimated, and just go through this rendering pipeline then. Yeah, so, and that's a key advantage. Essentially, we don't have to do physical rendering, but a single forward pass of the network gives us that much.
Any other questions? Or people can also ask questions from Zoom if you just unmute yourself and ask.
Does my audio need to be on for that?
He is in control of that. So not good.
Yeah.
Wondering usually that this is where we have the fire to make sure that the new design will practice for somewhere and more and more futuristic environment is the
Yeah.
Maybe potentially including innovations or some interior design.
Yeah. So not any interactions that that have been deep enough, and I would love to essentially do that at this workshop. So I think what we have here are essentially some motivations for what we can do out here. I'm sure if we talk to an interior designer, they would tell us different things. So yeah, so would love to have that feedback.
Things that come down.
Yeah, thanks. Oh,
Yeah, this back to you. I guess this is yours.
Okay, thanks.
I think, yeah, go ahead.
Okay. All right. Hi, Mani. I see you, Mani. Our next speaker is Professor Mani Golparwar-Fart from University of Illinois at Urbana-Champaign. He's a professor of civil engineering and computer science and technology entrepreneurship. And he's a faculty entrepreneurial fellow, excellence faculty fellow, and the director of the real-time and automated monitoring and control lab at the UIUC. Dr. Golparwar has several patents and is currently involved with Reconstruct Inc., an early stage technology company with $28 million in venture capital funding that was funded based on the outcomes of his ongoing research projects. With that, I'll turn the mic over to you, Mani.
Thank you, Yelda, for that kind introductions. Hi, everyone. Very glad to be here today.
Sorry, I muted my phone.
Can you hear me now?
Yes,
yeah,
we can hear
sorry,
you.
that was my fault.
No worries at all. I was just saying thank you, Yelda, for that kind introductions, and hi, everyone. So I have thoroughly enjoyed all the presentations today. We heard a lot about some of the applications of computer vision for design and operation in the built environment from Avide, Pimbo, of course, our competition winner, and Mohan's presentation on augmented reality. I'm going to give you a slightly different twist. I'm going to present some of the problems that we have in the construction phase of the built environment. And while I try to do that, I'll show you a number of applications of computer vision and how we looked into solving these problems, and a few cases where knowledge from design and construction was brought back into computer vision, and it was able to enhance some of the techniques that we have for reconstruction and recognition. Since majority of the audience have computer vision background, I thought maybe I should just touch on a few statistics for you and kind of excite you about the type of problems that we're trying to solve. So with that, I'm going to go ahead and speak about the state of the industry today. So over the past 10 to 14 years, the value put in place in construction have been increasing year by year. In fact, last year, this value exceeded $1.8 trillion. While there's a lot of money that goes into construction, a big portion of that goes into labor. What I mean by labor is the effort that we put into design, effort that we put into managing the project, and of course, our own construction labor. And unfortunately, the vast majority of the work that we need to do is associated with a lot of coordination and communication issues. And that's roughly around 35%. So if you do the math of 35% times that 40% number that I have times 1.8 trillion, that is roughly $250 billion. Now, I'm guessing some of you in the audience might be fans of American football. You might have seen the SoFi Stadium that hosted the games last year. That stadium finished roughly $5 billion. So if we address some of the issues that we have in coordination communication, we can add another 50 of these stadiums to a construction every single year. But what does that mean to you and I that are passing by construction job sites every day, or we are waiting for our next physical asset to be constructed? Unfortunately, this waste that we have with coordination communication means many of our projects are behind the schedule. Roughly 1 every 2 projects that we perform end up being behind the schedule. And when it comes to larger projects where coordination communication is more important, pretty much every one of these projects are suffering from cost overruns and delays. Now, over the past few years, I've had the opportunity of asking many owners, what is it most important to you during construction? And I'm sure many of you on the audience that are coming from architecture and engineering background would agree with me that we spend more time in planning and design, we can save a lot of that construction effort. But of course, we asked this question post-design. So design was already bought in, and hence project design wasn't as highly ranked by the owners. Now, you may look into the rest of the metrics here, and you may argue, why not safety? In construction, we rely on our contractors to offer a safe environment. Quality, we have designs and a specification that define what quality means. Budget, if owners are good at one thing, it's managing their money. But if there's one variable that impacts our ability of leveraging our physical asset to add more value for the owners, that happens to be the schedule of the project. And that is why owners have ranked that to be the most important metric during the construction phase. Now, why managing a schedule is so difficult? I want to take you back to some of the basics of what we do in the AEC world. Every project that we start, it starts with a plan. We go on and execute that plan. We get together in a timely fashion to see if we can find the delta between that reality and the plan, to see if we can reconcile the delta and improve the base of planning for the next cycle of work. So if you think about this cycle of planning, executing, monitoring, and adjusting that delta, there are 4 specific problems that are really interesting to solve. Number one, over the past 2 decades, the construction community, and especially from an academic perspective, we've significantly enhanced the way we plan projects. But the byproduct of some of these theories that we brought into construction is we've added the number of tasks that need to be coordinated and communicated on a job site. What you see on the left side is our normal practice, where we typically have hundreds of activities that needs to be done on the job site. What you see on the right side is one of our better practices. Now you see thousands of tasks that needs to be coordinated. Bringing these concepts into the practice have shown us that, while you're enhancing the effort, you highly rely on experts to guide the team through this process of who's doing what work in each location. Not only we have issues with respect to how you're planning the job, but when it comes to executing the plan, there's still a lot of room for improvement. So we've been surveying a lot of project teams and superintendents on why we're unable to execute our plans in short term, daily and weekly. There are all kinds of reasons. Sometimes work plans change. Sometimes we show up at the job site, somebody else has occupied the workplace. Sometimes we underestimate the effort that it takes. If we look into these efforts and reasons that are behind delays, you see that roughly 80% of them are preventable. The problem is that we do not have visibility to what these problems are in time to address the problem in the first place. The third problem that we have is how we are tracking progress on the job site. Now, this picture is one that I actually took myself from a modern electrical vehicle plant in Michigan. This is the state-of-the-art practice. You walk on a job site. Today, you ask contractors to stand up in front of a trailer wall and color code 2-dimensional drawings, like the floor plans we were discussing earlier, in terms of how much work has been done. Now, some of these projects, if you think about data centers that might be relevant to the audience here too, you're spending somewhere between $2 to $5 million a day. So you're waiting for an entire week to learn about where the problems are, and these problems are stacking up, and all you can do is simply react. And guess what? Progress that are being documented is being documented on the 2D drawing. Where do we need that feedback? We need that back into our plan, our schedule of sequence of the work, so we can go ahead and update the basis of that for the next cycle of work. And unfortunately, folks that are engaged in the process of planning are not the ones who are on the job site. So we're always missing that feedback loop or what really happened on the job site and how do we use that data to update the plan. But there's room for optimism. Over the past few years, there's been a significant growth of visual data. And data has been helping us with respect to finding ways that we can solve these problems without adding new work to our construction workflow. What type of data is relevant to us? One, growth in visual data. Over the past 2 decades, we've seen a surge of pictures and videos that are being captured on the job site. It's very common for us to walk around with our smartphones. So, some of the examples that Manmohan was referring to earlier today, to take pictures of the job site and document what happens. Not too far from me in Vancouver, there used to be a startup company called Multivista that was the basis of documenting pictures on the job site in a structured fashion. And that company has already been acquired by another technology provider. Time-lapse cameras, we have 360 videos, drones. Construction is the #1 market to drones. Abide also pointed out to some of the use cases of drones. And scanning, like the data set that we're using for the floor plan generation process, is an example of these types of data. So there's a lot of opportunity to tap into this data to capture what really happens on the job site. To improve the basis of the planning, you can also tap into 3D design that we spoke about earlier today in form of building information models, tying them against the timeline of the schedule so we can create an animation, computer graphics animation that shows you the sequence of the work in terms of what is that work that is expected to happen. So from one side, we have pictures that show you the reality. From another side, we have design tied against the schedule that shows you the expected work. If we bring these 2 sources of data together, we can create this sort of twinning strategy that from one picture, you can see what is there on the job site. And from that graphics that's being tied against the schedule, you can see what should have been there on the job site. And perhaps we can start looking to detecting changes so we can color code what is behind the schedule and what is on schedule with different colors, such as metaphor of traffic light colors. So going back to those 4 specific problems that I mentioned to you for planning, executing the job, and adjusting, you can actually augment that workflow with what I would call a computer vision project controls workflow. where now the basis of that graphics plus a schedule provides you with reliable plans. Twinning that design against pictures that perhaps will be transformed into models can provide you with that true digital twin that improves the way we coordinate and communicate the work. And if you start finding the delta between the two and forecast the future, perhaps we can come up with a proactive risk management strategy. Now, speaking about this from a picture perspective is pretty straightforward, but now let's transform into a computer vision problem. How am I going to be aligning every one of these photos that I have on the job site against this 3D design that is tied against the schedule? So we call that 4D BIM, fourth dimension being the element of time. Now, not only I have to solve that problem with one fixed viewpoint, but now I have every one of these pictures that I'm taking with my smartphone, with drone. I have them coming from the 360 cameras that we're mounting over hard hat. There are a few technical problems here. One, you may argue that some of the pictures may have GPS or IMU related data so we can identify it. But yes, unfortunately, in real practice, that is a luxury that we can't easily find. The second issue is that design is an abstraction of the reality. We cannot fully rely on design to be able to match that cat picture you see on the right side against the picture. The third piece has to do with time. You see, the problem that we are trying to solve here is monitoring construction. So we don't know exactly how many of these elements are on the site to be able to do the perfect matching between that reality against the design. So now we can actually start thinking about this more from a computer vision perspective. What if we transform every one of these images into a pinhole camera? And in a very standard model, we have many degrees of freedom that we have to worry about. Unfortunately, directly solving this problem wasn't as straightforward. Now, I happen to have a degree from University of British Columbia, not too far away from where the event is happening. And at the time, I had just learned about SIFT feature detection techniques and had been exposed to the work of David Loy with Matthew Brown that were looking to using some of the SIFT concepts for image-based 3D reconstruction. Fast forward, I had moved from UBC to University of Illinois, and Yasu Furukawa had just released his multi-view stereo technique. So I was really passionate about maybe there's a way I can tie these pictures together and generate the representation of the scene. But of course, there was a pipeline that I had to worry about. How do I automatically organize these pictures in 3D, a classic structure for motion problem? How do I identify that process, perhaps through a multi-view stereo? And how do I do some sort of shape fitting so I can generate a complete representation of the scene? But here's the outcome that I had. I thought, what if you organize these photos against one another and generate an as-built representation of the site? Then I'm going to go ahead and twin the reality that I have on the job site against the design. And now that I have this within the same site coordinate system, essentially every image that's been registered against my point cloud can be augmented with some standard computer graphics technique these days that I can show you what is expected to happen on the job site. So you see a color coding of a picture that shows you what are the work that our contractors are expected to perform. The design model that you see here contains quantity of the expected work. And if your picture in the background is measurable, then you have a basis of arguing that you can track actual work against expected work. And that's exactly what we did. We sort of thought, this can actually transform into a 3D representation. We bring the element of a schedule so we can color code areas, tasks, as to whether they're behind the schedule or on the schedule. And fast forward, bring a little bit more predictive analytics so we can understand the trend of the work that is happening on the job site and forecast the future. So next time we go into a coordination meeting, instead of worrying about the past, we look into our future. What are those problems that are problematic for us? And how do we collaboratively work together to solve these problems? So this is bringing that computer vision project controls into a real coordination meeting and kind of engaging the team with feedback as to how we can fix a problem. Now I'm going to go ahead and touch on a few specific problems that are really interesting from a computer vision perspective. The very simple problem is, how do I organize these photos in 3D? And how do I automatically register the BIM model so I can go ahead and augment them? This is a standard classic problem. For the audience that is sitting in the room today and listening via Zoom, fast forward, this is pretty standard. It's a pipeline of a structure from motion that follows dense reconstruction. A variation of it could be PMVS, TMVS that you also had worked on with mesh modeling. But what is unique here is that dominantly, the superintendents and project managers you have on the job site have a hard time dealing with point cloud data. So what you see here is that images are geo-registered against the point cloud. So you can go ahead and click on any specific point in the scene, find that image of interest, and instead of interacting directly with the point cloud, you will have this image-based rendering technique that allows you to measure and augment the scene. Now, we started working on these algorithms, and the next problem that we had to solve was, how do we organize this data over time? So the idea was that, over time that you keep taking pictures, maybe there's a way for us to perform feature detection matching against the previous point cloud. So over time, we can come up with an efficient number of, algorithms within our pipeline to sort of generate this 4-dimensional reality. And I'm just showing an example. There's nothing unique here, except that, from a novelty perspective, you are constraining your new reconstruction against what you had before, and you have to make sure it's efficient enough that, within the time you have, within the budget you have to run this on a cloud, you'd be able to support the computational power. So if you can achieve this 4D reality against the design, against the point cloud data, you can go ahead and align it against the design. Now, from a computer vision perspective, from a computer graphics perspective, you may argue that, this is a problem that can be solved automatically. You have 7 degrees of freedom that associated with uniform scaling issue, rotation, and translation. And all you need to do is to bring this into your design coordinate system. In early stages, we really didn't want to solve this automatically, because in construction, we have tolerances issues. And what that means is that perfect matching of the feature, that doesn't necessarily mean it's a very great engineering registration of the design against reality. So the user is guiding us by providing us with a number of correspondences between the reality and the design, and voila, we solve for this regression problem, and you'll be able to have this digitally twin created scene that shows you the plan against the reality. And fast forward, what that means is that you can even turn off the point cloud, because point cloud is really not necessary. It's a byproduct of this entire pipeline. That now you get these images that are all tied against that 3D model of the first place, and you'll be able to go ahead and overlay that on top. Now, when we started bringing some of these computer vision to the AEC application, we started realizing that testing at the scale matters. Before the solution was commercialized, we roughly tested around 120 plus job sites before even FAA came up with regulations around drones. And we learned a lot. We learned about some of the problems that are more related to computer graphics that I'm not going to explain today, but a few problems associated with our standard structure for motion. One, when you're dealing with these, type of scenes, there's no guarantee that your scene will be completed. And I know Yasu was specifically asking a question earlier around robotics, and I'll get into that. The second issue is a classic problem that we always have with, whether you're using a structure from motion, or even worse, when you're using Islam, a body of algorithms, that, you will have a problem of drift. And of course, our point clouds are up to scale. We still have to bring them into the site coordinate system so we can use that as a base of measurement. This was one of our first attempts on bringing the knowledge of AEC back into computer vision. Can we envision an image-based 3D reconstruction that will be assisted by the design, as opposed to the other way around? As opposed to using the design after the 3D reconstruction, why don't we use that knowledge prior to our 3D reconstruction and use that as a base of reconstruction? So here's the simple idea. This was the idea that, we're going to go ahead and take a few images. We call them anchor cameras. We have the 3D model. We can establish those correspondences manually or automatically, and we can solve for a very classic PNP algorithm that brings the design into this image that we call anchor camera. Once we have the anchor camera readily available to us, now we can go ahead and unlock registration of every other daily photo that we had. So how is this different from standard structure for motion? You're constraining your structure for motion against the design. So it's model constraint. And hence you have these anchor cameras that have been pre-registered. Everything else is being optimized in 3D and overlay with respect to that. So what does that look like? We start with these anchor cameras. We transfer the knowledge into the rest of the photos through a number of transformations. And yes, there are going to be moments that our registration may fail. You can provide as a feedback to the user so they can assist that input process or organize all these anchor cameras prior to it and achieve the registration. One of our first attempts of bringing that AEC knowledge into computer vision. So of course, we had to establish for the audience that this also works for some of our classic problems. Now, if you think about what we use for our multi-view stereo, the Middlebury data set, we also looked into whether we can use that CAD data set that is also provided with the Middlebury data set and minimize or measure our translation and rotation error, which are standard techniques that we use for this type of work. So what are the findings? First, that we learned that, leveraging that knowledge of AEC, specifically design, can potentially minimize a lot of the drift and issues that we have with preserving right angles. We're looking at the plan view and how we've been able to improve that. Second, we can also go ahead and improve the completeness of our 3D reconstruction because the likelihood of registering images for unordered collection of photos dramatically goes up. So hence the very first example of bringing some of that design knowledge back into computer vision. The third issue that we had was, how do we automatically track progress? And what I mean by that is the picture that I showed you earlier. It's a classic change detection problem. We had a CAD representation of a scene, we have an as-built representation, point cloud, and images, and all we want to do is we want to see if we can find the delta between the two. Now, instead of merely looking to this from a occupancy perspective, in earlier days, some of the work that I did with Silvio Savaresi and Penny Amora was focused on how do we take advantage of the occupancy and visibility of the scene and create a probabilistic view of objects in the scene, and perhaps cast this into a very simple deterministic approach of identifying what is there versus what should have been there. So we put this into testing, and it was a very simple process in early days. We learned a lot from it, that if we purely rely on geometry, we're gonna have a number of failures. One, examples I can show you. One, if you look into this example on the top, the system was automatically detecting concrete as formwork. And unfortunately, it was not able to recognize progress correctly. I'm showing you another example at the bottom. This is an example of a false negative where you had a severely occluded scene, and unfortunately the occupancy in the scene and assessment wasn't good enough to pick out a case like this. And of course, you can ask a very simple question. Is there a way for me to take advantage of semantics and some of the classic work that was done in computer vision for texture recognition? We have a lot of problems. It's not as straightforward as you would think. One, in construction, we've never formalized these techniques. These are steps that we have for how we do construction of various components. A very simple example of a concrete wall. We start with formwork, we go into reinforcement, placing concrete, finishing, waterproofing, insulation, cladding. There are all kinds of materials that needs to be detected. Now, at the time when we were looking to this, some of the classic work that was done by Luang and Malik from UC Berkeley was actually showing that texture recognition area was pretty mature. So we were pretty excited. We brought these techniques into construction, and unfortunately, we're facing with some of these real challenges. Some of these algorithms would fail. So we started, augmenting these techniques with a very simple bag of words model. We tapped into a one versus all classification technique, and we enhanced it by the knowledge of texture and color at the same time. And we brought into the problem of progress monitoring. And in early days, we were able to show that, these techniques that are working in computer vision with some adaptation can end up solving these real problems that we have in AEC. But here was our opportunity. Now that we learned that these computer vision techniques actually solve some of our problems, can we learn something from the knowledge of AEC and use that to improve the process of material recognition? So fast forward, this is the work that I did with one of my colleagues, Derek Hoem, one of the senior organizers of another workshop that is happening today, and Joe DeGaulle, a student that we were working on together. And the idea was that we understand what type of geometry we expect to see in a built environment. What if we infuse that knowledge in the process of our recognition? So we came up with a very simple feed-forward network plus a support vector machine classifier that for the first time we're showing that infusing in that geometry information into our classification problem can enhance the way we do material recognition and texture recognition. And of course, we've released that data set. So if some of you in the audience are interested in tapping into a 3D geometry data that is associated with materials, that data set is publicly available. So what are the takeaways? I showed you a number of solutions that we brought in from computer vision to solve the problem of construction monitoring. And I also showed just a few examples of how that knowledge from AEC domain can augment the way we look into these computer vision tasks, specifically to reconstruction by using design-assisted process for reconstruction and recognition. In recognition, tapping into the knowledge of geometry that we have from CAD, BIM, semantic information we have, and some of the interdependency information that I would have loved to see some of that being used by our competitors in the floor plan competition. Now, fast forward, as Yelda mentioned, we had the opportunity of commercializing this work, and then we learned that still there are many, many scientific problems that have remained unsolved. So I want to go back to the example that specifically Yasu was referring to early in the session. What about, using robotic platforms or some of the examples that Avide shared about using robots? Yes, there are a number of problems that we can look into. One, we have an issue with incomplete coverage of the scene. We have that problem of drift. In many cases, we have an expectation that we can achieve certain ground sampling distance or surface sampling distance, and we might be able to address that low visibility because guess what? Robots have actually made their way to the job site. But the question that we wanted to answer is, what are those methods and metrics that we have to use to guarantee if you create your flight plan, if you create your motion plan, you can make sure that you have enough data that can solve both your recognition problem and your reconstruction problem. I'm not going to get into the details of it here, but we looked into some of the classic metrics that Steve cites, introduced back in, I think, 96, for multi-view stereo, and we augment them to come up with metrics associated with the stability of reconstruction. And then we added a number of other metrics. How do we want to make sure that coverage, resolution, viewpoint, line of sight can all be optimized both for construction applications and bridge inspection? And these are some of the recent works that we've done on that front. So here's an example of a very, coming up with techniques that can, improve the way we feed data into our computer vision algorithms can solve the end use problems. The other area that's pretty exciting is progress tracking. But, fast forward, when you deal with many real projects, you would see that maturity of the design and schedule varies a lot across the industry. So, the very promising trend that I see these days is looking to progress tracking without using that BIM or without using that schedule. There are a number of challenges I want to point out. One, construction progress doesn't mean visual change. I want to show you an example. If you see the picture that I have on the right side of the screen, hopefully shows you that simple case of a drywall. When we come up with CAD representations, even that competition we saw with the floor plan, we don't necessarily represent all of these layers using visual data. There's some semantic data that sometimes we embed in the model, and sometimes that data doesn't exist. So we have to come up with creative ways on how we can take advantage of that and improve recognition. As I mentioned before, these states of work in progress are not formalized. Data. It is easy for us to make a case that, we can capture certain types of construction materials, but guess what? If you want to scale this to just building projects, we have a little bit over 600 classes of objects that we need to worry about. And BIM models help, but unfortunately, we have very limited amount of annotated data that is currently available. And as you saw some of the examples that Avide was presenting, without having human in the loop or using products, some of these real problems would remain unsolved. So you would not be able to easily attract the industry audience to be engaged in the process and make sure that you use that as an opportunity to capture better data and enhance the body of knowledge. But there are reasons for optimisms that I'm hoping that I can pitch this to some of you that have computer vision background in the audience. One, there's been a lot of trend associated with generating synthetic data as a base of improving recognition. And AEC knowledge provides you with that very unique opportunity. We have a lot of these models that we use as a base of design. These models are equally used during a construction phase and can provide you with that semantic geometry and dependency data that you would need to create the next generation of recognition models. Coming up with techniques that can, leverage human in the loop and product feedback can be extremely helpful. So a very recent example, I'm excited about Segment Anything that I think one of the competitors for the floor plan also generated, because now you can actually have users to provide a little bit of that input and improve. And I think Avide even pointed out to that in the context of asset detection. And what I also wanted to remind everyone is that, for us, it's pretty straightforward to take some of the techniques from computer vision, adapt them to, publish them really quickly, rather in the next 12, 18 months in an AEC domain. But it does take a little bit longer for us, but there's an opportunity to bring some of this AEC knowledge back into computer vision and help rethink the way we look into some of these classic problems of reconstruction and recognition. So at the University of Illinois, with our partners at Carnegie Mellon, we've started looking to this from a broader industry perspective, an effort funded by National Science Foundation to plan for an Institute of AI for the construction. We have a little bit over 10 academics, Pinbo, who's on the call. You may recognize some of the colleagues, Derek and David, who are attending the event today. We have a little bit over 310 participants, 85 companies that are tech providers, startups, investment community, and international partners. And I welcome those of you who are in the audience to join us in this effort as we look into solving these real problems and bring some of the core knowledge back into rethinking the way we look into these recognition and reconstruction problems. With that, I hope I've shown you a few cases of construction as opposed to operation and maintenance, and I'm open to any questions you may have for me.
All right, thanks a lot. Any questions from the audience, please? This was an amazing talk. Okay, so I guess I can ask one question. So I think you mentioned a lot of computer vision challenges that you have actually already solved. Can you also talk a bit about the remaining biggest unsolved computer vision challenges?
Yeah, that's a really excellent point. So you might have noticed that, I only picked one use case of construction, which is construction progress monitoring. And what that means is understanding how much work has been done on the job site. Even in the context of that, semantic segmentation still has a lot of room for improvement, particularly by tapping into the knowledge of geometry. So when I see, from the trend, I'm pretty excited about some of the work that's being presented, but it's hard to see folks looking to how do we leverage combination of geometry and semantic data to solve these problems. Part of it has to do with data. I'm guessing, computer vision community hasn't been provided with that right type of data. And I'm hoping that the built environment would be that, starting point that we can look into some of these segmentation techniques more from a combo of geometry and recognition. But the other problem I want to touch on is the process of going from point cloud to design. I think my colleague Fernanda Leche, who is in the audience today, she's going to speak about it later today, so I'm not going to steal her thunder. But that's another very exciting area that I'm hoping that folks in the computer vision community will be looking at.
Thank you very much. Any other questions? All right, thank you again for amazing talk. And yeah, with that, we are going to go to the lunch break, and then we will come back at 1:30. And then we'll start at 1:30 with our presentations for the 3D challenge. And then we have more invited talks and other exciting sessions in the afternoon as well. All right. All right, see you back in about 15 minutes.
Nice to meet Don't worry about it.
I don't know. I know there is lunch on the best, but I don't know what happened.
Grammarly Go is the only generative AI product that you need. It's easy to use in the
We help you find a domain that fits your business and protects.
To whom it may concern, I know I'm capable, even when I'm nervous about jumping in.
Do we have the third place presenter for the 3D challenge here?
Hi, can you hear us?
Yes, great.
Yes, we are here. We are available.
Good, good. Can you test sharing your screen, please?
We can. Just a second. We are testing.
Okay. Yes. Hi.
Test sharing the screen.
The sharing. Yeah. Yeah.
Yes.
Just a moment.
Yes.
Is it?
Yeah, the screen.
Yeah.
Well, we haven't seen it yet.
Yeah. Now.
Now, yes. Yeah.
Okay. Stretch and disperse.
Okay. Good. Then I stop sharing.
I was actually wondering, maybe you guys can start. That would be.
Oh, okay. Yeah, sure. We can start. Yeah.
Yeah, right. We will have then the second. So we'll have you guys start and then the second, and then the winners at the end. Will that work? With everyone?
Yeah. That's okay. We can do it.
Yeah.
Yeah. Okay.
Yes.
Should I share already the presentation or?
Yeah, you can
Okay.
to start sharing. We'll wait for maybe 1 minute.
Okay.
Yeah, and then 1 sec. Let me get this one off. And think we can get started. So, okay, so welcome back to the CV for AEC workshop at CVPR 2023. And so our afternoon session starts with the presentations for the winners of the 3D building reconstruction challenge. And we'll start with the third place team, which is from Human Tech. And then we'll go after that, we'll go with the second place team. And then finally the first place team. So we'll do it in this order. So yeah, and then I think they are already, Dr. Jason Rumbach is ready to present, I hope. And then we'll have you start whenever you're ready.
Okay, thank you very much. Thank you for the introduction, and hello everyone. My name is Jason Rumbach from DFKI, from the German Research Center for AI. And today I'm going to present our results on the Scan2BIM challenge for the 3D building model reconstruction from the project Human Tech. So the team that worked on this challenge consisted of Fabian Kaufmann from the University of Kaiserslautern, the Department of Civil Engineering, and Madi Chamsadin and Jason Rambach from the DFKI, the team Spatial Sensing and Machine Perception. So this is the pipeline of our method. Yeah, a general overview of the method. We start by doing a semantic segmentation, as we've seen from most of the methods. And we split the point clouds into the different elements based on the class we have. Then, depending on the element, for the walls, for example, we treat them differently. So we do a plane fitting and try to get 2 planes of the walls. While for the columns and doors, we try to get the bounding box from the point cloud itself. Yeah, then from the bounding boxes, we create the IFC models. So we start with the semantic segmentation. This is based on the Point Transformer version 2 network. We pre-trained it on the Stanford dataset, but added point cloud normals and a random sampling of color. The reason for that was that in some of the test data of the challenge, they were mixed, so there were some points with color and some without. And then we fine-tuned on the challenge training data set with a modified detection head, so to have the less classes, to only have wall, door, and column. We do a density-based noise filtering to remove this noise as much as possible around the main building. Then we proceed with an axis sorting and clustering. So we sort the walls based on the axis in two directions. And we use the dbScan algorithm to perform a clustering of the wall elements. For the wall detection, the idea is that we can detect two planes, so from both sides of the wall scan, and fit a bounding box around them. So here we use the histogram of the point density that's orthogonal to the alignment axis, and we get peaks of usually very good peaks of the wall locations. Then we can use these points to perform an SVD plane estimation within a RANSAC framework with points from each peak. So this is in essence a RANSAC, but typically we only need one iteration because we feed already points that belong to the correct plane. Then because there are cases like this here where walls are not well connected, of course, because of missing points and so on. So we developed some algorithms that check nearby walls to see if they can be merged or if they can be closed in case they are perpendicular to each other. So this gives us an updated bounding box model. For the doors, the way we handled them was by taking the points from the segmentation, creating clusters of only door point clouds, and then checking if these clusters fall within one of the detected walls. So if in case they do, we fit the bounding box around the door cluster. For the columns, it's similar. Again, we hope that we get a good clustering from the segmentation, and then we fit bounding boxes around it. This is an example of a resulting IFC file in one of the test data. Generally, an issue that we struggled with quite a lot was the outside walls. So in many cases, they are half scanned or missing completely. So it was a problem dealing with that in general. Future work and improvements. So there is, of course, a lot to be done, as indicated by the scores as well. So we need a better noise removal and removal of some false positive walls. We need an improved semantic segmentation. So actually, due to time constraints, we were not able to finish the training. So we had a kind of half-trained semantic segmentation model that we used. So we hope with improving that, we can get a large gain in the future. And perhaps be able to identify some more elements that we missed completely, like a column here. Then we could look into improving the merging algorithm. Because we have some cases where it performs a bit suboptimally. And finally, we want to look into the door closing. So this means that sometimes in the semantic segmentation, we had open doors, so we detected only the leaf of the door, and that could not be assigned to a wall. So this needs to be turned and aligned with the wall to create a bounding box. This we, again, we're not able to do yet. This work is a collaboration that happened within the EU Human Tech Research Project, which looks into human-centered technologies for a safer and greener construction industry. If you want to know more about the project, you can follow the link here. So thank you very much, and we'll be happy to hear your questions.
All right, any questions for this team, either in person or online? If you're online, you can just unmute yourself and speak. Yes, there's one question. Yeah, just come up a little bit, maybe to the podium and you can. Yes.
Okay. Hello. Thank you for the presentation. I actually missed part of it at the beginning, but just quick question. Have you guys encountered any?
I'm sorry, I cannot hear you at all.
Maybe
Can you come closer to?
Yeah, sorry.
Sorry, hello?
Yeah, it sounds better now.
Okay, great. I was just wondering if you encountered any interesting things or issues with just the scale of the data set. Did you guys have any specific engineering tricks to work around the scale issue? Like with how big the buildings are, basically.
Okay, so there were problems, for example, with using the segmentation network. So in that case, we had to process the point cloud by parts. So this was one problem. Other than that, after this step, there was no big problem with the pipeline, just some memory issues at some parts that yeah, we had to downsample a bit. Yeah, in some cases.
Okay, thank you. Any other questions? All right, thanks a lot for your presentation. Let's move to the second place team.
Yeah, thank you.
Yeah, thank you. You could stop sharing. And let's move to the second place team, which actually they did the best in terms of the endpoint prediction. So they, if I remember correctly, yeah. So the Tsinghua team, could you please unmute and start sharing, please? Do we have the Tsinghua CBIMS team here on Zoom?
Yes, and sorry, I have to quickly reopen Zoom to allow it to access screen sharing. Sorry.
No problem. Yeah, no problem. Yeah. Did you have to allow them to? Yeah. Okay.
Okay, let's see. Desktop one.
Right. Yeah. So see your screen.
Okay. Can you hear me clearly?
I can hear you very clearly. Yeah.
Okay. Hello, everyone. Good afternoon. I think here is nearly 5:00 a.m. It's UTC +8. We are a team from School of Software at Tsinghua University. Our team name CBeams means computable beam standard, as we deal with beam data for its whole life cycle, and we are counting reconstruction from collected point cloud as a part of the life cycle at two different aspects. One is for as built in use building. The reconstruction is for creating digital twin and serving for better maintenance. And the other is for newly built rough house. The reconstruction is useful for validating the construction status. And we hope to standardize the input points data and output BIM data in the future. So we have done this contest last year and did a talk about it as well. So I might fast forward some parts of our processes which are similar to last year. I will talk about the overview of that first, then briefly talk about the data processing and semantic segmentation part, then the wall extraction and optimization, column extraction and door extraction, finally conclusion and a bit discussion. First of all is our method overview. We have took part in both 3D and 2D lanes of this competition, and my colleague Peng Chen have already shared our approach in 2D earlier. There weren't much differences except that we decided to not keep columns and doors in the final 2D submission as they actually led to worse scoring status. So I will mainly be talking about what we did on columns and doors here. And here is the abstraction of our method. Our data processing pipeline wasn't much different from last year. From the raw point cloud, we downsampled them random 10% using Cloud Compare. Then we filtered out the outliers. The train set and validate set labeled with given JSON were used to train and validate point transformer. After that, we run down all the test sets and gain labeled point clouds. So our semantic segmentation pipeline was exactly the same as last year. So we figured that the point transformer is not really good at segmenting the thing into multiple labels, but it was pretty good at segmenting things into just the target and others. So what we do is we used four binary classifiers onto four target types: walls, columns, doors, and others. So moving on to wall extraction and optimization. So my colleague Peng Chen have talked about this part in detail in the 2D lane. So I will go through it real fast. We first find wall candidates by plan fitting on the whole scene and select wall candidates by semantic segmentation results. Then we did local optimizations like extend, merge, trim, and connect to generate the regulated wall layout. Next is the columns. According to the semantic segmentation results, we obtained the point cloud belonging to the columns. Then we use the dbScan method to segment the point cloud into instances of columns. dbScan is densely based non-parametric clustering method. Given a set of points in space, it can group the point cloud into several clusters based on their relative distances, marking outlier points that lie along in regions. Finally, oriented bounding boxes of the column are figured out based on the clusters as shown in the right figure. In order to create a clean column reconstruction, we actually sliced up the point cloud at around the middle point of the height for about 0.5 meters thick. This way, the segmented points are cleaner on the edges without much noise. Then the doors. So doors are a big deal in our process this year. So we know that doors are embedded in walls. So we took the bounding boxes of walls from our previous construction as reference planes. RGB images were then generated for both sides of the walls. And for models with relatively bad lighting, which contains poor RGB information, we calculated the distance of each point to the surfaces of the walls and generated gray images using the depth value. So as we can see, that is the 11 Mat Office f2 with RGB images, the 8 short Office f1 with only gray images. Then segment anything model was used to split the images into masks. Among those which satisfied basic thresholds to form a door would be reflected back to 3D space as a bounding box and be used to cut up the 3D semantic segmented point cloud. As we can see in the lower left figure, it's a wall cut off from the original point cloud and rotate a bit to and then we use the mask to cut off the door out of it. And within this small batch of points, the ratio of points labeled as door would be calculated. Then when it is higher than a given threshold, say about 30%, if 30% of the points are already labeled by semantic segmentation as door, then we identify this mask as a door. Then with most doors identified, several occurrences of possible door with height pair were collected and used to filter the rest masks with similar feature. This was to make compensation for door points possibly missing out by semantic segmentation. That's about it. And here are some visualization of final output. As you can see, we regulated most walls to fix up a mostly watertight building structure. We have identified most columns and doors at their right position with slightly wrong extents. And we are quite confident in our reconstruction results. And here are some conclusions. So first of all, the ransack we used are a modified version of efficient ransack, which considers more regional influences when ripping out confident candidates, which helps preventing the overly generation of candidate shape proxy in one location. While we have done lots of regulations onto the walls, I would say in most cases it was better when we regulated them by extending and merging the related ones. Yet we might have done it a bit too far in some other cases. And 2D insights in 3D problems may make a big difference, such as our utilization of segment anything model to extract doors from walls. At last, a bit discussion. Here is a simple table we made. So when coming to real project in this industry, the cost is always one of the top priorities. And as some cities starting to create their digital twin, we have received significant amount of field point cloud data. And to be honest, the quality, as in both accuracy and density, are getting worse and worse because of cost. So a standard terrestrial laser scanner can cost about $35,000 US. It yields point clouds with acceptable quality, like provided in this contest. They're around a few millimeters. They cost a bit more than a common SLAM device for device price only. But when coming to workforce, I'm not sure if I'm explaining this right. It costs more time and manpower to use TLS device to collect point clouds. And the added cost in the end, when trying to scan the entire city, the cost difference is huge. But when using SLAM devices, the points gets worse in accuracy when spending less and less time on the job in the field. The cloud gets thinner in density. The reconstruction on these are disasters. Well, on the other hand, we have research associates who are super interested in things like airport terminals and factories. They are mainly composed of steel structures which are shaped in like LICT, which require much higher quality in the collection of points. This thing may also be considered in future workshops. Well, that's all. Thank you for your time.
Right. Thanks a lot for the presentation. Any questions from both in person and online? As I have said, online can just unmute yourself and ask. Okay, so I would like to ask a question. So I think you mentioned that your doors were about, like semantic segmentation was about 30% right in terms of identifying the door. So we did expect this, right? Especially for open doors, it's pretty difficult for semantic segmentation actually to get them. So I didn't fully understand how you did the compensation for open doors. I think you mentioned it briefly, but maybe can you again elaborate a little bit of that on open doors especially?
Okay. Actually, we can focus on the right figure here. So the red points are the points labeled as door by point transformer, and the blue points are actually labeled as wall. So what we did is if we already identified a mask from segment anything, so I think I can draw something here. Pen. Okay. So when a when a mask is already identified as a door, so we can take its width and height as a candidate pair. So any other masks that can fit into this pair, we think it is highly likely another door.
Okay, that's very interesting. Thanks. Any other questions?
Yes, I had a question. Can you tell us a bit more about how you handled the outside walls? If you did something special there, in the cases where the points are very sparse or missing?
So I am not the one responsible for dealing with walls. So I might not be able to answer your question.
Okay, that's okay. Thank you. Thank you.
Any other questions? All right, thank you again. Great presentation. And if you can stop sharing, that'll be great.
Okay. Thank you.
You cannot. All right. So for the first place talk, I think they would like us to play a pre-recorded video. However, the speakers are actually present on the Zoom, so you can. I mean, if you have any questions, you can ask the speakers, and then they will answer the questions live. So let me try to play this video.
Good afternoon, ladies and gentlemen. I'm Frank Xue, and we are a team from the Hong Kong U iLab. And it's our third time to attend this CV for AEC workshop. And this round, we would like to introduce our new pipeline space mode for the 3D track. And here are 4 members contributing most for the 3D track. 4 sections today. First is a very quick introduction to the scan to beam. And actually in Hong Kong, beam is being mandated it was mandated for all public works and will be mandated for all private major projects by 2026. This is because the government have seen the benefit and the stakeholders have seen the benefits. And among all the top uses, 3D point scans are popular in two uses. One is as-built modeling, the other is existing condition modeling. 3D scans can deliver the accurate dimensions and as well as a real status of their assets. And for existing such many buildings also require a scan-to-beam service. Especially, for example, this iconic 100-story ICC tower, because it was built 2010 before the beam era, so it has no beam models born with the completion of the project. And from all perspectives, the general workflow of scan beam, either it was done by manually or automatically. There are 4 steps. First step is point level segmentation. Second step is the primitive level, most likely 2.5 dimension, not the real 3D dimension. The real 3D dimension details are most likely to be implemented in the third step and consumes a lot of the labor hours because we have so many details. We are happy to see the CV4EC concerns all the 3 steps here. And however, we still lack of the very detailed things like the door handles, hinges of the door leaves, right? Yeah, and lastly, then we can have the system level, building system, urban system level applications. So for all pipeline space mode, we try to respond to the 4 major challenges to automating LiDAR processing. This is not only for the scanner beam. These 4 challenges are vital in any LiDAR data processing. The first is the cluster and the environment. So we labeled a few things like the remote trees and the unwanted board and houses outside the target floor. And second is unbalanced building type. We have less car parks in our test data set. The third is the openings, like windows and doors. There's no physical points there, but in our opt model, we need to annotate that we have the movable parts, although they are not here according to the LiDAR, but we would say they were there according to the model. And the fourth is the occlusion. That means like our doors, some of our doors and some of our wall parts was blocked. The laser was blocked by other furnitures. And then we designed the 4 response, actually 3 response to these 4 challenges in our pipeline. The first response is we designed a space voxel and the space voxel based simple machine learning model. This is not deep model, it's simple models to have the unsupervised segmentation. Here we have the unsupervised segmentation with the clearance with 1 meter to have the core cluster of a room, and then we expand to the physical points of the room. The second is we can easily classify whether a room is an indoor area or is an outdoor environment we do not want. And the decision rule is surprisingly simple. Only 2 terms. First one is the surface area. Second is the density of the space voxels inside the room. And from this very simple rules, then we can quickly remove the trees and the glass reflections. When the outside is dark, then we can have many reflected points. There are virtually no physical object there, but from the glass reflection, we can remove all these scenes from our further processing. And combining all the aggregated room features, we can further determine whether a target floor is an office building or it's a parking. So here are some examples of the rooms. You can see that the environment have been almost perfectly removed from the next steps. And the second is, of course, the semantic segmentation, very important for every scan beam automation. And specifically, we tested more than one type of the deep learning. Here we test the KPConf, point contrast, and the point next. We also try to train a soft group and mass 3D, but I didn't finish the training before deadline. And from the observation, we find that no model is perfect. And we circle some defects here. So we try to combine and try to do the embedding meta learning from different levels. So by the deadline, we only achieved the first level, quantum level compensation. And the third response in this pipeline is the boundary adaptation. So this mechanism mainly aims to suppress the errors from openings and from occlusions. So overall, we have a 3-step adaptation. First is rotate all the points to the Manhattan-like world, and then have the coarse region growing, and then the boundary adaptation to stick all the proposed region growth to the physical points, to the most likely physical point. And by applying this adaptation, we can see some defects in the upper charts have been improved. Then we can have the walls perfectly snapped to the physical points. And from the test that every type of object, walls and doors and columns, can significantly contribute to the MLU. And for overall, then our space mode pipeline is like this. So we have 3 parts. In the segmentation part, we have a space voxel guided unsupervised clustering, and also some pre-classification to remove the noise. And then we have multiple deep learning models. Then it's possible to do the ensemble. And with multiple guidance, then we have multiple normal guided proposals for walls and columns, and then followed by the boundary adaptation, and then the proposed doors based on the walls, and then the boundary adaptation. So the multiple guidance here, as well as the adaptation, mimicked the very typical multi-star search strategy in the optimization. That means we can try to start from different points, so then we have a higher likelihood to reach the global optimum. And the results was encouraging. We can see that in our last year's results, for F1 values between the 2 centimeter level and 20 centimeter level, there is almost a half of gap there. That indicates our boundaries were inaccurate in last year's submission. And we tested the overall effects of the first mechanism. It will contribute to 3% of the MMU increase. And the third mechanism will contribute into around 10%. This is very huge. And the number 2 mechanism will contribute further to 3 to 7%, depending on cases. And as a result, so this year, our F1 values between the 20 centimeter level and 5 centimeter level, the gap has been reduced into a quarter. So that indicates boundaries were actually more accurate this year. And for the second mechanism, we test some single start policy. That means we only employ one deep learning results. And also we tested some step 1 ensemble. And some results was improved, like the first combination of KPConf and point next. And some results was reduced. And we also have this room level aggregated feature guided multi-stars. And the results was more encouraging. Now we can achieve like 0.39 if we based on the training data set, training cases, and it can be further increased to 0.43 based on the test response. And here are some results we realized. We can, of course, we can see some missing components because this year we do not improve the proposal method too much. and discussion here. So first, we feel privileged to have this journey, 3-year journey with the Scan to Beam 3D challenge. Over the first year, we only tried but not submitted any result. And last year we got second place, but we're happy to devise several concepts like the space voxels and like the head level, which indicates less blockage of the laser. And this year we have a heavy workload. Yijie is coordinating the 3D team as well as a lot of codings for the 2D part. And we trained 4 deep learning models, each one of us trained one. And we also tried to analyze the staircase and the space voxel classifiers. I'm also responsible for the 3D boundary optimization code and ensemble multi-start combination. And to summarize, we think that the Scan to Beam is vital to both new buildings and existing buildings, and automation here is limited. And likely it might be flawed, but we can respond with the knowledge and we can respond with the computational power. But in the future, we can improve the current space mode with primitive level ensemble. I believe that will be useful. And also we would like to complete the missing doors and column and walls. This year we do not really have time to complete that. And we also have some recommendations to the next year's CVPR. First option is perhaps you can consider the new 3D objects like windows and annotation of floors, beams, and lighting. Based on my observation, it's not too difficult. That would be interesting. And the second point is we may involve the movable objects, the reality parameter. For example, we have doors marks, but we do not have this door lift, the real location angle. And some window curtains are on and some window curtains were off. So with this movable objects, then we can escalate this Scan to Beam to, let's say, Scan to Digital Twin. And third option is, this will also be difficult to balance the building types, like increasing the car park cases. And we'd like to thank the funding support from the Hong Kong ITF and the GPU support from Hong Kong HPC 2021 and all our lab GPUs. We would like to announce some job vacancies closely to the Scan to Beam, 1 postdoc fellows and research assistant and a PhD post. Okay, if you are interested, please email me or Yijie. Okay, guys, enjoy your weekend, and I would like to join your workshop next time in person.
All right, that's a very, very good talk. Thanks a lot. And I guess let me stop sharing. So I think we do have the authors here. So any questions to the authors? Also maybe from online as well. Okay, so I'd like to ask one question. So you had 4 models and so on, but then you also tried like some of these models that you tried didn't actually seem to help, right? So did you actually find it useful to ensemble all 4 models rather than a subset of them?
Thank you, Professor Lee, for the question. And I'm sorry, 2 reasons. First, I'm here now in Fujian province for another conference about the digital heritage. And the second reason is now it's almost 5 a.m. So I was afraid of that I could fall asleep. So I record a video to you. Yeah, you're right. So yeah, actually I tried to do the ensemble of all the deep learning model results. And for the step 1, that means we merge the prediction of the same class together, and found that the result was bad. It was not good. But by merging 2, combination of the 2, that will be a lot of combinations, but that will increase. But if you merge every model, at least at this combination level, it did not help. But I think for the second step, that means we will have a point level meta learning. Perhaps the result will be better. So we will see. And for the primitive level, I'm pretty confident that for the primitive level, higher level meta learning, that will sure increase, I'm not quite sure how much, but it should increase the accuracy.
All right, thanks. Any other questions, the audience? And also from online, feel free to just unmute and ask your question. All right, and we also definitely welcome the suggestions. So maybe I will also contact you after the workshop, and we can talk more about this. All right. Thanks a lot. Okay, so we are right at 2:15, and we are going to go through our next session. So I'm not sure. Oh, really? So yeah, we are right at 2:15, and then we are ready to go through our next part, which is community engagement. And I think we have already Dr. Mike Olson from Oregon State University online there. He is going to lead us through this community engagement session, which we really hope to have like an open discussion from all the audience in person and online. And then he will let us know what will be done. So yeah, Mike, so the floor is yours, I think.
Sounds good. Thank you, everybody, and for attending the session, and thank you, Fuxian, for leading us through it. So this next portion is going to be geared at kind of building the community and giving us a chance to interact and cross-pollinate across different disciplines. I think there's been more and more of a trend at conferences to try to bring back in more of the community discussions and get people to be more active in conferences. I think a lot of times we attend conferences, we sit back passively, and we absorb a lot of great information, but we really don't get a chance to talk with one another and kind of really get deeper into the discussions and share insights, because we have a great presentation, there's Q&A afterward, and then we move on to the next thing, right? And switch topics. And sometimes during the break, you get a chance to talk, sometimes you don't. And so the goal of this next period is to kind of shake things up and talk. We're going to have kind of two different parts to this session. So the first part, we're going to focus on the first topic, which is related to considering of building information modeling and some of the factors that are associated when you're trying to use CVPR algorithms to basically generate those BIM models from different data sources. And so a big issue we have is accuracy can have a lot of different meanings to different people, and depending on the domain and application and how it's defined. And even if you use the same metric to denote accuracy, there's differences in how people communicate those and how they're interpreted. And so when we think of accuracy or model quality in general, there's a lot of different things. So kind of throw up some of the different ways that model quality could be defined. One is geometric accuracy. So that is how well does it match the actual physical dimensions, the size of the object, the position, the rotations, tilt, bowing, any sort of other factors in the data set. A lot of times in models, we simplify those things because we want to keep the model simple and we don't want a lot of extra data in it. Sometimes that's important, sometimes that isn't. We also have what we call local accuracy, how well we can measure between 2 points in the data set that are really, relatively close together, versus absolute, how well does it match with other data sets that are in the same coordinate systems? And those are another accuracy factor to consider. We've got modeling accuracy. Did we classify as it the right type of object? Did we fit the right shape to the object, or did we oversimplify it? Did we confuse a cube with a sphere or other types of things like that? Completeness, how many objects did we capture? How many did we miss? What were the false positives associated with it? How realistic is the model? We may have a model that is geometrically accurate, but doesn't really look that good to the end user. Some applications that's important. How reliable are the attributes or the textures and so on? And then the level of detail is kind of the next factor. We may have a model that we consider relatively accurate, but it's at a very low level of detail, but accurate within that kind of realm, compared to something that's a higher level of detail where we're going to have more artifacts and other issues, but overall is more accurate. So how do we balance that detail with the accuracy? And then lastly, simplicity. does the model adequately balance being as simple as possible, but encoding as much information of what we need? So are we making it too cumbersome with too many nodes when we could really simplify it with simpler shapes? And this is just a sampling of all the different factors to kind of consider. It goes on. And, this, as we've kind of launched this competition, these are some of the discussions we've had internally as a group of which factors do we consider in terms of the contest? How do we judge whether one model's better than another, one approach is better than another at generating these different models? And it gets very complicated very quick. We listed a couple metrics here to kind of think about as you discuss in your groups. And so the first one is intersected in union. We've got precision, accuracy, recall, the F1 scores, Matthews correlation coefficient, and there's all sorts of other different metrics that we see in the literature for people to define things. And so kind of what we wanted to do is give you guys a chance to break out into groups, and so have a chance as a group to talk about these. And what I'd suggest is, as a group, rather than try to cover all of these, start with one, pick one that you want to kind of start with, and then kind of work your way through that. And then if you have some extra time, work through the other. So we'll give each group 15 minutes, trying to kind of break up into groups of about 5 people. We'll have some breakout rooms on Zoom as well that you can join and participate in for those of you that are on the Zoom portion. And talk it through as a group. Try to give everybody at the group a chance to start talking for about a minute or two before you kind of jump into your group discussion. And in 15 minutes, we'll come back here and to the main and have kind of each group report back on kind of what they learned. And then once we kind of finish this discussion, we'll jump into kind of the next topic area. So any questions on that on the chat or in the room? Find one of the conference organizers, they'll kind of help you with it. But we'll go ahead and start breaking out into the rooms. I will see, I don't know if I have the possibility online to create the breakout rooms, but Iro, do you have I think you're the full host, so I think you have the ability to turn those breakout rooms on. So if you turn those on, that'd be great.
You will do it on from our side, yes.
Or it's Mosen's got the button to do it. It only lets the official host do it. So Mosen, if you could turn on the breakout rooms, that'd be great.
Mike, can you zoom in your document a bit? We cannot quite see it from here. Yeah, is that better? Is that better or furthermore? Furthermore, can you just zoom it all the way so that it fills up the whole screen, please?
Yeah, I got it there about as good as I can. It will kind of cut some of it off, but hopefully enough that people can kind of use that.
Yeah, this is fine.
Okay.
Yeah, this is fine.
And Mosen, were you able to get those breakout rooms started? I haven't seen the invite. If not, if you want to make me the host temporarily, I can turn those on. Otherwise, if the breakout rooms aren't working, then we'll just go ahead and talk amongst ourselves here as a group of 16 or so, whoever's online.
Mike, can you hear me?
Yeah.
So the breakout rooms are not possible because it's just a normal Zoom meeting. However, since there are not that many participants online, you can be one big breakout room.
Yeah.
All right, let's do it.
Kind of mute you from our side. We'll keep you very low maybe, or like completely off, and you text us over Zoom chat when you're ready to come back in, okay?
All right, sounds good. Thank you.
Thank you.
Yeah, we're kind of at the mercy of the CVPR for the Zoom here. So those of you that are online, who wants to share their thoughts first about their favorite metrics? Mani, you got your hand up, so we'll start with you.
Mike, great seeing you. Yeah, I mean, I always start with the use case. You know, the intent of generating an as-built representation of the scene is driven by use cases, and we have use cases for design, we have use cases for construction, and obviously we have use cases for operation and maintenance. Now, one way that we've sort of classified maturity of the design as a function of the use cases, the concept of LOD, level of development, right? Where we sort of, you know, define a number of metrics that help determine how mature the design is for every engineering discipline. It would be great if you can kind of, you know, have some form of a metric around what type of LOD, you know, we're targeting per model discipline as it applies to the use case. I don't know exactly how we can capture it, but that would be really helpful. For example, if you think about, you know, some of the earlier examples that Avida was sharing, you know, energy assessment. For energy assessment, the sort of granularity you need for design is far less than some of the use cases of, you know, using the model for renovation, right? So what level of granularity are we expecting? And even in the context of that, the other question that's really important is what really defines an object? If you're trying to create a BIM model, I mean, you just heard teams presenting the concept of generating BIM from point cloud data. And door, interestingly, was only presented as one piece, right? But I mean, there's so many assets that go into that door too, including the door. How do you want to, what defines an object? And, you know, there are a few answers to that. One is, for example, we say, you know what, our intent is to generate objects at, let's say, ASTM uniformat level 2, which is a, you know, obviously standard classification that we have, some way of documenting our expectation on geometry. Now, a little bit more detail level, there are sort of 3 pieces. How good is the geometry? How good is our recognition of what this object is? And, you know, maybe you can call it semantic, you can call it appearance. The other piece is how well interdependencies have been modeled. Those 3 key pieces are all really important for, you know, a range of BIM use cases. For example, a wall is supported by a floor. A pipe is embedded in, you know, an opening. Things of that nature, right? All that needs to be really documented for BIM to be a full BIM. If the intent is to generate the scan to CAD, not a problem. I think we can stick with, you know, the metrics and topics that we have in here. But if you really want to go into that semantic CAD representation that we call BIM, it's helpful for us to kind of figure out if you can add some of those metrics. I'll stop there.
Yeah, thank you. You just remind me, I left topology off the list there in the kind of last part there, but there's lots of key factors, and I agree with you on the level of detail aspects and the use cases, really kind of driving what level we target for those. Awesome, thank you, Mani. Who would like to go next?
Hello, sorry, fine still.
All right, yeah, Pingbo, we'll have you chat
sorry,
next.
I can go ahead. Yeah. So what Mani has been saying, it's makes perfect sense. Level of detail might be related to something different than level of development, because when we are talking about engineering information, we are talking about not just how small an object is. We also talk about how mature is the information, and for design, we have those level of development concept in BIM, but for 3D reconstruction, I don't know to what level of confidence we can put into those information we can use for, like, for example, renovation design or mechanical system operation, facility management. So level of development could be different than level of detail. That's just my personal opinion. Yeah.
Awesome, thank you, Pingbo. Great insights there. Frank, you had your hand up.
Yeah, and just following Mani and Pingbo, I think apart from the level of detail and level of development, we also have a term called the level of information needed. So with the abbreviation of the LION, okay, LOIN. So that will be very close to the use case concept. For certain tasks and applications, they need the information might be at a very COAS scale. Right? For example, let's talk about the digital twin of agriculture. Actually, they do not need to model every single crop, right? So what they need is like a 10 hectare, and what's is their average temperature and water supply and expected date to do the harvest, right? So the level of information needed can also be added somewhere around the level of detail.
Yeah, awesome. Thank you. Great examples there. All right, who would like to go next? Don't be shy. There's no right or wrong answer here. As you can see, there's a lot of different directions that it can be defined. And I think especially kind of when we talk as a research community, this is one of the things that we struggle with in papers is how to compare one approach versus another. You know, as has been talked about, we've got differences in use cases, which is going to dictate which factors make more of a difference, but then also which metrics do we use as a judgment of the quality of the algorithm that we develop, and then how is that comparable across these different papers based off different use cases? So maybe a couple of those questions somebody may want to take a stab at answering for us. Don't be shy.
Here, I'm thinking a lot here. One of the challenges that we have is oftentimes when we capture a built environment, the environment has already been subject to the use phase for some time, and as such, it does start, demonstrating defects. The big question is, how do you roll that defect detection and characterization into this? Because oftentimes that can actually play a role in granularity of the segmentation.
Yeah.
What was really interesting is, when teams were presenting the result on the challenges, all of them were sort of looking to this from a planar fitting approach, meaning especially for the walls. Now, I'm thinking about this from an architectural perspective. Oftentimes you go after double curved surfaces by design, because they do accommodate for both planar and non-planar surfaces. And from a BIM community perspective, we came up with NURBS representation in industry foundation classes just to accommodate for these imperfections that happen in reality. And we do want these imperfections to be modeled. Yeah. I'm not trying to make this judgment more complicated. I'm just throwing out one extra factor that is helpful to consider in this whole thing, because for different use cases, again, you may have to worry about those details, you may not.
Yeah, no, I appreciate those thoughts there. And I think that's the other challenge that we have is, we may develop a BIM for one particular application, but people may want to use it for something else, right? And so now we start adding that complexity of it, of how do we judge whether it's useful in this other application, and get kind of more value out of the time that's spent in putting that model together and really kind of communicating those aspects. And there's been progress through like the USIBD, trying to remember what their abbreviation stands for. Basically the US Institution of Building Documentation, if I remember correctly. Hopefully I got that right.
That's correct.
All right, awesome. I got one thing right today. So I think there's definitely progress that's kind of been made in the practical sector, but I think like in the research community, this is still something that we haven't quite got together.
One, it's maybe a more question. I haven't had a chance to look into this, ground truths that we are offering for these data sets for the competition. What taxonomy has been used to define these classes? Is that based on any standard? Did we look into using maybe uniformat, maybe? Because I have a feeling that the labels that we have for the ground truths are probably more driven by the typical classes of objects that we have in computer vision, as opposed to any of these use cases. Maybe that would be helpful to kind of define, what an object is based on one of these standards, like, ASTM uniformat.
Mhm. Yeah, that's a great point there as well. And so the data sets used in the contest were basically developed, and we got to kind of keep it anonymous, but it was an agency, and they basically have kind of their listing of what things need to be called and how they're coded. It was basically originally provided as CAD data, and then our research group kind of went through and did some of the 3D modeling associated with that. And so they've got some kind of standard specifications with it, but things aren't perfect, right? It was professionals that were charged with basically creating these models and putting them together. And you know, as much as they try to be consistent, there's always things that come up that don't quite fit in there, and you know, they got to get the work done, so to speak. But they're overall pretty good. But I think it kind of gives you an idea of what, here's the state of, you know, what is kind of currently manually being done.
Yeah,
Other thoughts?
I just put the link in the chat just in case if someone wants to look into that AST classification.
Oh, awesome. Thank you. Anybody else want to share their thoughts on that part? Yeah, Pingbo.
I found out that when we talk about using the model in different situations, is there anything like a flexibility for the model reconstructed from point cloud or from any imaging sensor data? I just not sure. Is there anything like we can say there is a foundational group of classes and that there is another layer to say different combination of those classes or different extension of those classes will be useful, but they all trace back to a foundational group. It's pretty much like IFC, but I'm not sure. Are we able to evaluating those model quality by their flexibility? Because it takes a lot of time for people to label those and to build it. Then it would be beneficial to make sure that when we build it, it could be useful and reusable for multiple disciplines. Then the key thing I think we could start from is a design construction, because it's an interface, has a designer, school has their intention. They need to use the model to run their simulation, to do a lot of things, and to use the information in a very, very different way than those people who are trying to build it. Then could we start with one interface and to define what is the flexibility of the model reconstructed and to make it useful for both designer and the construction engineer? That's just my very, very rough thoughts.
Yeah, that's that's a great question, and I think there's a lot of opportunities there. I mean, you look at kind of how things are done in the industry. Sometimes you have that, you know, engineer's model that gets created, and the construction company creates one when they build one, and then somebody comes in later and builds one for maintenance purposes, and they're all kind of done with different intents. Money. Oh, sorry, Bing.
I mean, I guess, you know, over the past few minutes, we've been mostly speaking about this in the context of use cases, but maybe switching gears and thinking about this a little bit more at a computer vision level. I'm looking at these metrics and I'm wondering, you know, whether we can bring back that concept of completeness. I see precision, accuracy, recall, F1, you know, score. And I'm going back to, you know, these two standard metrics that we created for multi-view stereo reconstruction, Steve cites, and one of them was actually on this notion of completeness, meaning off of this CAD model, how much of that scene has been, you know, fully reconstructed. Now that metric, you know, conventionally has been defined for reconstruction, so it makes sense. But here, you know, how much of that element has been transformed into, how much of that, whatever we recognize off the point cloud has been transformed into CAD. Thinking about this in the context of two things, you know, given that intrinsically we have some incompleteness in the capture, how good is our model fitting, right? The other piece is, all right, maybe we had the data, but, you know, our reconstructed object doesn't look as complete as it should have been. For example, it's connected, it's extended enough, things like that. And you know, that metric is something that, you know, had been scientifically defined, what, like back in 2006. So it's been around for some time. Maybe that's another one that could be added to this list. And I just linked the paper.
Oh, sorry, Money, I cut you off there. What was the last part you said? Sorry.
Link to the papers here in the chat.
Okay. Awesome. Yeah, no, I think there's the challenges. The sensors aren't going to capture everything. Us as humans are going to miss things, and even the AI algorithms are going to do it. And we want to have that kind of completeness aspect, because that's going to make a big difference in what's done and the decisions made from the model. Frank, we'll go to you, and in just a few minutes we'll be going back to the main room.
Okay, just follow Manny and Pingbo's idea. So as we practiced in doing all these modeling, automatic program processing the LiDAR, we see LiDAR scans are, no matter how fine the data sources, there are always occlusion, there are always clutters. And I think for AEC domain knowledge, what we can contribute back to computer vision is whether can we embed it or domain knowledge back to this automation program, so that the computer vision, they can like treat this flawed LiDAR data, but generates this fine, complete, some terms like the waterproof model with every component has been completed. Even it is blocked, a large part of the wall was blocked by a shelf, by a cabinet, but still all work can help the computer vision community to restore that perfectly back. I think that is kind of also a point to note here.
Yeah, and I think that's great comment there. And as you're kind of talking, I think one of the things that's another big challenge we have is a lot of things are now be done with multiple sensors. You know, it's a combination of your mobile, terrestrial, iPhone platforms, you know, computer vision, photogrammetric type methods as well, kind of being mixed together, and then hand information, right, that we're putting in associated with all these different models. And so you know, that's kind of another factor in training AI to work with these different data sets and different sources of data to kind of produce a complete model. All right, so it sounds like the group in there is having some really in-depth discussions. I was going to try to bring us back in there, but sounds like they want an extra 8 minutes to talk about it instead of jumping onto the other topic. So I think we'll keep this conversation going. I think we're on a good roll here. But maybe we can talk more now about kind of the specific metrics to get into, and you know, how to quantify. And this you know, kind of our selfish motivation in asking this question is when we have these submissions that come in for the contest, you know, we've got to decide how to choose which ones are the top ones and other ones, and there's different metrics and things that get computed with it, and we kind of have to decide how to combine those together to make a decision. And so I guess kind of open it up to what people think are the best accuracy metrics to report. You know, maybe what's a minimum that should be reported, and what are some of the best ways to quantify these aspects, and which ones, you know, would you like to see in the contest, or which ones would you like to see in research papers as examples of the success of a method? So anyone want to pick their favorite way to quantify accuracy? You know, you're thinking of what the reviewer is going to say about your method. So which ones which ones do you like to show and go about computing it? Frank, all right.
Yeah, maybe I start this football. To me, the precision, recall, and accuracy is kind of let's say biased matrix, and MLU and macro F1 score would be much better. Still, the micro F1 score is also somewhat biased to me. Okay, so I vote for the MLU and the macro F1.
Yeah.
So after all, because or BIM whole model is just based on the family and the instance, so all object oriented, then it will be naturally fine to use the macro F1. But since we also have the volumes and some components mainly emphasize on the surface area, so it's also fine to use the MLU. Yeah.
Awesome, thank you. Yeah, and I think, as you mentioned, there's ways that these metrics themselves can be biased, and then I think there's a bias in how they're executed. You know, when we talk about point cloud semantic segmentation. We can often quantify based off of the number of points, but then that starts biasing some of the bigger classes, and, and some of the smaller classes just get kind of washed out in these overall numbers. So there's a lot of things that can be done that maybe don't necessarily show the overall quality. Other thoughts? I mean, would you say it's pretty common for people to report kind of the completeness in papers that you see? You know, what kind of maybe factors do they tend to focus on in terms of these metrics? Or do we just go qualitative because it gets hard?
Yeah, actually, if I may, I would like to vote for some invisible objects to be considered in the next rounds or in the later rounds. For example, the joints and the room space. Okay, all invisible. But if possible, we can try to annotate and to ask this automation scan to beam, try to guess what are the type of joints and where are the surface area. Okay.
Oh, makes it tough. I'll have to give that one some thought. That's a great idea, though. All right. Anybody else want to share their thoughts there? Okay, well, this isn't your only chance to kind of share that input. You know, the goal, and two, if anyone's interested in being involved in this more, involved in the contest. You know, obviously we want to get more and more people to submit, which we've seen a lot of growth over the year. But two, behind the scenes, there's lots of opportunities with it. If you have data sets that you want to contribute to it and other things, that's very helpful to it. Or if you want to kind of take a deeper role in those kind of things. Okay, so one thing we will need is in about 2 minutes, we're going to come back to the main room. So we do need somebody who wants to volunteer to be our spokesperson and kind of share some of the key insights that came up in this part of the session with those that are attending in person. And kind of summarize our comments. So who would like to volunteer for that? Who would like that prestigious honor of being the spokesperson for the online people at the third CVPR AEC workshop?
Mike.
Yeah. I think, Pingbo, you're unmuting to volunteer yourself.
No, I'm a volunteer, Mike.
I don't think anybody wants to hear more from me about it. I'd say it's ideal if it's not me, but if it has to be me, it will be me. But going once, going twice, no one. All right, so okay, so we'll join it in just a second. So I think probably kind of a lot of things in the conversation focused around the use cases and using those to define a lot of the aspects of the level of detail versus the level of development that the BIM model was created for. We talked a lot about you know, different factors and issues in the data sensors that are working to collect the data and how those get kind of communicated through. So we covered a lot of ground. So trying to think other key things that you want to make sure I emphasize in there.
We mentioned something about the flexibility and the reusability of the model. Is that right?
Yes.
Across different things.
Yeah. Yeah. So they kind of talk about multiple use cases and then the models being used for other use cases. We talked about biases and the metrics, and Frank shared some great thoughts there on the MIU and F1 scores. All right. So it looks like they're ready for us to join back now. So I will tell them we are ready. We'll see if they go first. So thank you all for your excellent contributions to the insights and ideas. And I think hopefully this spurs some ideas as you work forward on proposals and working groups on the different committees that you work on. Really hopefully kind of getting things defined, and the taxonomy was kind of another factor that kind of came up with this, and getting those things clear and getting the shapes clear that match, not just going planar surfaces.
Thank you, Mike.
Yep, thank you. All right. Kind of wait till they unmute themselves. I've sent them the message, we're ready. They sent me the message that they're ready. So hopefully we join back here in just a second. I see most of them walking around. So, and there's Fusion. All right, so that means we're coming back.
Great. Yeah. Okay. So I think we are back here, and then maybe it's time to connect the online and offline sites. I think online has been very active, and here we are also talking a lot. So maybe we can get readouts. So maybe we can get it from the online side first. Is that all right?
I was going to vote the other way, but we'll go ahead and go this.
Sorry, I'm still muted. 1 sec.
Oh, yeah.
I have the speaker off. Yes, I have the speaker off. So sorry, can you say that again? Because we didn't hear.
Yeah. Thanks, Fusion. So we'll go ahead and we'll share first then, it sounds like. So unfortunately, our group felt the assignment of having someone other than me be the spokesperson. So you all have to listen to me ramble for a few minutes, but we had a really great conversation, and a lot of people participating, sharing their insights and ideas and thoughts. So definitely appreciate the discussion that took place. And so one of the things that we kind of started with in our discussion is really centered around the use cases. That's really going to dictate what sort of metrics and what sort of things are important in terms of the models. And so, models are developed to support a lot of different applications, a lot of different purposes. Everybody's got their own kind of insights into what gets put forward with it. And that's one of the things that makes a big challenge for the flexibility of the model. So Pingbo from our group kind of shared some thoughts towards that models need to be flexible to support multiple use cases. And so that's one thing that kind of getting these metrics together is important, is it helps people know whether a model is suitable for their application, what level of detail or what level of development got put into the model. How much effort was put into it, what sort of features did they extract and put forward in the model. Monty also shared some thoughts on basically kind of looking at different types of taxonomy, shared a few papers that we can post to the website, or post links to the website, that kind of go into defining some of this taxonomy to really start sharing, what are some of the IFC classes and how well they're being achieved, but trying to kind of get that common language to help in the process there. So those were some of the good resources there. We then had a discussion on the metrics themselves and talked about them, and so Frank shared some thoughts that he had there on some of the metrics that he likes to go with in his research, as well as what's kind of shared with the community. So talk about precision, accuracy, recall, and F1 score, kind of our typical go-tos, as well as IOU. But that each one of these have different types of biases associated with them, depending on how objects are counted. And so going to things like the macro micro IOU or macro micro F1 score are some ways that you can kind of help improve the results with that, but we're still kind of stuck with some of those issues in kind of how things end up getting reported and how they get kind of quantified in the research that comes forward. So anyone in my group tried to cover kind of the broad range of conversation there, but any other thoughts you wanted to kind of share with the broader group that I missed in the kind of key points of the conversation? Okay, well, let's hear from those that are in person in Vancouver, live from Vancouver. Let's hear your thoughts.
Okay. I wasn't sure if I got enough of everything. So I guess we didn't get to a lot of answers from the in-person side. I mean, we were starting with basically the complexity of any construction project is a lot of different parts, and then it is very difficult to quantify or really even to figure out any specific part, because for every different specific project, they may want very different level of details on different components. Like some people may want the wallpaper to even be modeled, and then some people would not care about it. And then about, for example, we've been hearing suggestions about the door angle, right? So that would be something some people may be interested, and then in other cases may not. We did come up with a few more concrete things in the sense that maybe the cost of construction could be an overall overarching goal that we seek to get to, because that in the end, the users would be really happy if our metrics would be more directly linked to the cost of construction. But then we kind of struggled a little bit on how to actually decompose it into different components. Yeah, we definitely talk about materials and for example, even looking behind the wall to see what's the wall like, whether it's a solid concrete wall or it's like a dry wall. So maybe we can even think about that regard. Maybe I mean, this is my own creation, but maybe we can also look at some different kind of sensors from other than plain cloud, right? Such as something that actually goes into the wall. We did talk a bit about topological things, like in Revit BIM models, there is a lot of constraints. Those constraints really make sure that, for example, rooms are closed, the walls are attached to each other, and things like that, which is not necessarily true for the current scan to BIM, especially for the 3D part. We haven't really got to the topological part of things. And then we also talk a little bit about trying to use ChatGPT or language models to guide, right? Because of the complexity of the definitions. So we talk a little bit about how maybe we can actually use language models to put that, to put that together, like into maybe going away from our current practice of trying to find a few common categories and evaluate on those, but maybe actually just try to read language and directly satisfy people's needs, like think in the ChatGPT era, not in the computer vision era, maybe. Yeah, so that's all the things I captured, which may not be everything. And yeah, feel free to add on to what I missed.
Anyone? Oh, go ahead, Fusion. Anyone want to share any thoughts?
So what is the conclusion?
Any conclusion, or we should chat among us. I think maybe offline and online should now share comments with each other.
Yeah, I think that's a great question. I mean, I don't feel like we came to any sort of consensus in our conclusion in our group, but I don't think you ever really can in this short of a time period, right? I think this is something that, yeah, one kind of comment we made towards the end is that this is something we need to kind of bring forward to the working groups that we're working in and really use those to kind of establish this consensus and get that going. So, you know, that's one key thing in getting the models adopted is people need to know that they can trust them, right? So I think your group said just ask ChatGPT, is the model good? And ChatGPT will make the assessments for us and we're good to go, right? So maybe that's what we need to do.
Oh, I think it's rather ChatGPT can read the user's requirements. And then somehow some model can just do it. Of course, that sounds like a pipe dream, but who knows? Yeah.
Yeah. Well, that was going to be our next, discussion topic is involving ChatGPT a little bit, but I think there's a huge opportunity in ChatGPT reading the specifications that come out of all the different agencies that want you to do modeling and really digging into what they want and what they're looking for, and what kind of their taxonomy and how they want things labeled and everything else, and helping us wade through those things, because that's something I think we struggle with a lot in the ASE community is we have these massive design documents we got to go through that don't make a lot of sense and are really confusing. And I think ChatGPT is prime for doing those kind of things that nobody wants to do.
Although it is, if I can say one of the deficiency, it's not necessarily completely faithful to the document, especially if you actually have tabular data that you actually want this particular thing to be that in that particular place. I'm sure the current LM language models are prone to place column A into grid B and things like that. Yeah, so I don't know whether we have something there anyway.
Yep. Yeah, there's definitely still got to check it, but hopefully it can take some of that grunt work away from us. Well, great. Sounds like both entities had a lot of great discussion, and we have reached 3 o'clock, Fusion. So I think we probably should table the next discussion topic. We were going to have an interactive topic with ChatGPT for the next activity, but we'll save that for the next challenge workshop next year, just to kind of get us back on the schedule.
Yeah, we can talk about it more in the panel, because we will have another panel discussion after all the talks have been ended. So maybe we can save the rest of the ChatGPT discussions to the panel. And then with that, so with that, I would like to welcome our next speaker, Dr. Despoina. I'm sorry, I'm going to butcher her name if I try. Thank you. Yeah, Iro, you need to introduce her. Yeah, that's the. All right. So, what do you have? I do also have it back. Okay. I will move mine away. Yes. Folks. Oh, one second. I will from my end. Okay. So it will be better if you also put on your video, if that makes sense.
Oh yes, of course.
Like,
I'm sorry, I forgot about this.
I'm sorry. Hybrid is just me. Yeah.
I think you are doing a much better job than us, actually.
Yeah, okay. So a more proper introduction. Dr. Despoina Pascalidou, sorry, is a postdoc at Stanford University, working with Dr. Leo Gibas at the Geometric Computation Group. And she did her PhD at the Max Planck Institute for Intelligent Systems in Tübingen and the Computer Vision Lab in Zurich, and working with Dr. Andreas Geiger and Luc Van Gu. And her research is around the editable and interpretable representations of 3D objects and scenes. Okay, and with that, let's welcome her to start the talk.
Hi, thanks so much for the invitation. This is a great workshop. So you can call me Despi. Feel free to come and talk to me laterwards if you have any questions. So today I'm going to talk about a topic that I feel is actually quite close to the previous discussion that we had, and this is very exciting for me. So should I keep it? No. So yeah, like let me the main focus of the talk would be I'll try to discuss some methods that we have developed throughout the year. that can be used to generate and manipulate 3D objects and scenes. The world that we live in is highly complex. And of course, as we discussed before, it's very diverse. We can have different levels of detail, depending on which place of the world you are in. It might be more sunny or more dark. So for example, this image is taken from Athens in Greece, where I originally come from. And as you can see, this is a scene that has a lot of content. And if we were to somehow try to recreate the scene using AI generative techniques, as you can imagine, this might be very, very challenging, because it's very hard to create all these small details that actually make the 3D scenes and our 3D world alive. So let's for 1 second forget about the outdoor scene, outdoor world that is much more complex, and let's look at an indoor environment. So you look at this and you might be thinking, yes, this can be more easily recreated, or we might easily develop a model that can synthesize something that looks like that. And I guess the first thought that comes to mind is, okay, what makes a living room a living room? So we will all agree that in order for us to have a living room needs to consist of some chairs, a table, a sofa. However, if we take a closer look, you can see that this is not what makes this living room so beautiful, right? I mean, okay, yes, it has some fancy chairs. The design of the individual pieces is very interesting, but there are also these other core pieces in the background that bring this whole space in life. So for example, we have like these decor pieces on the walls, and all of this is like a relatively simple living room, I would say. If we want to try to do something, if we want to develop models that can capture and can generate diverse living rooms, we need to have a model that would be able to generate something that looks like this. And without a doubt, I don't know about your living rooms, but my living room definitely doesn't look like this. However, I think this is the beauty of what we're trying to do here. We're trying to build models that can generate fundamentally diverse environments. And this is something that is very hard. And of course, now I'm only talking about indoor spaces, and I've shown you some nice pictures of living rooms and of this very beautiful kitchen. And if we go to places like kitchen, where we can have like a diversity in terms of also the objects that can be found there, you understand that generating this type of environments can be very, very tricky. And so far, we've only seen static scenes. What happens if we bring humans into the play? Being able to capture these type of scenes and recreate them becomes way more challenging the more humans we are and the more alive we actually are. So, for example, here we have some people partying for the 4th of July. And if we were to recreate these environments with these humans in this environment in a realistic way, this is something that is very challenging. And I think regardless of what people are saying on Twitter, etc., we are very, very far away from here. So I think we still have our jobs for a couple more years to come. So anyways, I want to take a step back and try to discuss first what are some desired properties of generative models. So I think this goes a bit, this is related to the previous discussion. So I think that generative models need to be able to produce diverse and meaningful generations, meaning that we don't want, for example, to have a room where two chairs will be facing the opposite side of another. I mean, when we talk to others, we normally want to either be next to them or to at least be able to look at them. In addition to that, we want to be able to edit the scenes that we generate. So we want somehow the generative models to exert intuitive control on what has already been generated, so that we can easily manipulate the generated instances. If you ask me, because as I said before, I come from a computer vision background, I think what is extremely valuable is to be able also to allow generations with versatile input, meaning that we want to be able to generate an environment conditioned on a text description, on an image, on a sketch, on a point cloud, on a bunch of primitives. And this is something that I feel many people are still not considering very much. And I feel this is a very, very important aspect that could potentially fundamentally revolutionize generative models for 3D environments. In addition to that, I think something that is also related to the previous discussion is that for the type of data that we are considering here, it's very important to think what is the type of supervision that we really need. In all these works that have been focused on generation mostly of indoor spaces, you see that some people have created scene graphs. Others have created models where they define relationships between objects such as adjacency, support relationships. As you can imagine, this type of supervision is very, very hard to acquire. And in addition to that, which is okay, I mean, we can pay someone to do it. But for me, the main issue is that this is not really meaningful. And it's not really meaningful because this type of supervision was produced in very controlled environments, and by no means it cannot generalize in the complex real 3D world. Another aspect that I feel is very, very important for generative models is to be able to generate scenes fast. We don't want to have to wait one day to generate a single room, or we want this whole process to be very efficient. Maybe if you have time afterwards, I would love to also know your thoughts, but when I was trying to think, okay, what are the desired properties, was like a very small list that I could come up with. Okay, so without a doubt, I think generative models are awesome, and we have seen how significantly they have revolutionized various aspects of image synthesis. If 2D generative models are great, I think 3D generative models are even better. Why is this? 3D generative models can be very useful for a variety of applications, such as, for example, applications where we want to recreate and generate realistic 3D scenes, such as, for example, this teenage bedroom scene that is generated programmatically from this startup called Promethean AI. I think this is fantastic. So this particular scene is not generated with AI, but it is generated with a different type of architecture, but still it is artificially generated, and I think this is pretty awesome. The last few years, as I mentioned before, I have been talking to a lot of civil engineers and architects, and this make me start thinking of other potential applications of generative models. So what I think would be very, very interesting is to be able to use this kind of concepts in mixed realities application. So for example, we want to be able to take, to have a scene, and we want to hallucinate what can be positioned at a specific location in the 3D scene. And if we can do these type of things for these complicated structures such as buildings or bridges, etc., I think that would be pretty amazing. Of course, some of the things that are already happening right now is using these sort of 3D generative models in mixed reality applications that are focused for indoor design. So I know for a fact that some of my friends in Greece, for example, that were decorating their house, they went to an interior designer and they were able to wear a VR headset and see how their room would look like with specific furniture pieces. And personally, I think that this is pretty awesome. Okay, so the first work that I'm going to briefly talk about is a relatively old paper that we published 2 years ago. And the focus of this work is synthesizing 3D scenes using versatile user input. As I said before, I consider conditional scene generation is a very important task, and we want to be able to generate plausible furniture arrangements conditioned on an empty floor, as you can see here. We are also interested in being able to complete a scene that contains already some objects in a meaningful way. So for example, we wouldn't like our model to place a cupboard on top of this cabinet, right? And some other things that I feel might be more interesting for practical applications is to be able to, for example, do object suggestions, such as say, hey, what is the best furniture object that I could put here? So what is the motivation for this work? Our main motivation is that scene synthesis methods, at least a couple of years back, were typically imposing unnatural constraints on the scene generation process. So they were assuming that if you wanted to generate a scene, it was important to place the objects with a specific ordering, meaning that you first need to position in the room the most dominant objects, the bigger objects, such as beds, cupboards, etc. data, and then position the smaller object. However, this is unnatural and imposes some constraints that hinder various interactive capabilities of the model. So what we decided to do in this project, we decided to pose the scene synthesis as an unordered set generation task. The input to the model is a scene that consists of a collection of objects and its floor plan. And each object is parameterized using a collection of 4 random variables that describe the category, size, orientation, and location. And we predicted the object attributes in an autoregressive manner, meaning that we first predict what is the type of the object that we want to place in the scene, and then we predict its location, subsequently its size and its orientation, and then its size. And if you think about it, this makes a lot of sense because you want to know what is the type of the object that you want to place in the room before deciding how big this object is going to be. So what we did in this project is we trained this such that it maximizes the likelihood of generating a scene with any possible ordering. And to do that, we define a permutation function that pretty much tries to compute the set of all possible permutations of all objects in the scene. And if we were to optimize this likelihood, this might be a bit problematic. So instead of doing that, what we want to be able to generate a scene with any possible ordering. This means that it doesn't matter with which order do you see the furniture pieces, or the algorithm can complete any type of partial rooms. And why this is important? This is a very important property because it allows us to perform various applications that were not possible before, such as, for example, I give you a living room with a single chair, and the algorithm is possible to complete the entire room reliably. Okay, so let me walk you through the whole pipeline. So the architecture that we propose is a very simple transformer encoder architecture that takes as input, as I said before, the floor layout, passes it through a layout encoder that estimates some features that describe the floor layout, and the input objects parameters are passed through a structure encoder that pumps them to a per object, a context embedding that is then subsequently fed into a transformer encoder that predicts the features for the next object to be added in the scene. So this whole model is an autoregressive model, meaning that we predict the objects autoregressively. And based on this feature representation Q hat, this is decoded and we generate the next feature to be added in the scene. This object is appended to the objects that we already have in the scene, and this process is continued until the end token is predicted. So how well does this model work? Actually, it works pretty nice. So here you can see some generations of the model. The only supervision that we have is labeled 3D labeled bounding boxes, and here you can see random samples of living rooms, bedrooms, and dining rooms, and I think there are also some libraries. However, what I found the most interesting experiment of this work is this one here. So what you see here is I drew on Inkscape these scene layouts, these floor layouts. These of course do not exist on the training set, and you can actually see that the generations pay attention to the room boundaries. I think my favorite by heart is this one, where you see that the bed is somehow aligned with the wall of this weird floor layout. Another cool interactive application that we demonstrate here is object suggestion. So the user can indicate a specific position in the scene, and the model automatically suggests something that makes sense. So these positions here are indicated with red boxes. So for example, for the case where the position is not meaningful, the model says, don't put anything here, such as for this example there. And another relatively easy and fun application that we considered in this paper is we create messy rooms that are not properly structured, and we task the model with fixing them. So we, for example, take this bed, put it in a wrong position without telling the model what is the problematic object, and then our model identifies the problematic object and repositions it at the right location. Okay, so very briefly, this is a very nice alternative formulation for scene synthesis by posing the scene synthesis task as an unordered set prediction problem. This model has fewer parameters, is simpler, and runs up to 8 times faster. And although I think this is a very important step towards automating scene synthesis, indoor scene synthesis, it has some limitations. So for example, the model only predicts bounding box parameters. So we need to replace these bounding boxes with the actual 3D objects, which means that we have to rely on a retrieval. And in addition to that, it would be very nice, I think, if we could learn a generative model that does not have so strong supervision. Okay, so the next question that comes in mind is, this is a very interesting formulation. Can we somehow extend it to 3D objects? And the answer is yes, we actually can. So what we do in a similar manner, each object for this task is defined using a collection of n semantically meaningful parts, as well as a bounding box that defines how big or small this object is going to be. And similar to before, for every part, we use 4 values describing its label. What is this part? Is it like the leg of the chair? Is the base of the chair? Is the back of the chair? As well as its size, a rotation, and then translation vector. A rotation is a 6D representation because we've seen that it is more robust, but we have also experimented with quaternions. It works also kind of okay. In a similar manner, also here we predict the attributes autoregressively, meaning that we first predict the per part class, followed by the per part translation, followed by the per part rotation, etc. And as we did before, again here, we maximize the log likelihood of all possible permutations for any part arrangement, because as I mentioned before, this allows us, this does not impose any constraints on the generation ordering. And I think this is very, very important for a bunch of interactive applications. So what if we only take this model, let me walk you through the same pipeline that we discussed before, just for completeness. So again, the input is the bounding box defining how big is the object, as well as the per part arrangement, and we feed all of them in a per part encoder that simply estimates some features that describe how big its part is and where it is located within the object. And then similar as before, we have a query token, and we use a transformer encoder to predict the features of the next part to be added in the object. This is an autoregressive model. So using these features, we have a part decoder that decodes these features and gives us the next part of the object to be added in the part sequence that we have already generated. As you can imagine, although this is very interesting, in the end, we will end up having some bounding boxes. And of course, this is not very nice. So what we do here, in addition to that, to make things a bit more fancy, we introduce a blending network. What is this blending network? It takes an input, the part sequences, feed them through a part encoder that again estimates some features, and then what we do here is something relatively simple. We define a transformer decoder that implements a very standard occupancy network that takes query points and converts them to occupancy probabilities. So what this model does, transforms part sequences to implicit shapes. So let me show you some results to understand a bit how the model works. So here we compare with 2 baselines. We compare with IMNet, which is an implicit based generative model, and PQNet, which is an SDF part-based generative model. And you see that results seem to be very promising. You can see the generations just as they're predicted from the model, as well as after the blending network for chairs and tables. And of course, because our model is trained for completion, we can also do various completion tasks. For example, starting from this very vague chair that looks like this, we can complete it in a meaningful way and get consistently plausible completions. The same also applies to tables. Okay, this is all very good, great, but what's the main problem with this work? It requires a ton of supervision, which is hardly ever available. So this model requires supervision in terms of part annotations, as well as supervision in terms of 3D data. So the next question to ask is, okay, can we maybe do something similar just using significantly fewer data? And ideally, what we would like to do is we want to be able to train this model using only posed images. And the answer is Kind of, yes. So let me walk you through of existing generative model for 3D object synthesis. So here I have categorized them into big families. So one is these part-based generative models. Part-based generative models take into account the decomposition of an object into 3D semantically meaningful parts. And as a result, this enables them intuitive control, part-level control over the object, meaning that the user can select this part indicated with blue and deform it in a way. Say, for example, make it bigger, make it smaller, etc. There are two works that actually have done this. One was published in CVPR 2020. The other one is this very, very cool work from Amir Hertz, the spaghetti paper that was published on SIGGRAPH. So although both of these works enable part-level control, they require 3D supervision. And in addition to that, as you can see, they can only produce textureless objects. And this can be relatively limited. Another line of research that is in a similar direction are NERF-based generative models. So throughout, in particular, in the last few CVPR, ICCV, CCV conferences, we have seen a lot of 3D-aware generative models that actually can generate high-quality 3D meshes and require only 2D supervision during training. However, they do not enable part-level control. So it's very, very hard to say, okay, you know what? I want to select the tire of the car and make it bigger or make it smaller. Or for example, I want to select this window and change its color and make it, I don't know, red. I don't know why you would want to do it, but yeah, this is not very intuitive. You kind of, what I say is not 100% correct because implicitly you can do it through the race. However, semantic control is not really available in neither in the second category of methods. Okay, so in case it was not very clear until now, I think that parts are very important because they allow us to do local changes on the shape and appearance of different regions of the object. So for example, we might want to be able to select a part and apply a rigid or a non-rigid transformation, or we might want to be able to change the appearance of a specific part of the object. In addition to that, we might be able we might want to add or remove a specific part of the object. More interestingly, we might want to be able to combine parts between different objects. And the key idea that we have for this project is that we want objects regions to be edited through parts. So what we do in this paper that is going to be presented here at CVPR, and the poster session is on Tuesday, if you want to come by, what we do is we represent each object using parts where each part is parameterized as a nerf. Every part is equipped with an affine transformation that defines its local coordinate system. And this is very important so that we can define local transformations on its part. And in addition to that, we also associate every part, every nerf, with a scale vector, indicating what is its spatial extent, meaning what's the area of influence that each part can have. Finally, because we want to be able to independently change the shape from appearance information, we also associate every nerf with a shape and the texture code that independently allows us to control the shape and the appearance of each part. So the architecture that we adapt is a bit unconventional because we do not predict densities, but instead do occupancy prediction. So each part is parameterized using two networks, a color network that predicts the color, as well as an occupancy network that predicts the occupancy value of each object. And in order, the main problem that we have when we have nerfs with all implicit shape representations is that pretty much there is no constraint. Implicit representations are so powerful that they can represent arbitrarily complex geometries. However, for the case of editing tasks, we don't really want this. What we want instead is every part to only capture continuous regions of the object. To this end, we multiply each part with an occupancy function of an axis-aligned 3D ellipsoid, and as a result, we restrict its area of influence. I want you to note here that we multiply the points, X denotes the points, before we pass them to the occupancy function of the axis-aligned ellipsoid, we transform them to the per part local coordinate system, which is denoted as TM. Now, as I mentioned before, we don't predict densities, we predict occupancy values, and this is the very standard per part rendering equation. Another thing that we do is that we introduce a hard assignment between arrays and parts, and this is actually a very essential property of our model because it allows us to change one region of the part while not changing the others. How we do this? So the way that we do it is the association is defined based on the first array that intersects with its part. And because every array is only determined by a single nerf, we can then perform the rendering equation of the entire object as the composition of the per part rendering equation, which makes everything so much simpler. During training, the input to our model is a collection of pose 2D images of a specific class. So we only train for airplanes, chairs, or cars. And in addition to that, we also have object masks, meaning we know which pixels correspond to pixels of the object and which correspond to background. And our architecture is our generative model is an autodecoder architecture. So starting from the per object shape and texture code, we pass them through a decomposition network that decomposes them into per part shape and texture code. One thing that I want to mention here is that we don't have any part level annotation. So the parts are emerged naturally through this training process. And what we do next is conditioned on this per part code. We predict the local coordinate system of each part. And for the set of rays from every view, we transform these points into the per part local coordinate system. We fit them to the nerf. We do the per part rendering, and then this process needs to be repeated for all nerves, and in the end, the final rendering is simply the composition of the per part renderings. Our optimization objective is a bit too complex for my liking, but unfortunately, all these losses are necessary. So the first one is very simple: a reconstruction loss, an MSE loss between the rendered and the observed image, mask loss, MSE loss between the rendered and the observed mask. Now here things start to be a bit more interesting. We also have an occupancy loss. This occupancy loss tries to encourage that rays from pixels within the object mask should be internal to at least one part or nerf. We also have a coverage loss that ensures that our model would not result to degenerate part arrangements, meaning very small parts or parts that are completely outside the object. And of course, because parts also need to have some semantic meaning, we want parts to be non-overlapping. And since our goal is controllability, we also want our parts to be relatively comparable in terms of size. So we don't want to have gigantic parts and very, very tiny parts because we want to have uniform control over the object. Okay, let me show you some results. So starting from this tractor scene, here we select the bucket and we move it towards downwards. You can see here the per part decomposition, and you see that throughout this motion, the rest of the parts do not change. This also happens for the case of the translation. So here what we do, we take the cockpit, cut it, and move it in front of the tractor, and you see that the rest of the object remains the same. And of course, this is also the case for some other operations such as scaling or as coloring. If we weren't having this hard ray part assignment, the results that we would get would look like this. And the reason that this is happening is because now the is not determined only by a single nerf, but of a collection of nerf, meaning if we change one nerf, everything changes. For the case of color changes, this operation is not even possible. Here you can see some shape synthesis results. I think they're promising. They're not yet super good, but I have to say here that we are not using any adversarial losses. Yet I think that this is interesting because all these objects are editable. And what I really like a lot are these interpolations where, for example, starting from the scooter, we can get a motorbike. I think this is very cool. This is probably my favorite visualization throughout all the paper. And I'm showing you these results so that I can show you that the latent space is very meaningful also on a texture level as well as on a part level, which is a bit more semantic, and I think this is important. We can also interpolate on parts, meaning we can select one part and change its location You can see here the variations, and you can also see how it changed for the final object as well as its texturing. And one thing that I believe is also exciting is the fact that we can select different regions of objects and produce new meaningful variations, such as, for example, here we select these parts and we keep the texture of the first chair, whereas here we select the geometry of this chair, but we keep the texture of the bottom part. And I think these are interesting operations. And of course, we're not limited to only mixing two shapes, we can mix more. Okay. Let me wrap up a bit. So the field of generative models for objects is very large, and based on the categorization that we did before, if we were to compare our model with NERF-based generative models, you can see that we have a similar representation. Both are neural fields with the same level of supervision. However, the benefit of our model is that we can have more intuitive control on the generated shape. Here you can see some results. I think that the quality of the Get 3D that was recently published in last year's NeurIPS, I mean, this is not so recent, but yeah, it was published in the last year's NeurIPS, is significantly better than both all the NERF-based models. And I think this is partially because of the fact that they're using a differentiable renderer. And what I found very interesting is that if we compare our model with the part-based generative models that use a 3D supervision, you can see that the results, even though we don't use any explicit 3D supervision, are very comparable. You can also see this in terms of numbers, but I don't think numbers are that important. I just have them here for completeness. And just to recap, what I have introduced is the first part-aware generative model that parameterizes parts as NERFs, and it enables intuitive part-level control. And since it does not require explicit 3D supervision, it means that it can be easily trained. Is it perfect? Of course not. Texture quality is a big issue. We really need to work on that to improve it. And in addition to that, the semantics are not necessarily interpretable. I didn't show results on this, but I think this is a big issue. So before I complete, I just want to ask one more question. So similar to this work, is it possible to have a generative model of 3D scenes without requiring any 3D bounding box annotations? And I just want to put a teaser here for one of our recent works, where the answer is actually yes, we can. We can perform scene synthesis condition on semantic layouts. Ideally, I would like this to not even be a semantic layout, because this representation, even though it's in 2D, it's very, very powerful. However, you can see here that our model is capable of generating plausible variations. And the pipeline is inspired by the recent EG3D, and it's relatively simple and intuitive to train. So although I presented this work, all these papers was definitely not done by me. So yeah, there has been the work of many great people. So thank you very much, and sorry for taking longer than expected.
Thank you. Yeah, any questions for Despy? Online as well. Any questions from Zoom? Please feel free to just add. Oh yeah. Huh? Yeah, just come out. Yeah, I guess to the mic at least. Yeah. That one. Yeah.
All right. Yeah. Thank you for the great talk. So I actually have two questions, and I also come from a computer vision background. So one is kind of technical, and I guess the other one is a little more open-ended. So the first question is, so it seems like the room generation quality and all that is really impressive, at least qualitatively. I was just wondering, like, what are some quantitative metrics that you consider?
This is a very, very good question. So in this project, we only consider PSNR, which is a 2D metric, and this is a bit bad, to be honest. So we render the images and then compute PSNR. However, I think it's very, very interesting if we can think what type of 3D features we can use for 3D PSNR metrics. Can we use PointNet? I don't know. Can we use implicit shapes? I don't have a good answer to that. Another alternative that we try to do is we try to use a 3D bounding box classifier, because we also have like a 2D classifier. We also report KL divergence in terms of the distribution of the objects that are generated in the scene. But to be honest with you, mostly 2D, very bad metrics for a 3D generative model.
That makes sense. Yeah. So my second question is also kind of related to my first question. So I kind of feel that, especially related to your first work, like maybe one of these strategies that we can take is to like have generative models that can personalize to the user. So let's say,
Yes.
you know, maybe like I have really like red chairs, and I don't want my generative model to generate blue chairs or something like that, right? I mean, on a bed in the center of my room and nowhere else. So we also consider those directions.
Yeah, so this is a fantastic question. And actually, there was a master student from Greece that did exactly this as a master's thesis as what you're describing. So the problem the problem that the first work has is that it is completely style agnostic. It can generate a blue chair, a yellow chair, and I don't know, a green chair in the same room, which of course you wouldn't like to have. So you can take into consideration style information. Unfortunately, this brings us back to the problem of data, because the style annotations that we have are very monolithic, meaning that we have some single word description saying luxurious or Chinese or I don't know, Gothic or whatever, which is not very useful. What we did is that we generated from the images features using a clip pre-trained image encoder, and actually this had very powerful image features that we used for style guidance.
Okay, thank you.
You're welcome.
Any other questions, both in person and online? Is that the class? Oh, no.
No.
Okay. All right, thanks. Let's be again.
And starting this fall. With that, I'll turn it over to you, Fernanda.
Sorry, thank you. Sorry if I wasn't unmuted before. But thank you for the nice introduction. Let me see what you see, what view you see.
It's a little bit tricky. So somehow I only see a little bit. Wait, maybe let's see. Can you reshare? Maybe you can like here, just stick here, but in Zoom, don't exit the presentation. No, start the presentation.
Okay.
First. Let's see if this actually already worked. No. So now go back to Zoom, switch out to Zoom. Don't exit the presentation. Switch to Zoom. This is on Zoom. Oh, it's on the other side. Okay. So stop share this and then share it again. So this is it. And let's see how that works.
Okay.
Yes, that worked.
Thank you. Thank you. Apologize for that. Okay. I guess y'all see this is fine, right? We can all survive. Okay, so now we're back in the construction engineering domain. I'm a construction engineer. So my interest is supporting the decision-making process of engineers in construction. So a lot of the work here that I'm gonna talk about here today is on this built environment research at the interface of engineering and computing. back when I first started my academic career at the University of Texas, most of my research was around building information modeling and technology applied to construction projects. Slowly, and you'll see why in the trajectory of the research that I'll be describing, why I've been moving more towards information modeling and sustainable systems engineering. So these are just some of the research projects that I've been working on recently, but I'm going to highlight these three that are circled there in this talk here today. But before I get into that, I wanted to acknowledge the people that are behind all of these different research projects. One of the best things about being an academic is working with really smart, motivated people. And you'll see their names highlighted throughout several of the research projects. The ones in bold are the ones that I'll be talking about some of their work there. But I feel like I'm really lucky to be able to work with all of these different individuals. So let's talk about this first project, virtual reality in construction. So this was commissioned by the Construction Industry Institute. So if you've never heard of CII before, they're a research consortium that brings together construction engineering companies and owner companies with academics, with that idea of pushing the capital projects industry forward by bringing the subject matter experts, folks from industry, to academics that understand research projects together. And so they typically commission research projects that are of topics that are of interest to them. Most of CII member companies are in the heavy industrial sector. So you'll see that some of this research is heavily leaning towards industrial construction projects, which also has a lot of complexities that from a geometric standpoint that we'll look at. So this project here, the PhD student at the time that was working in this project was Bing Han. He's now an assistant professor at UC Denver. So in this case here, what we were commissioned to do was pretty simple. They just wanted a guidebook of, okay, we're a bunch of heavy industrial companies. We want to be able to use virtual reality in our projects. But that's just like with any technology, it's like a squirrel, right? Oh, there's this new technology. Let's see what we can do with it. And we see a lot of that happening in the construction industry with new technology, people wanting to prototype or use that new idea in that project. In this case, we saw an opportunity to also assess what are use cases that are appropriate for this type of technology in our project. So we looked at a variety of use cases from serious gaming, narrowed that down with our SME teams. We found one of the two use cases that we ended up doing user tests for was a design review use case. So this is what you see there is a liquefied natural gas plant. And what we were doing is trying to answer the question of, does virtual reality actually help engineers make better decisions or identify design errors, identify more design errors if they're interacting with that 3D data immersively versus in a traditional 2D screen. So that's what we're trying to answer. So we did do the guidebook. We looked at especially how to set up these teams, how to develop functions that we could roll off into multiple projects and not have to redo and redesign a bunch of these functions for each new project for several use cases. This team here is composed of members from the industry. So the people there in the photo with me are from 3 different contractor companies, Zachary, Fluor, and Black & Veatch. These are big engineering and construction firms that work in multinational projects. So they worked alongside our academic team to develop the guidebook and the study. And the little girl there that you see at the time, she was 3 years old. That's my daughter. So she's been going to these conferences for several times. And I like this photo because it just shows that young people just find it very easy to interact with this data. And you'll see from our results how it also enhances their performance. Not this young though, it wasn't meant for this age, but I just like that as a metaphor there. So ENR was at the conference there when we presented in 2019. ENR is a weekly magazine focused in for the general public in engineering and construction. It stands for Engineering News Record. So they published this article, CII study finds virtual reality helps reduce design errors. So I want to explain what that means there. So in this case, let me show you an example of a design error that they were walking the model and trying to identify. So this is the orange object is a pipe spool in like I said, a liquefied natural gas plant, an LNG plant, right? So these are very complex geometries. A lot of these pipe spools are pre-assembled, pre-manufactured offsite and welded, assembled on site. And so you see that there are 6 support objects that are not quite, I don't know why that thing is, that are not quite touching the pipe spools. So they're not really supporting those pipe spools. So the idea, that's just an example of a design error that engineers should have identified if they were walking the model virtually. So these are design errors that are not automatically identified if you're running an automatic clash detection tool. So what you see here, we did a series of user tests, and they all had to walk the model, identifying these types of errors like this one, right? So the difference was that we had 2 groups of people, novices, we had about 45 novices, people with engineers with less than 3 years of industry experience, and experts. They had more than 3 years of industry experience in heavy industrial projects. And then within each of those groups, we split them into treatment and control group, right? So the treatment group, we're using an Oculus Rift headset, and the control group, we're interacting with that same exact model in a 2D screen. So what you see in the results is that for the novices, so much like my very young daughter, right, they identified more than double the number of errors in the model by simply interacting with the data in a different way, with the model in a different way. The experts also had a statistically significant difference, but not as drastic, right? So what that shows us is maybe we could use this form of interaction to really train novice engineers to learn this process of design review. Bing later continued that work. He then looked at other use cases of when does augmented reality is not the best solution for a specific problem. Maybe it's mixed reality. Maybe it's other forms of way to interact with the model. So then he developed a workflow that he called a generic XR model to just minimize the development time of that process there. We also interacted with a highly interdisciplinary team, and I'll talk about Planet Texas 2050 in a bit, to develop interactive tool to really teach the general audience about scientific research output. Instead of a traditional PowerPoint presentation or poster, we're trying to share scientific output in an interactive manner, and also teach concepts related to sustainable systems engineering in an interactive way. So here you're looking at imperviousness, and then the person is trying to connect concepts and to understand it. Is it related to water, energy, ecosystem services, urbanization? What is it related to? So you see that it's not related there to energy. You can pull up a video and hear more about what imperviousness is. And we do that with several different concepts related to sustainable systems. And then you move to this other part of this lab, and we interact with data that was estimated or developed by a series of urban planners of how population growth in the state of Texas. So the title 2050 is because the population in the state will double between when we started this project in 2018 and 2050. So there's a lot of stressors put in our infrastructure systems there. So we have to learn how to deal with that population growth in the state. So they're making those predictions in terms of water demand in our state. So this next study here is related to updating. How do we automate the process of updating living BIM models? So I have 2 PhD students that worked in this project at any given point. So Jungwon Ma, he's an assistant professor at Concordia University in Montreal, and Thomas is an assistant professor at Arizona State University. So the original idea with this project, which I like to call the poetic title, Living BIM, is just this idea of buildings as living organisms. They change throughout their life cycle. How can we remove the human from the equation when we're trying to update these models? Because we see the challenge with using these models in the operations and maintenance phase from an AC perspective is removing the barrier of of updating these models. Lots of facility managers don't have that expertise or in-house staff to maintain BIM models up to date. Nonetheless, like that leads to a lot of money spent, and this is just in the US alone, and these dollars are outdated dollars that are not even in today's dollars, but still it's significant. When you're trying to update a facility, you have to go and survey that facility and generate that data. So they're constantly changing, but we have to figure out a way to better update them or remove the human from the equation. So our approach in the Living BIM project was leveraging 3D imaging, semantic segmentation, and model federation. So at the time when we started this research, our smartphones didn't all have depth cameras, right? So we actually had a sensor, a structure IO sensor added onto an iPad so we could generate the depth data as well, along with the color data. So we created this little app so we could collect the 3D mesh data, and then we could label it, semantically segment it with the help of lots of undergraduate students. We semantically segmented this data, labeled the data, to then use that to train our algorithms. And we're lucky that at the University of Texas, we have the largest supercomputer, academic supercomputer in the world, which is a part of the Texas Advanced Computing Center. And so we use that. We mapped our models to TAC. And we created this data set called 3D Facilities that is a specialty data set. So it's a semantically segmented data set, and I'll show you what it contains. But we didn't just use only 3D facilities. We built off of existing data using transfer learning, and we use open source algorithms. So that's our general approach. We did publish this data set, so it's available for anybody to download. It did get like an ASCE data sensing and analysis best data award, because like I said before, this is not something that's traditional in the AEC industry in terms of publishing data, but making an effort to create these data sets and share it. So we're trying to change that culture in our industry. So what 3D Facilities contains, it contains 110 scene reconstructions, and they're projected into 2D space. So what goes into the neural network are actually these 2D 25,000 individual RGBD frames that are labeled. So that's what we use to train our data set. So we initially, when we were training our algorithms, we started with only color data, then we added depth, then we added IMU data as well. And we're able to automatically classify 13 different classes of objects, which was at the time a lot better than any previous algorithm had done before. And we're still working through this research in terms of the next step of then, once we identify that change, actually modifying the model using generative design. And you'll see that most of the publications that we publish, they're all from the engineering domain, right? So in papers in automation and construction, advanced engineering informatics. So that's where we tend to publish this work. And I'll wrap up here with Planet Texas 2050. This is pretty interesting because this when we talk about decision making, right? So a lot of my work is motivated by supporting the decision making process. This is to the extreme in terms of deep uncertainty, right? So Planet Texas 2050 is one of 3 Grand Challenges initiative out of the University of Texas. These are 10-year programs that are internally funded, and they bring together researchers from 10 different colleges on campus. So there's 3 of them, 3 active programs. Planet Texas 2050 is focused on climate change and population growth and the impacts in our cities and infrastructure systems. Whole Communities, Whole Health is a longitudinal study of population health in a vulnerable community. And Good Systems focus on ethical artificial intelligence. So I'm part of Planet Texas 2050. The idea is that each of these grant challenges gets internal funding. So we operate like a startup, and then we apply for external grants during that decade. So Planet Texas has had over 140 researchers involved in the study, 40 different departments across the university. You can learn more about us in planettexas2050.utexas.edu. And you can see from the leadership committee, so we sort of operate like a funding agency, but also we do research internally. You can just see from the affiliations, people from integrated biology, community and regional planning, geography and the environment, geological sciences, archaeology. So lots of different disciplines represented, and we're all trying to solve this wicked problem, right, of climate change and population growth and the impact in our cities. So we organize ourselves in what we call 6 flagship projects. And the project that I'm involved in is called Equitable and Regenerative Cities in a Post-Carbon Future. So we're looking at how can we co-design more equitable and regenerative cities alongside communities. So lots of people that do community engaged research, and we're building off of a lot of past research that we had done early on in Planet Texas 2050 days, including saw that the virtual reality there. So the premise here is that in our cities and infrastructure systems, we our production cycle is very linear, right? So a take, make, use, dispose model. So we're moving more towards a circular model in which we're decoupling that growth from resource consumption. So thinking about waste can actually be a resource, and that can have a huge impact in the construction industry. From a dollar value as well, not even thinking about the sustainability aspect of it. And in the construction industry, we still haven't built more than 50% of the infrastructure, buildings, roads, everything that we'll need by 2050. 50% of it hasn't been built yet. Yet, if we continue to build how we're building, using the same processes, we're just going to run out of natural resources. So what that tells us is that we really have to rethink how we design and build. Otherwise, we won't have the natural resources that we'll need to continue building it. So we're trying to apply circularity at the urban scale. And that's what we're doing there in this project. So in terms of visualization, right? How are we doing that? How are we leveraging visualization in this project? So engaging with the broader audience in this conversation of there's a lot of invisible systems all around us in our cities that enable our cities to be more resilient. And an example is what you're seeing here. This is a C-Home district in downtown Austin. It used to be a power plant. It's decommissioned now. It's been transformed into a rainwater harvesting site. It's underground. Most people don't even know that it's there. So what we worked with Microsoft to develop a mixed reality demo in which people can visualize that underground rainwater harvesting site, that underground infrastructure that actually serves as a buffer when there's major rain in the city, and we're not flooding the river that runs downtown. So that is rendering these invisible infrastructure systems visible so that people can understand the importance of these systems. And at the same time, now we're pushing that even further by working with a decision-making under deep uncertainty. And the deep uncertainty that we're talking about is climate change, right? So in this project, we're one of 4 urban integrated field labs that are funded by the Department of Energy. And we're making climate projections for the next 80 years, and then integrating those, bringing them into flood models. And this is a very large interdisciplinary team. So we have teams from 6 different universities, a national lab. There's 29 research scientists involved in this project. But the overarching idea is make these climate projections, which feed into the flood models, which we then integrate into our co-design models, which we're designing climate resilient infrastructure systems, and using visualization to be able to engage the broader stakeholders in that process of co-designing those infrastructure systems. So one of the ways that we do that is we collect raw data of the built environment. So here we're collecting data of a pump station here in Southeast Texas. So this is a region that that's very flood prone. Much of the region is below sea level. This is where there are a lot of refineries, a lot of power plant. It's what enables the production of energy in the US. When Hurricane Harvey hit in 2017, this area flooded. It was nearly 3 meters of flooding in this area. So there's a lot of vulnerable communities that live in this area. So they suffer from both flooding and air pollution. So we're trying to generate these models that can then be integrated. The flood models can be integrated into them, and we can simulate different scenarios there of climate resilient infrastructure systems that we're designing. So in this case, we're trying to work with the problem of model integration. So we're building a knowledge KMP, knowledge management platform to integrate all of these models together there. So I know I talked about a bunch of different topics there, but I think that the underlying connection there is the importance of understanding what these use cases are, right? How can we better support the decision-making process by leveraging data, by leveraging models, by leveraging integrated models to understand what people need to be able to make better decisions. And that way we can move towards a more sustainable and resilient world moving forward. So thank you for listening, and I know that we'll have some time in the panel discussion to talk a little bit more.
Right. Yeah, thanks a lot for the great talk.
Should I stop sharing?
Yeah, it's fine. Yeah. So question time. So any questions from here? Euro.
It was actually very interesting, and I like how we end up with this talk more broadly about sustainability and anything climate change, and also the big urban development that's come ahead of us. These are very important topics to keep in mind, and this brought all the big aspects of discussing before about having as a metric cost. But maybe we have to think of costs, not only as construction costs, but maybe as cost of living, the cost of sustainability, like so not like what are your thoughts on that? Like, what's actually a question I get more fundamental.
Yeah. So I like to to break that down. So if you think about resilience, right, what does that mean? So does that mean that you're enabling a community to bounce back to the previous state if a stressor event takes place, right? An acute stressor takes place. But sometimes when you're talking about vulnerable communities that have been suffering from chronic stressors like poverty, food insecurity, sometimes they don't want to bounce back. They want to bounce, what we say, forward to a different state, right? So I think that there's that cost of how do we invest in building resilience to enable communities to be more. That's why we talk about this whole work from an equity lens, right? Because we want to enable people to be in a better place. So there's the cost associated to that, yes, but that's the cost of equity. And oftentimes equity means some communities might need more help than other communities. And it's adapting to what the needs of each stakeholder groups are.
Other questions from, yes.
So, one example, how can we, what resources, if they run out of resources, how are we going to face that?
Yeah, an example is concrete, right? If we continue to heavily rely on concrete, which is a major construction material that's used globally because a lot of people know how to build with concrete, we simply will not have the raw material that's used to make concrete. And there's a lot of environmental impacts associated to the cement industry as well. With population growth, we're going to need more infrastructure but at the same time, we won't have the same input, the same number of the same availability of natural resources to build all of those systems that we'll need in the future. So one way that we're trying to address that in the construction industry is via a process called design for disassembly, right? So I didn't talk about this, but I do have one of my current PhD students doing this kind of work, that we're thinking proactively. Instead of when a building goes out of commission, you demolish it, and a lot of the rubble just goes into a landfill. Can we start now designing proactively, thinking about disassembling that infrastructure and reutilizing those pieces and parts? Because each one of those resources are now much more valuable, because we're not going to have enough of the raw material to go around to build new systems. So that's one other line of research that's happening a lot now. There's a lot of challenges from a computational standpoint, computational design standpoint too, of thinking about designing with disassembling in mind, and even how the materials that you use for that also have to be pretty unique, because a lot of let's say cast in place concrete systems are not really adequate from a disassembly standpoint. So I don't know if that answered your question or generated more, but that's some of the challenges that are happening now. And Texas is just one example, right? So it's a state that's growing a lot and rapidly. So it's pretty, the name Planet Texas 2050 is because what's happening in Texas is just can serve as an example for what's happening globally in a lot of heavily urbanized regions around the globe, that there's an influx of people in those regions. It's just putting a lot of stress in urban systems. And 2050 is just the year that the population will double, is predicted to double compared to the year when we started, which was 2018, which is not too long if you think about it, that you'll have double the population.
All right, so I'm sure that we still have a lot more to discuss, but I think at this point, let's just get caffeinated. Yeah, so we'll have this coffee break until 4:30. This is about 20 minutes, and we'll have a great panel discussion at 4:30. And then hopefully everybody would even get a chance to speak as well during the panel. Right. Okay. Yeah. So yeah. So I was unmuted. I'm sorry. Yeah, I was not unmuted. So yeah, you guys can go. And I was just saying that we are going to a coffee break, and then we hope our invited speakers and also our audience can remain on the line at can join us back at 4:30 for our panel discussion. In 20 minutes. Thank you. Where is my coffee break slide? Yeah, I was trying to find my coffee break slide and I couldn't find it. I'll just make it new one. Right, my new coffee break slide. And I cannot share because she's still sharing. Mosen, can you stop her sharing?
Also try this
This?
for the panel discussion.
I see. We didn't really make it work last time. So, and then, but we could try it again. So how is this supposed to work? Do you think this potentially actually need power?
No, I think it gets power through.
Oh,
Ooh.
much better. Adapter. Oh, we have a big one.
Oh, sorry, I'm just connecting this for people who are passing by if they want to stop by. No?
And Robert Chinese. Yeah, so,
Hello? Yeah. Hi, test.
Hello, test. Hello.
Yes, I can.
Hello, can you hear me? Okay.
Yes.
Okay, we can hear you too. The mic check works from here. Yeah, Fernanda, do you want Despina? We have a panel situation. Yelda, would you like to also join us? You can step out now. Okay, yeah. Oh, we're never.
Sit in the edge so you can sneak out. Yelda is gonna sit right here. So she can sneak out.
Yeah, yeah.
It was really interesting to see your presentation and my presentation. I love your presentation. So different.
Okay.
But it was really cool.
So, I want to begin by engaging the audience first. We are missing one speaker who is coming, is on the way. But I might still play the game because I know what they will say. So we are missing Manmohan, who is gonna come. He was the speaker that talked about the renderings. And so the way I want to do that, I'm gonna tell you, oh, here he is. Perfect, welcome. So we are at the beginning of everything, and oh yeah, let's come this way.
So this is the game time?
This is a game time. It's not for
Okay.
you. You're
Oh,
not
not
just
for us.
listening,
Okay.
but you will enjoy it, hopefully. I don't
Okay.
know, maybe not. But it's worked very nicely for your side. So I asked all the speakers to tell me one sentence of what computer vision for AC, architecture, engineering, and construction means to them. And I'm going to tell you that sentence, and you have to tell me to which person it corresponds, right? We have 5 people here, 1, 2, 3, 4 people here.
And we have to keep a poker face.
Oh, and we also have online Manny and Pingbo as well, so you can see them over there. I'm going to make this a little bit bigger. So the information that I will give you will also correspond to them too. So we have 1, 2, 3, 4, 5, 6 sentences. You can pick and you can shout which one you think it is, okay? I will start with the first one. Computer vision for AC means the set of tools that allow us to recreate our cities and homes in a way where any novice practitioner could freely interact and modify with their environment. Who do you think said that? Anyone also online, anyone who wants can just speak up. Speakers can also participate, it's okay. Although it might sound, you can also, the person who said the sentence can also just say someone else to make it even harder. Anyone? A guess? Who did you say? Despina or Manman?
Yeah, me.
Manman, no.
I would guess Despi.
Yes, very correct. One down. Okay, here we are.
I paid attention. Wait, are there prizes?
Okay, the second one is acquiring, processing, analyzing, and understanding digital images and extraction of high-dimensional data in order to produce actionable insights that support safe, productive, efficient design, construction, and maintenance of buildings and civil infrastructure systems. Who said it? In person or online, the speaker can be.
That's a tough one. I would say Fernanda.
I agree. I agree.
It's not me. But
You
at this
sure?
time, whoever did that was very eloquent.
Are you sure?
You can take credit for it.
Anyone?
Are we there?
No. I actually don't have one for you.
Yeah. I was gonna guess Mani, but Mani was pointing in a different direction.
Correct, it's money. And
Is it
Manny
Manny?
followed my suggestion.
Ah.
Very good. Okay, the next one. Computer vision in AC can augment human performance, enabling us to deliver safe and more complex projects. Safer, more complex. Who said that? Anyone? So we have Manmohan, Fernanda, Pingbo left, right? Yeah. So out of those three. Pingbo? Think again? No? No. Consider the key criteria of safer and more complex projects that augment
Fernanda.
Here we are, yes. It's all the keywords. Good. Then we go to the next one. The ability to interact, create, modify, visualize with built environments just as humans do. Interpretable, semantic, realistic, structured. So the ability to interact with built environments just as humans do. Who said that?
They have too
Yes.
much questions left now. Yeah.
And I guess we have one more, and let's see if you paid attention to which speakers we already revealed.
Process of elimination.
Yes. Computer vision for AC means non-contact and high-resolution information that allows computers to help humans see what they may miss by their eyes and all the information that could not be collected by point contact sensors.
There's only Pingbo.
There's only one.
Yes, I paid attention. It is Pingbo. Okay. So this is the small game that I hope made you a little bit more at ease, everyone, including speakers and audience. And
I like that game. I might copy that.
Yes.
With credit. I'll credit you
No problem.
in the future.
You can do it without credit. So I always like to begin panel discussions in two ways. The first one is the one you just saw. The second one is more to warm up the speakers, not the audience, and is to throughout the day-to-day, hopefully you were able to hear a little bit more here and there some other speaker from the workshop. And I'm wondering if there was something that really grasped your attention, really sparked your interest, something maybe you disagreed with. And if you can maybe pinpoint to that, and we can take the discussion from there. And whoever wants to start first, online or in person, maybe someone online wants to start. Manny, Pingbo.
You can start before you have to head out.
I can start. Oh, Mani, you want to start? Okay. Yeah, I found out the DESP is a pronunciation. Okay, DESP is that right?
Yes, it's perfect. I'm so sorry.
DESP is work. It's a yeah. I'm not an expert on that, but I find it's very interesting. Make the scene editable. I realized that for design, construction, collaboration, there is a big issue called mass customization. When the designer want to customize part of the design, it usually takes a very, very long time for the engineers to make a big cycle, say, okay, I need all the design information and I need to figure out how to construct it. Then whenever the customer want to make a customization requirement, it takes very, very long time. It might be interesting for us to use this technology, if I understand it correctly, to produce a lot of different customization possibility of a design, and to understand which customization will cause the real trouble, and how much trouble is going to cause, and how people should be propelled. What I mean by people is the construction engineer or the designer. I don't know. So that's a customer. That's my understanding about that. If I understand it in an incorrect way, please correct me. Sorry.
No, I think what you said is absolutely perfect. So if I can share some behind the scenes story for this paper that I think it's interesting. So this work, the first one with the scenes was done during my internship at NVIDIA. And actually it was a project that the IKEA was paying for. So IKEA contacted NVIDIA because they wanted to develop a tool where people could like draw their living space, and they could select like, a free hat and sofa, for example, and have a model that automatically completes the rest of the scenes. And one of the biggest challenges that we had is that we were trying to find an office, like some architects that could give us some sketches of the rooms. It was horribly difficult. I mean, we failed completely. So this is why we used the scenes, the relatively simple scenes from the 3D front dataset, which is the best data set that we have, but unfortunately is quite limited yet. So, if we can get access to more indoor scene data set, also like of bigger houses where we have the information of the walls, windows, doors, that would be amazing. It would completely unlock this type of tasks.
Perfect. Desmond, do you want to take it now and say something else maybe that you've seen or you heard? If I'm not putting you on the spot.
No, not at all. So I heard a lot of interesting things. So for me, I really liked to listen to the things that are interesting from the perspective of people that actually know the job. Because, we do ML, computer vision, but we don't really, at least I have a very hard understanding what will be useful for you. Because, for example, I was thinking that, okay, you know what? If you draw a sketch and then I convert it to a 3D model, that will be major. But after talking to some architects, like Alberto, who is there in the audience, was one of them, I came to realize that you don't really care as much about these things. So yeah, I'm also like very, very interested about the environmental aspect of architectural engineering. So I really like the connections that you made in the presentation. For me, this is something that I deeply care about. And it's, at least in my eyes, it's very hard to put into words and say, okay, what's the impact? And when I was talking about cost, for me, cost is not only about money. It's also like, cost can be the impact that we have to our environment. So I really liked these connections that you drew in your presentation. Thank you. Appreciate it.
And I was chatting with Yelda after the fact about the construction industry is the most wasteful industry. About 50% of everything that's in landfills comes from the construction industry. So we're very impactful, right? And Yelda was even talking about a statistic of all the airplanes in the world don't generate as much CO2 as the construction industry does. So I think if we really rethink how the built environment is created and is built, we can have a huge impact in our environment too.
Yeah. That's actually just cement production in the whole world is a lot more than, I forget the numbers, but a lot more than what the greenhouse gas emissions produced by airplanes. No, it's very, very impactful.
So we have to stop using cement.
Yeah. And as Fernando was mentioning, I mean, we're gonna run out of raw material too. We just have to find ways to recycle that material.
Can I ask you something? Sorry if I am jumping in, just like a thought that I have been asking, I have been wondering, do you think 3D printed houses is an option? Can be doable in the future? Could be a solution to this cement?
You know who could answer that question? Mani. We would love to hear from you. Did you hear the question?
Yes, I did. Thank you. We have an extension here at the University of Illinois, Construction Engineering Research Lab of the Army Corps, that has been conducting a very fascinating project on 3D printing, which is using local material for the purpose of 3D printing. That's actually a very creative way of tapping into existing resources and using them for the purpose of 3D printing. There are many business aspects that can challenge the usage of technology, like many of the things that we have in construction and design world. And I see a lot of promise on that front. That's all I can add. If you don't mind, I actually want to go back to the earlier question that was asked. What was really fascinating listening to all of you and also our competitors was sort of the interaction between HCI, human-computer interaction, computer vision, and computer graphics. Pretty much every presenter who presented on various use cases touched at least 2 out of these 3 topics. From Manmohan, who touched on some of the HCI components of how you can actually insert and what that really means from a computer graphics perspective, all the way to Pinbo that touched on HCI from a safety perspective, what it means to have augmented reality for that type of support. It's really fascinating when we look into how many of different disciplines need to come together to satisfy use case, which leads me to the second point I wanted to make. When it comes to validation, we often go back to some of the more fundamental scientific metrics that even Mike referred to earlier today. But when you think about use cases, I want to go back to what Avida mentioned today, the importance of having human in the loop and the role that products can make. for those of us who happen to be in the computing and civil engineering world, and we bring some of these components of computer vision and AI broadly to civil engineering, we are also not in the world of products. We only work with that 1% of the 1% of the market that happens to be first adopters. And when you start looking to the masses, and if you want to truly get that feedback, it's really, really important to have that element of human in the loop and product. And it would be great in the future if we can engage more of technology companies, because they're also an element in this chain of going from core computer vision to applied computer vision to things that truly solve our use cases.
Does anyone want to say a bit more about the human aspect? Pingbo, you discussed a lot about the role of humans in the process of having more safe operations. What are your thoughts about integrating more humans into the workflows?
I think I would refer to our very recent efforts from ASCE. And the ASCE, we have a task force called IHMI, which stands for Integrated Human-Machine Intelligence. We are going to get together, and we already published a conference paper 2021 on I3CE computing workshop in civil engineering in Florida and Oregon State next week. We are going to have a track called IHMI on the conference organized by Yeda. She's there right now. And I could not say I understand the whole thing about IHMI, but I think I do wish that we could all together understand what human can do, what machine can do, what is the boundary between human and the machine. Generally, there is a I just use my very recent work as an example. We try to do like a data imputation to predict the deterioration of a vehicle, like trucks, right? Then we find out that if we do interpolation, some of those data imputation method, it's good, it's better than human. But if we do extrapolation, if we don't know the context, like the environmental, people driving the vehicle, how people drive it, and how they maintain those vehicles, then machine is not very good at human, and some human know something a machine don't know. Maybe interpolation and extrapolation is just like a very, very high level classification. I think we need to go deeper into that and to understand in what situation, for what type of tasks, machine could do something better than human, or machine can support human to do better things. And all those things is a huge area. I would say we need to work together, and I do encourage people to come to Oregon State to the conference of computing civil engineering conference and to participate in the discussion. We also have a special issue called IHMI for Journal of Computing Civil Engineering. We encourage all of you, if you are interested in this area, please submit your manuscript. Thank you.
I think the comment that Pingbo just made also connects with the ChatGPT point that you wanted to make earlier, right? Of what's the impact? Are we going to be seeing ChatGPT helping project engineers, construction engineers in the future? How so, right? How do we do that? You probably all have used ChatGPT for one reason. I've been using it. It's great to write letters of recommendation for undergraduate students to go to grad school. It's great to write memos. Now I'm transitioning more to administrative roles. You will not believe the amount of memos that I have to write. I use ChatGPT to help me write memos super quickly. But how do we do that for projects, right? What are the challenges? And I'm just asking everybody here to chime in.
Yeah, so I think that's something I was wondering about as a computer vision person sitting through this, that so fundamentally we are talking about built environments here, and we could extend this to pretty much every man-made product that we see around us, right? So there's what we see is a manifestation of a creative process, a design process. There's an engineering drawing that happened. There's a CAD model somewhere for everything out there. and there are engineering specs to which something is fabricated and manufactured. So I think that's a very interesting space where simulation, all the progress we are making in simulation and all the progress that we are making in language could come together. Because as a user, if I have to redesign my house, there's a language I speak, which is purely defined in terms of utilities. I want this room to be bigger. I want to fill up my swimming pool and whatever I need, right? And that means something completely different to someone who's actually creating or doing the engineering for that. So how do we go from completely natural descriptions that people have about what they have visualized, convert that to an engineering description and be able to simulate it and connect this feedback loop to the user and say that, and then the user says that, oh, that's not what I had in mind. I want to tweak something else. So for me, human in the loop means that, like, how do we get the human who's the user speak the language of design that all these man-made things require without actually knowing that language? So, and there, I think simulation and large language models probably have a big role to play.
I have something small to add to this one. I think another very interesting use case of large language models is data generation. But in what sense? So for example, let's try all think of, let's imagine that we want to generate a Ukrainian war zone. What type of objects are there in a Ukrainian war zone? I don't know. I mean, I'm lucky enough, I've never experienced anything like this, but we can use ChatGPT to let us know what type of objects should be in a scene that is a Ukrainian war zone, or like, I don't know, a saloon in the middle of the States, I don't know, whatever. And the thing is that if we have a list of objects, then we can use, for example, a library of assets of objects, and then we can texturify them or change their appearance, material, whatever. And I think this might be a solution to the limited training data that we have, because obviously we have the data set that we have considered like very few use cases. We cannot have use cases for everything. So I think for me, this is a very exciting use case of large language models.
I mean, I want to touch on a little more on the computer vision side of it. I mean, recently there's been a lot of text-based image captioning methods that are coming out, right? And I'm pretty excited because, many years ago, I used to be a field engineer, and one of the tasks I was in charge of was daily construction reporting. For those of you in the audience that have not seen that, that means you as a field engineer, you literally walk around the job and you just take notes of whatever is happening. You write down that you saw this contractor performing task X in location Y, and this is how much progress was being made. Extremely tedious task. Every owner requires that. And this is a very low-hanging fruit opportunity of bringing that and making a really good use of it. Now, speaking about it from a use case is pretty straightforward, but transforming that into a fundamental computer vision would actually expose a lot of interesting problems. One, oftentimes we have workers that are interacting with tools performing your tasks. Now, human object interaction is a pretty hot topic in computer vision. Putting that in the context of the work, understanding what's happening at the event level, and the fact that many of these models actually don't work when somebody touches an object. And look, the data sets that are being used in computer vision, see a lot of examples of dishwashing and things that are ordinary tasks that we see every day. But there's a tremendous amount of important tasks in construction that can transform into these data sets that community can use. And in fact, it's so structured. We know what type of tools are expected to be used, so we can significantly enhance that opportunity. So go back to what I started with, the textbook image captioning can actually help us a lot in terms of creating these daily reports that are really impactful for us.
So, but Mani, so what do you think in terms of, so my impression of vision language models is kind of that, like GitHub Copilot, right? So I think it's good at doing the boilerplate stuff, but not at the expert stuff, right? So, and so do you think that what field engineers care about really is, or is that the use case that you imagine, that you still need a human expert to actually spot the anomalies or spot dangerous situations that might arise in a misconstructed zone, whereas you get a vision language model to actually do the boilerplate stuff?
That's
and because Yeah,
Please.
so it's similar to like safety critical scenarios that arise in like self-driving and all, where some experience with these open vocabulary detectors has been they do interesting things, but they don't quite do the exact thing that you want them to do, right?
Yeah, I mean, you're touching on something really important. What is fascinating is that many of our construction monitoring or condition inspection tasks are visual in design construction, perhaps because we are a community of people that like visual data. We interact with visual data from design all the way to how we document everything. You look into every code that exists out there when it comes to inspection. They're dominantly based on visual data, meaning a superintendent walks around and makes an observation and based on some specification makes a decision as to whether this is safe, this is productive, this is the right specification from a quality perspective. But what has also been fascinating is that over the past 5-6 years, I've been heavily engaged in commercial activities of software solutions. And in my life as an academic, I've touched on non-visual data too. And what is really exciting about visual data is that whatever automation we do on it, you always have a proof that you can show someone that this is what my machine learning engine was able to infer, predict, and here's a visual proof that this is exactly what we saw. It's fascinating when people are being exposed to these AI algorithms at scale, and I'm not referring to those top of the top that already is bought into the idea. This is for the masses. They always question, can I trust this technology? So the fact that these, types of inferences are accompanied with visual references that you can go back and show that as a proof, hey, you see, I detected this defect at this severity level. That's already extremely promising because you can actually help with adoption of the technology.
Before we continue, sorry, one little comment here. We do have an audience, and I want to just prepare the audience that maybe in a couple of minutes from now, like in a comment or two from now from the speakers, I would like to open it up for you as well. If you have any questions, don't start preparing in your mind. If you have any, Mani, please continue.
And just to complement what Mani was saying in terms of inspection data, right? Using visual data for, let's say, inspection of a defect in a civil infrastructure system. I don't think we have to solve every problem, every level of complexity, but if we can identify or minimize the time that a construction, if you look at a bridge, right, an inspection report for a bridge, depending on how big that structure is, it can be like 200 pages, the inspection report that has every single element analyzed, pictures, tables, that somebody went there and observed elements of that bridge, right, and measured things. If we could minimize, do 80% of the work of the easy parts automatically and just leave the challenging parts for a human inspector to do, that in itself is going to save a huge amount of time. And we're seeing that with in the medical field, right? With, okay, maybe a radiologist that's evaluating images. Some of the images that are easy to evaluate can be done automatically by a computer vision algorithm. The more challenging, difficult cases can be done by a radiologist, right? By that human eye. Maybe one day, we have enough data that can be done automatically too. But I think if we can start by minimizing the manual labor that it takes, using visual data and just leave the very difficult ones for the human, that in itself is a huge contribution.
I love what you're saying, Fernando. For now, I think if we look at the bridge inspection, there is a big chance we need to find out what type of failure mode of the structure. It's easy and obvious to computer vision algorithm. We're not just looking at individual defects. We're looking at the relationship between defect and the human inspector. Somehow they know where to look at with a sequence to find out what's the failure mode. But computer algorithm seems like they are very, very good at locating defects. Right now, it's difficult for computer algorithm to catch up with a human inspector when they are looking at the context and to capturing the failure mode. And some of those failure mode is very difficult to distinguish by even a very experienced human, and not to mention by computer algorithm. Now, one thing we are trying to look at is that for our domain, we don't have enough data. It's always we don't have data. And we're not going to have like 1,000 pictures from the file scene. We're not going to have like 10 millions of pictures about how people are falling apart, right? We don't have those. But I think we have a good chance to use those research done by if my pronunciation is correct, Manmohan, and Despi, your work has been producing a lot of those synthetic data and the synthetic scenario. The question is, to what extent, in what situation, those synthetic data can help? In what situation is actually misleading the algorithm? Because civil engineering, it's a difficult business. If we have a model learned from the synthetic data, we got to have a good reason to understand what synthetic data is different from a real data. We don't know. And it's like a magic. We just got more data from a file thing. Maybe I don't know the answer yet. Maybe some of you know, is there any theoretical foundation to distinguish and to characterize what type of situation synthetic data is more reliable for training the machine learning model? What situation we should be careful? I don't know.
Yes. So, so that's a hard question for, I guess, machine learning in general, right? So usually we do not know how, or we do not know where distribution shifts will arise. We just know that they exist, and the only reason, or the only way we can determine that is through validation, right? So, but I think my feeling about synthetic data is similar to what I mentioned earlier, that I think there are the common cases that that one can simulate out. And those are essentially what we can simulate are things that we know or things that we have observed. And at least one step that we can take forward is to know that everything that we have observed in the real world is something that we can also simulate, because then that gives us the ability to go and modify things in a way that is that's physically meaningful, right? So, so I think that there's the difficult question of we care about anomalies in applications like this, or we care about defects and so on, for which fundamentally there does not exist a lot of data. And those are perhaps the type of things that simulation just fundamentally cannot help us there. But it can help us with the common cases. And that's where we can have machine learning speed things up for us, but it does not take away the human impact. I mean, I was wondering about a different thing actually when we were mentioning the parallel to healthcare or medicine. So because there's this real thing, there's a Wall Street Journal article on that a few days ago, that now you have decisions being made by AI, and they are actually sometimes in conflict with the decisions that the nursing staff make. And so who do you go with? And nurses increasingly find themselves overruled by AI. So there could be similar challenges in other safety critical applications also. So there's a defect on a bridge and a human expert thinks otherwise, but then you have AI telling you, no, everything is fine. And then one day, so over time, if we start trusting AI more, do we have fail-safe mechanisms? So that, I think, would be a sort of question that simulation would also face, right? So like, to what extent do we trust simulation?
That's a very good point. Did anybody want to add something to that? No, because I heard something. Good. I wanted to see if anybody from the audience has any questions about anything that we've heard today in the workshop, or any other question that is in your mind you wanted to address to the speakers, be that in the room in person or online. You can just step up to the mic, maybe. Anything? Can be thoughts. Yes, please. Yeah.
Yes. It's just a question regarding like the I believe like the data types, 'cause it's really cool to have like good both sides of the view in terms of like residential buildings and data with like indoor layout generations or design, and then the workshop is really nicely focused on large scale industrial commercial buildings. Are there any like fundamental different focuses with these two types of data, or do you think one of these days it's a matter of like scale, like we're working smaller scale, larger scale, but the problems, the formulations are actually the same, or should they be different?
Maybe I can try to share something.
It's open for anyone else.
Yeah, no, I mean, some thoughts, because actually we have been trying to answer a similar problem for the last 6 months or so. So the reason why we started with the indoor layouts here, like, is two reasons. One, because IKEA was paying NVIDIA, which was the obvious reason. And the second one is because we had more data, and it was, you know, it's also way more easier for me that have no idea of how architects design a building to familiarize myself, because, you know, so what this model does is pretty much by observing how furniture pieces are arranged within the scene boundaries, it can learn to regenerate these arrangements. So for example, without explicitly saying to the model, hey, nightstands are normally positioned next to the bed, the model discovers this directly from the data. I think that if we were to try to, so my goal when I started my postdoc was that I want by the end of my postdoc to have a generative model that can generate cities, like be able to generate New York. That was my vision. You know, you see, I didn't present anything like this, but I think this is still a very valid dream. However, it's way more complex because the relationships and all the things that we need to take into account are way more complicated. For example, for the case of scenes, NVIDIA has two very nice papers called MetaSim and MetaSim 2, where they try to recreate some streets from, I think it's also from Canada, but you know, the variability of the scenes that create is very, very limited. Again, we don't go to something that I personally think would be more interesting, such as doing bridges or doing, you know, some more interesting construction work. I don't know how we could do it, but I think if we have the data is one thing. And the second thing that I want to point out is in which format, because we computer vision people are very used to working with data in a specific format. So it might be a bit hard to tune our line of thought with the, I don't know, this blob diagram it's called. I think there is one data set that we are using, which is called the building GAN data set. And they have like the room layout within a building that has multiple floors, like as a, you know, as like this bubble gram. And I was like, what is this? How do you interpret it? But yeah.
I think I can reflect on your comment there. And I think the reason why we see a lot of indoor spaces in computer vision, in the computer vision domain, first off, we all are humans and we all spend 80% of our lives indoors, right? So we're sort of all experts and understand the indoor environment pretty well. So that's a really great starting point because we understand those spaces. When you start moving to engineered equipment and engineered systems, like in heavy industrial projects, you walk into a space that unless you have a background of understanding what those pipe spools represent, what those engineering systems represent, that's all gibberish, right? Unless you understand those chemical processes. So and the parallel is fundamentally, the geometry is the same, like of building systems. It's lines, it's it's fundamentally the geometry doesn't differ, but what it represents is something that might be more farther away from the domain expertise of us as human beings living in indoor spaces, right? So I think that's one of the reasons why we see a lot of computer vision applications in indoor spaces and floor plans in buildings, because we understand that better and it's easier to communicate. And we see less so in a nuclear power plant, like Pingbo said, right? Or in a liquefied natural gas plant, right? Simply because it's harder to communicate to a broader audience what those processes are. But I think if we can slowly solve problems in one, they can be extrapolated to other spaces as well. They're all built by the same types of people. right? They're all built by engineers. I'm not a specialist in chemical processes. I don't understand the chemical process that go about in a gas refinery facility, a gasoline refinery facility, but I understand how to build it, right? So it's all a matter of bringing together different expertise. But I don't know if that doesn't answer your question, but it's just a reflection, I think, on why we see that.
I think to an extent it did. I think your point. Oh,
yeah. So they can hear.
Oh,
yeah.
for sure.
Yeah.
I think it did answer to a good extent because I think it reminds me that like different spaces have different purposes. And is it for living, which what you would target for comfort, ergonomics, and whatever, or compared to industrial spaces, and it's as with many other systems, it's highly engineered. It's the metrics is a little different. Might not be necessarily for someone having a good time finding spot to map, maybe.
Yeah.
It's okay. Yeah. Thank you.
I saw Mani was ready to speak something about this. I saw Mani, you were ready to say something.
I was thinking about this in the context of business models and renovation and retrofit that happens in residential sector versus non-residential. So if you think about residential, there are all kinds of use cases, right? You constantly need floor plan. You constantly need to understand how you can change the layout. And thanks to a number of imaging system providers in platforms that now are being used for real estate rentals and buying new places, everyone has been exposed to these sort of a street view walkthrough experiences. And that data has been readily made available because of the large amount of use cases that you can envision. Now, automating that process is pretty interesting because you're not competing with service providers. In the non-residential world, we have a totally different set of companies that are in the business of generating floor plans and the business of generating models. And the cost of acquiring customers on that front is pretty high, and liabilities are totally different from the residential world. So it's being dominated by a totally different group of people, totally different business model. You don't see that data a lot. That doesn't mean that doesn't exist. Many of us actually come from a civil engineering background. We interact more of that data because the residential world is frankly easier from an engineering perspective for us to deal with, while non-residential parts where you have mechanical, electrical, plumbing, fire protection systems in close proximity to architectural and structural components, that's where engineering becomes a little bit more sophisticated. That's where there's more challenges for us from an architecture engineering perspective. So part of it has to do with the way that businesses have evolved and how the data has been made readily available.
And also how like an MEPF, that mechanical, electrical, and plumbing and fire protection systems in a building, that's less, there are less company secrets from a process standpoint in a building's MEPF system, as opposed to, let's say, a liquefied natural gas or a gasoline refinery facility. We don't have access to that data because many of these big energy companies have trade secrets in how they run their processes. So that's why we don't have access to a lot of that data as well. So it has to do also with the business model, even though fundamentally, like the fundamental raw geometry at the baseline is very similar.
Yeah, I can share my experience with the airport. Even though they collect a lot of data and for the air terminal, runway, and every part of the airport, I know they have a lot of camera, but they never share with me. I just don't know why, but some of you might tell me why. Then my guess is that for critical infrastructure, there is a very obvious reason. They don't want you to get those information for the protection of people. Some of those airlines, they might not want to let you know what are the something happens within their business, and they do not want people to get access to their data and to find it out. Generally, we may want to have a data sharing protocol, just like Mani has been saying. If we want to have that protocol, we need to solve three problems. Number one, it's a technology problem, which is obvious. Number two, policy problem. Number three is the business model, like Mani has been saying. Then if we look at these three issues, then it's not just about we need to get the data. People do not want to share the data at the policy level, at the business model level. Is there any way we can figure out an ecosystem to share the data in a reasonable way and with a reasonable protection for everybody?
Yeah, I also wanted to touch on something else that is happening at CVPR. I've been, following Twitter, and what was fascinating, a lot of conversation around startups and technology companies participating in CVPR. If you go back 10 years ago, that wasn't the case, right? And there's been a lot of those companies that are coming in. So if you go beyond, some of these issues of privacy, security, and liability that has to do with the data, you're also dealing with a totally different issue where startup companies are tapping into whatever comes out of computer vision, whatever comes out of NLP and broadly AI, and they're bringing them to the market with a lot of human in the loop, right? So if you're a construction company, if you're an owner client, you have only limited resources you can spend in terms of doing R&D. And you're looking to which approach would make your solution more standardized and what can be more sustainable. What I mean by that is you pilot a certain type of technology, and there's a team behind it that will be able to engineer that, adapt it for you, and help you scale and standardize that across a portfolio of projects you perform. And these are real day-to-day challenges of many of these clients that we're interacting with, right? So now from availability of the data, we are also competing in a fashion with many of these startups and technology companies. I go back to something I alluded to earlier today, that it would be really nice if we can streamline this entire process of what are these problems that these startups and technology companies are, worried about. And those are the problems that we as a community, we can address and let them bring some of these point solutions that can truly solve these issues at the scale of airports, commercial spaces, industrial projects like the ones that Fernanda was referring to.
All these are excellent points. We will have a conclusion at the end, and I will touch upon all these once again to remind everyone. But I want to see if there is any last question from the audience before I wrap up the panel discussion with my final question. Any last thoughts that you want to share with us, either from here or online, someone? Yeah.
Okay, so thank you for the great talks and discussion. I would like to ask about the air conditioning because I'm from an air conditioning company. Air conditioning must be a minor part of construction and building management, but actually 40% of the energy consumption comes from in the air conditioning in the building. And so does anyone have any research topic around air conditioning inside the construction or building management or any sort of suggestions of the area? Actually, our salespersons bring us cheap 3D sensor to reconstruct 3D model of the customer building to make a good proposal, how much air conditioning power is actually needed to make a good proposal to replace the existing air conditioning system. So the workshop is very related to my job.
So being a vision and graphics person, I would not have any pointers to that, but I can put you in touch with some people at UC San Diego who did a lot of cool work around the time there was a return to work after COVID, right? So, and air conditioning was a big part of it. So among all the US universities, UC San Diego had essentially one of the most effective return to learn programs and there were two parts to it. One was they pioneered this wastewater testing facility so essentially it's early detection of symptoms before you actually ask people to actively go into testing. But the other part of that was they redesigned all the air conditioning systems in the classrooms and other closed indoor spaces at UC San Diego to be more effective in terms of being able to better filtration systems that reduce transmittivity. So I don't work on that, but I can put you in touch with people who essentially redesigned those things.
Okay. I will give you my contact.
Sure.
I think from a sustainable systems perspective, I touched a little bit about design for disassembly, and and I think that connects with in the future, right? We don't know, like the pandemic had a huge impact on how we use our built environment, right? Office spaces, many of them are not used to capacity right now. And even now after the major emergency that took place, people are returning back to work. They're not returning to the same extent that we did before the pandemic, right? So we need to start thinking about flexible facilities. How do we design and build more flexible facilities to enable these changes that might happen over the facility life cycle? So we've already started seeing like buildings, high rises being designed and built. I know in downtown Austin, there are several facilities that are being built in which maybe a garage part of the building already has connection points in which that garage space could be transformed into an office space if more space is needed. So an HVAC system could be added more easily or connected to it more easily. So I think that there's a lot of potential from HVAC systems in flexible facilities. How do we design and enable spaces to be transformed from a non-conditioned space to a conditioned space, like from a garage to an office space or vice versa, right? And what is the impact? How do we integrate building systems into that equation if you're transforming from that non-conditioned to the conditioned space or the other way around? So we're seeing that happening already, right? And I think we just have to figure out how do we enable that better from the design perspective.
So at this point, I would like to make my final question to the speakers. Before that, I want to say, did anybody see the pun that Manmohan made about the cool project about the ACs? It was the only one that anyway. My final question to you is, I want you to imagine the world 10 years from now. The world where we are in need of new housing. We have a lot of urban development to happen. We don't have enough land to do that potentially. We don't have enough materials potentially to do that. And so we have this global problem of solving in a very sustainable way. So 10 years from now, imagine the best that you could think of this world. And maybe you can briefly tell us what that could be like and what could be the immediate next steps that we could take towards that. Maybe we will converge to one dream. Maybe we will have completely different dreams, or maybe some of the next steps we want to take could be similar. But let's see what you think. And I don't know who would be more prepared to answer this question right away. Someone who already has imagined that in their heads.
Yeah, I don't mind sharing. I'm not gonna go that far for 10 years, but I'm gonna, use some data as a basis of what I'm gonna say. We have a shortage of labor, skilled labor in the United States, and that shortage is close to about 650,000 workers. That's how many we're speaking. You talk to every project team, doesn't matter if they're designers, if they're contractors, or even the clients, every team is understaffed. So everybody's looking by ways they can focus on value-adding activities and minimize the amount of effort that they have to put into repetitive tasks. And unfortunately, in the world of design construction, there are many activities that are, redundant and can be saved. Anything that has to do with the administration of the project, from daily observations, from documentation of costs to schedule, every single one of them is subject to an opportunity that can be automated. And I pointed out that everything we do in design construction is visual. So there's a huge opportunity of bringing more of computer vision into many of our workflows so we can immediately address the shortage of labor. Both Abid and I think to some degree, Pimbo also touched on robotic platforms and their opportunity. And I know Yasu also touched on it. Of course, that's another angle to it, where you try to automate the process of data capture. So it also begs the question, can we focus on more of computer vision techniques that can interface with imaging systems? And how do you guarantee accuracy and completeness of the capture that can make computer vision system reliable from an engineering perspective? So I'm excited about that future, that we can address some of the skilled labor shortage that we have.
And I'll add on to that vision, right? Of there's a computer vision challenge and lots of opportunities in the construction industry. There's the automation and robotics, but there's also the modularization, prefabrication that I think we're we don't take advantage of enough in the construction industry, right? Because if the more we can build offsite in a controlled environment, the safer it will be for our workers. So we are a craft-based industry. So if we can minimize the amount of craft labor that goes into a construction site in an uncontrolled environment, put them in a controlled environment, we can have a huge impact from a safety perspective as well. And we know that the construction industry is the second most hazardous industry after transportation. So I think that in itself can also have an impact on people's lives from a safety perspective.
I could add to that for modular construction. One thing it's called standardization. It's about how to standardize the different Legos which can be assembled into different type of building, allow mass production at the same time allow customization. A big challenge I see from here is that in addition to Fernanda has been saying, it's called concurrent engineering. Concurrent engineering means if we have a designer and a construction engineer, they work sequentially. It's a big cycle of information flow, and the information flow could be accelerated by computer vision and many other technology, and allow designers and construction engineer work side by side with a smaller information flow cycle, instead of having like a large cycle of finish all the design, then engineer start, and finish all the engineer design start, and those are difficult for customization. And that is one, personally, I think that's one of the key problem modular construction has yet to satisfy customization requirement.
Maybe we have yet to hear from more CS-oriented people about the dream.
Yeah. So so maybe I can. It's fascinating to hear all these perspectives, and so I was also wondering about, so there's a field which is related to civil engineering and construction and everything that we have talked about today. I think it's also worthwhile to consider 10 years from now, there's a lot of progress that vision and learning might make in a lot of different areas, which might have nothing to do with construction, but could have significant impact, right? So I tend to think of these things as automation versus autonomy. And I think there's a lot of stuff that we can optimize with automation. And those are the type of things that we are doing today. But what autonomy can enable is entirely different paradigms in which entire industries get restructured. So if we have self-driving that becomes a reality a few years from now, then we are talking about very different modes in which we might be transferring stuff or transporting stuff from one place to another. That would be a lot more energy efficient. It could be that entire supply chains get restructured for how construction happens. And so that to me is really fascinating to think about. So maybe self-driving means that we don't need to have, I don't know, we don't need to have kitchens in our houses because everyone is just ordering food as efficiently as they want. So it could be that indoor spaces entirely get redesigned. It could be that entire supply chains get redesigned and get highly optimized. So that to me is fantastic to think about.
Maybe I can also share some thoughts. So I to be honest, I think at least for me, it's a bit hard to think how buildings or our cities will be in 10 years from now. But I think I'm quite confident that with this mixed reality and AR, because I mostly believe in AR, not so much in VR, in a couple of years, maybe 2 or 3, we will be able like to hallucinate and add content in our rooms that do not often offer any functionality, but are just there to please us, such as, for example, decoration pieces, or like you can, a very nice fancy sofa. I mean, you can be sitting on a very ugly sofa, but through your glasses, you see it as a fantastic sofa. So I think this will be one of the things that we're going to be seeing in a couple of years. And I'm wondering how doable it is to also replace some more core elements of a house, such as windows, for example. I mean, why do we have windows? of course, for fresh air to come in. Yes, this is a functionality, but apart from that, we could have like smaller windows at different locations. Like my house in Greece, for example, is my parents' house is in front of the sea, right? So we have a very big balcony with glass doors. I mean, this is of course more expensive, but if you can hallucinate and see the sea in front of you. So I think for me, this will be the major thing that it will change probably in 2 or 3 years.
Perfect. So with that, I will stop here the panel discussion. I want to thank all our speakers online and in person for their valuable insights. I have enjoyed this thoroughly. There were many times that I wanted to speak, but I didn't. And I'm glad I did not, because I've heard so many different opinions that really also opened my mind more. So again, thank you so much for being here and for presenting also. So you're welcome to take a seat if you wanted. And I will be giving a few small concluded remarks. Will not take long because I know it's been a long day and everybody's tired. So we've had a variety of speakers today and a variety of themes that happened. And I couldn't be more pleased about how many different topics we touched upon. We touched upon rendering, we touched upon indoor scenes, we touched upon industrial settings, about the business aspect, about the academic aspect, and about their urgency for a more sustainable and resilient future. And all about the ability to understand better, to use robots and create systems that are actually really working in the real world out there. All this created a very spherical perspective of what I would expect today this workshop to be, which is also a bit of a general topic, right? Computer vision for the built environment. That is exactly what, in my eyes, at least this workshop today was able to deliver. We talked about very important aspects of policy, of data sharing, of the business models. And this just points out again that we are not, this specific domain of AC is not in isolation. We have many stakeholders involved. There are many important safety aspects, aspects of privacy, aspects of concerning how we live in those spaces. It's the security, the liability behind everything that we cannot just easily circumvent as we might do with a very in vitro data set in computer vision, right? So we saw that many times, stakeholders and the ability to bring everything together, all the parameters, the complexity of the domain is what really puts us in a standstill a lot of the times. However, we also saw something, we heard something very important. I think Fernanda pointed that out, that right now, what is very important to our industry are things that will bring us a bit closer to doing our work a little bit less cumbersome. So we're looking at things that can automate a little bit of what we're doing today and let us solve the more complex things that we cannot really, don't have enough time to also spend on it. And this would help us achieve this global scale, sustainable future that we would like to see in the future, which comes a little bit in contradiction with what we usually do in computer vision, where we're trying to solve the hardest tasks, since this will bring us probably the biggest contributions and the biggest projects out there to be submitted to conferences. However, just keep in mind that even the smallest things in our domain could help so many people, have such a big impact out there. So I urge you to keep that in your mind. As I conclude this, I'm gonna tell you about 2 things that are coming up, at least from me, in this conference, as well as in the next computer vision conference, which is ICCV, in case you wanted to either stop by in this conference or join us in the next one. And I hope you will find interesting. Give me just a moment to share my screen so I can actually show you, just share very quickly a few things. One second. So the first thing I wanted to share is that we will have a demo presenting our new data set and benchmark on construction scenes. So we have captured several construction sites over time. And we have created a new spatial temporal benchmark, essentially to try to understand how our spaces change over time and how we can build robust computer vision methods that can address these large and drastic changes that we will be seeing and we are seeing in our built environment over time. This specific work now focuses on spatial temporal registration. However, we are hoping in the future to extend it more into semantics and have started tackling some of these problems that we have heard here and there today during the workshop. So if you want it, you can stop by this Thursday, booth 4, demo 42, to also, we have a VR device ready for you to interact with the data if you wanted to experience them inside. So this is the first thing. And the second thing is that in ICCV, we are organizing the first computer vision aided architectural design workshop with some fellow colleagues from TU Delft. And we have, first of all, keynotes from, these are the confirmed keynotes we have from very exciting people from computer vision and from the architectural practice. And we are going to have also paper submissions. You can check out with the QR code takes you to the project page, the workshop page. In case you wanted to submit some paper with respect to rethinking computer vision tasks for architectural design, about deep learning data sets for architectural visual data and what that means, model architectures or anything else that could fall under this specific topic. And also we will have a challenge that is about floor plan auto-completion, given essentially a graph with connectivity and a boundary. We would like to see what you can come up in terms of floor plans, and we will be using the Swiss dwelling data set. It's a huge data set in order to give you the training and testing sets. That is all that I wanted to say, and I will stop this promoting my work now to thank a lot my organizers. It's been 3 amazing years and we will continue hopefully sharing even more in the next years to come. I really enjoyed it. It has been tough, an entire day of this, but I leave this day jet lagged, but very, very rich with everything I've heard from all of you today. Thank you for being here. And thank you to everyone online.
And Despi, your work has been producing a lot of those synthetic data and the synthetic scenario. The question is, to what extent, in what situation, those synthetic data can help? In what situation is actually misleading the algorithm? Because civil engineering, it's a difficult business. If we have a model learned from the synthetic data, we got to have a good reason to understand what synthetic data is different from a real data. We don't know. And it's like a magic. We just got more data from a file thing. Maybe I don't know the answer yet. Maybe some of you know, is there any theoretical foundation to distinguish and to characterize what type of situation synthetic data is more reliable for training the machine learning model? What situation we should be careful? I don't know.
Yes. So that's a hard question for, I guess, machine learning in general, right? So usually we do not know how, or we do not know where distribution shifts will arise. We just know that they exist. And the only reason, or the only way we can determine that is through validation, right? So, but I think my feeling about synthetic data is similar to what I mentioned earlier, that I think there are the common cases that that one can simulate out. And those are essentially what we can simulate are things that we know or things that we have observed. And at least one step that we can take forward is to know that everything that we have observed in the real world is something that we can also simulate, because then that gives us the ability to go and modify things in a way that is that's physically meaningful, right? So, so I think that there's the difficult question of we care about anomalies in applications like this, or we care about defects and so on, for which fundamentally there does not exist a lot of data. And those are perhaps the type of things that simulation just fundamentally cannot help us there, but it can help us with the common cases. And that's where we can have machine learning speed things up for us, but it does not take away the human impact. I mean, I was wondering about a different thing actually when we were mentioning the parallel to healthcare or medicine. So because there's this real thing, there's a Wall Street Journal article on that a few days ago that now you have decisions being made by AI and they are actually sometimes in conflict with the decisions that the nursing staff make. And so who do you go with? And nurses increasingly find themselves overruled by AI. So there could be similar challenges in other safety critical applications also. So there's a defect on a bridge and a human expert thinks otherwise, but then you have AI telling you, no, everything is fine. And then one day, so over time, if we start trusting AI more, do we have fail-safe mechanisms? So that I think would be a sort of question that simulation would also face, right? So like to what extent do we trust simulation?
That's a very good point. Did anybody want to add something to that? No, because I heard something. Good. I wanted to see if anybody from the audience has any questions about anything that we've heard today in the workshop, or any other question that is in your mind and you wanted to address to the speakers, be that in the room in person or online. You can just step up to the mic, maybe. Anything? Can be thoughts? Yes, please.
I guess.
Yeah.
Yes. It's just a question regarding like I believe like the data types, 'cause it's really cool to have like good both sides of the view in terms of like residential buildings and data with like indoor layout generations or design, and then the workshop is really nicely focused on large scale industrial commercial buildings. Are there any like fundamental different focuses with these two types of data, or do you think one of these days it's a matter of like scale, like we're working smaller scale, larger scale, but the problems, the formulations are actually the same, or should they be different?
Maybe I can try to share
It's open for anyone else.
Yeah, no, I mean, some thoughts, because actually we have been trying to answer a similar problem for the last 6 months or so. So the reason why we started with the indoor layouts here, like, is two reasons. One, because IKEA was paying NVIDIA, which was the obvious reason. And the second one is because we had more data, and it was, it's also way more easier for me that have no idea of how architects design a building to familiarize myself, because, so what this model does is pretty much by observing how furniture pieces are arranged within the scene boundaries, it can learn to regenerate these arrangements. So for example, without explicitly saying to the model, hey, nightstands are normally positioned next to the bed, the model discovers this directly from the data. I think that if we were to try to, so my goal when I started my postdoc was that I want by the end of my postdoc to have a generative model that can generate cities, like be able to generate in New York. That was my vision. You see, I didn't present anything like this, but I think this is still a very valid dream. However, it's way more complex because the relationships and all the things that we need to take into account are way more complicated. For example, for the case of scenes, NVIDIA has two very nice papers called MetaSim and MetaSim 2, where they try to recreate some streets from, I think it's also from Canada, but the variability of the scenes that create is very, very limited. Again, we don't go to something that I personally think would be more interesting, such as doing bridges or doing, some more interesting construction work. I don't know how we could do it, but I think if we have the data is one thing. And the second thing that I want to point out is in which format, because we computer vision people are very used to working with data in a specific format. So it might be a bit hard to tune our line of thought with the, I don't know, this blob diagram it's called. I think there is one data set that we are using, which is called the building GAN data set, and they have like the room layout within a building that has multiple floors, like as a, as like this bubble gram. And I was like, what is this? How do you interpret it? But yeah.
I think I can reflect on your comment there. And I think the reason why we see a lot of indoor spaces in computer vision, in the computer vision domain, first off, we all are humans and we all spend 80% of our lives indoors, right? So we're sort of all experts and understand the indoor environment pretty well. So that's a really great starting point because we understand those spaces. When you start moving to engineered equipment and engineered systems, like in heavy industrial projects, you walk into a space that unless you have a background of understanding what those pipe spools represent, what those engineering systems represent, that's all gibberish, right? Unless you understand those chemical processes. So and the parallel is fundamentally, the geometry is the same, like of building systems. It's lines, it's it's fundamentally the geometry doesn't differ, but what it represents is something that might be more farther away from the domain expertise of us as human beings living in indoor spaces, right? So I think that's one of the reasons why we see a lot of computer vision applications in indoor spaces and floor plans in buildings, because we understand that better and it's easier to communicate. And we see less so in a nuclear power plant, like Pingbo said, right? Or in a liquefied natural gas plant, right? Simply because it's harder to communicate to a broader audience what those processes are. But I think if we can slowly solve problems in one, they can be extrapolated to other spaces as well. They're all built by the same types of people, right? They're all built by engineers. I'm not a specialist in chemical processes. I don't understand the chemical process that go about in a gas refinery facility, a gasoline refinery facility, but I understand how to build it, right? So it's all a matter of bringing together different expertise. But I don't know if that doesn't answer your question, but it's just a reflection, I think, on why we see that.
I think to an extent it did. I think your point. Oh,
yeah. So they can hear.
Oh,
yeah,
for sure.
yeah.
I think it did answer to a good extent because I think it reminds me that like different spaces have different purposes. And is it for living, which you would target for comfort, ergonomics, and whatever, or compared to industrial spaces, and it's as with many other systems, it's highly engineered. It's the metrics is a little different. Might not be necessarily for someone having a good time finding spot to map, maybe.
Yeah.
It's okay. Yeah. Thank you.
I saw Mani was ready to speak something about this. I saw Mani, you were ready to say something.
I was thinking about this in the context of business models and renovation and retrofit that happens in residential sector versus non-residential. So if you think about residential, there are all kinds of use cases, right? You constantly need floor plan, you constantly need to understand how you can change the layout. And thanks to a number of imaging system providers in platforms that now are being used for real estate rentals and buying new places, everyone has been exposed to these sort of a street view walkthrough experiences, and that data has been readily made available because of the large amount of use cases that you can envision. Now, automating that process is pretty interesting because you're not competing with service providers. In a non-residential world, we have a totally different set of companies that are in the business of generating floor plans and the business of generating models, and the cost of acquiring customers on that front is pretty high, and liabilities are totally different from the residential world. So it's being dominated by a totally different group of people, totally different business model. You don't see that data a lot. That doesn't mean that doesn't exist. Many of us actually come from a civil engineering background. We interact more of that data because the residential world is frankly easier from an engineering perspective for us to deal with, while non-residential parts where you have mechanical, electrical, plumbing, fire protection systems in close proximity to architectural and structural components, that's where engineering becomes a little bit more sophisticated. That's where there's more challenges for us from an architecture engineering perspective. So part of it has to do with the way that businesses have evolved and how the data has been made readily available.
And also how, like an MEPF, that mechanical, electrical, and plumbing and fire protection systems in a building, that's less, there are less company secrets from a process standpoint in a building's MEPF system, as opposed to, let's say, a liquefied natural gas or gasoline refinery facility. We don't have access to that data because many of these big energy companies have trade secrets in how they run their processes. So that's why we don't have access to a lot of that data as well. So it has to do also with the business model, even though fundamentally, like the fundamental raw geometry at the baseline is very similar.
Yeah, I can share my experience with the airport. Even though they collect a lot of data and for the air terminal, runway, and every part of the airport, I know they have a lot of camera, but they never share with me. I just don't know why, but some of you might tell me why. Then my guess is that for critical infrastructure, there is a very obvious reason. They don't want you to get those information for the protection of people. Some of those airlines, they might not want to let you know what are the something happens within their business, and they do not want people to get access to their data and to find it out. But generally, we may want to have a data sharing protocol, just like Mani has been saying. If we want to have that protocol, we need to solve 3 problems. Number 1, it's a technology problem, which is obvious. Number 2, policy problem. Number 3 is the business model, like Mani has been saying. Then if we look at these 3 issues, then it's not just about we need to get the data. People do not want to share the data. At the policy level, at the business model level, is there any way we can figure out an ecosystem to share the data in a reasonable way and with a reasonable protection for everybody?
Yeah, I also wanted to touch on something else that is happening at CVPR. I've been, following Twitter, and what was fascinating, a lot of conversation around startups and technology companies participating in CVPR. If you go back 10 years ago, that wasn't the case, right? And there's been a lot of those companies that are coming in. So if you go beyond, some of these issues of privacy, security, and liability that has to do with the data, you're also dealing with a totally different issue where startup companies are tapping into whatever comes out of computer vision, whatever comes out of NLP and broadly AI, and they're bringing them to the market with a lot of human in the loop, right? So if you're a construction company, if you're an owner client, you have only limited resources you can spend in terms of doing R&D. And you're looking to which approach would make your solution more standardized and what can be more sustainable. What I mean by that is you pilot a certain type of technology, and there's a team behind it that will be able to engineer that, adapt it for you, and help you scale and standardize that across the portfolio of projects you perform. And these are real day-to-day challenges of many of these clients that you're interacting with, right? So now from availability of the data, we are also competing in a fashion with many of these startups and technology companies. I go back to something I alluded to earlier today, that it would be really nice if we can streamline this entire process of what are these problems that these startups and technology companies are, worried about, and those are the problems that we as a community we can address, and let them bring some of these point solutions that can truly solve these issues at the scale of airports, commercial spaces, industrial projects like the ones that Fernanda was referring to.
All these are excellent points. And we will have a conclusion at the end, and I will touch upon all these once again to remind everyone. But I want to see if there is any last question from the audience before I wrap up the panel discussion with my final question. Any last thoughts that you want to share with us, either from here or online, someone? Yeah.
Okay, so thank you for the great talks and discussion. I would like to ask about the air conditioning because I'm from an air conditioning company. Air conditioning must be a minor part of construction and building management, but actually 40% of the energy consumption comes from in the air conditioning in the building. And so does anyone have any research topic around air conditioning inside the construction or building management or any sort of suggestions of the area? Actually, our salespersons bring us cheap 3D sensor to reconstruct 3D model of the customer building to make a good proposal. How much air conditioning power is actually needed to make a good proposal to replace the existing air conditioning system. So the workshop is very related to my job.
So being a vision and graphics person, I would not have any pointers to that, but I can put you in touch with some people at UC San Diego who did a lot of cool work around the time there was a return to work after COVID, right? So, and air conditioning was a big part of it. So among all the US universities, UC San Diego had essentially one of the most effective return to learn programs and there were two parts to it. One was they pioneered this wastewater testing facility so essentially it's early detection of symptoms before you actually ask people to actively go into testing. But the other part of that was they redesigned all the air conditioning systems in the classrooms and other closed indoor spaces at UC San Diego to be more effective in terms of being able to better filtration systems that reduce transmittivity. So I don't work on that, but I can put you in touch with people who essentially redesign those things.
I will give you my contact.
Sure.
I think from a sustainable systems perspective, I touched a little bit about design for disassembly and how, and I think that connects with in the future, right? We don't know, like the pandemic had a huge impact on how we use our built environment, right? Office spaces, many of them are not used to capacity right now, and even now after the major emergency that took place, people are returning back to work. They're not returning to the same extent that we did before the pandemic, right? So we need to start thinking about flexible facilities. How do we design and build more flexible facilities to enable these changes that might happen over the facility life cycle? So we've already started seeing like buildings, high rises being designed and built. I know in downtown Austin, there are several facilities that are being built in which maybe a garage part of the building already has connection points in which that garage space could be transformed into an office space if more space is needed. So an HVAC system could be added more easily or connected to it more easily. So I think that there's a lot of potential from HVAC systems in flexible facilities. How do we design and enable spaces to be transformed from a non-conditioned space to a conditioned space, like from a garage to an office space or vice versa, right? And what is the impact? How do we integrate building systems into that equation if you're transforming from that non-conditioned to the conditioned space or the other way around? So we're seeing that happening already, right? And I think we just have to figure out how do we enable that better from the design perspective.
So at this point, I would like to make my final question to the speakers. Before that, I want to say, did anybody see the pun that Manmohan made about the cool project about the ACs? It was the only one that anyway. My final question to you is, I want you to imagine the world 10 years from now. The world where we are in need of new housing. We have a lot of urban development to happen. We don't have enough land to do that potentially. We don't have enough materials potentially to do that. And so we have this global problem of solving in a very sustainable way. So 10 years from now, imagine the best that you could think of this world, and maybe you can briefly tell us what that could be like and what could be the immediate next steps that we could take towards that. Maybe we will converge to one dream, maybe we will have completely different dreams, or maybe some of the next steps we want to take could be similar. But let's see what you think. And I don't know who would be more prepared to answer this question right away. Someone who already has imagined that in their heads.
Yeah, I don't mind sharing. I'm not gonna go that far for 10 years, but I'm gonna, use some data as a basis of what I'm gonna say. We have a shortage of labor, skilled labor in the United States, and that shortage is close to about 650,000 workers. That's how many we're speaking. You talk to every project team, doesn't matter if they're designers, if they're contractors, or even the clients. Every team is understaffed. So everybody's looking by ways they can focus on value-adding activities and minimize the amount of effort that they have to put into repetitive tasks. And unfortunately, in the world of design construction, there are many activities that are, redundant and can be saved. Anything that has to do with the administration of the project, from daily observations, from documentation of costs to schedule, every single one of them is subject to an opportunity that can be automated. And I pointed out that everything we do in design construction is visual. So there's a huge opportunity of bringing more of computer vision into many of our workflows, so we can immediately address the shortage of labor. Both Abid and I think to some degree, Pimbo also touched on robotic platforms and their opportunity. And I know Yasu also touched on it. Of course, that's another angle to it, where you try to automate the process of data capture. So it also begs the question, can we focus on more of computer vision techniques that kind of interface with imaging systems? And how do you guarantee accuracy and completeness of the capture that can make computer vision system reliable from an engineering perspective? So I'm excited about that future, that we can address some of the skilled labor shortage that we have.
And I'll add on to that vision, right? There's a computer vision challenge and lots of opportunities in the construction industry. There's the automation and robotics, but there's also the modularization, prefabrication that I think we don't take advantage of enough in the construction industry, right? Because if the more we can build offsite in a controlled environment, the safer it will be for our workers. So we are a craft-based industry. So if we can minimize the amount of craft labor that goes into a construction site in an uncontrolled environment, put them in a controlled environment, we can have a huge impact from a safety perspective as well. And we know that the construction industry is the second most hazardous industry after transportation. So I think that in itself can also have an impact on people's lives from a safety perspective.
I could add to that for modular construction. One thing it's called standardization. It's about how to standardize different Legos which can be assembled into different type of building, allow mass production at the same time allow customization. A big challenge I see from here is that in addition to Fernanda has been saying, it's called concurrent engineering. Concurrent engineering means if we have a designer and a construction engineer, they work sequentially. It's a big cycle of information flow, and the information flow could be accelerated by computer vision and many other technology, and allow designers and construction engineer work side by side with a smaller information flow cycle, instead of having like a large cycle of finish all the design, then engineer start, and finish all the engineer design start, and those are difficult for customization. And that is one, personally, I think that's one of the key problem modular construction has yet to satisfy customization requirement.
Maybe have yet to hear from more CS-oriented people about the dream.
Yeah.
So maybe I can. It's fascinating to hear all these perspectives, and I was also wondering about, so there's a field which is related to civil engineering and construction and everything that we have talked about today. I think it's also worthwhile to consider 10 years from now, there's a lot of progress that vision and learning might make in a lot of different areas, which might have nothing to do with construction, but could have significant impact, right? So, so I tend to think of these things as automation versus autonomy. And I think there's a lot of stuff that we can optimize with automation. And those are the type of things that we are doing today. But what autonomy can enable is entirely different paradigms in which entire industries get restructured. So if we have self-driving that becomes a reality a few years from now, then we are talking about very different modes in which we might be transferring stuff or transporting stuff from one place to another. That could be a lot more energy efficient. It could be that entire supply chains get restructured for how construction happens. And so that to me is really fascinating to think about. So maybe self-driving means that we don't need to have, I don't know, we don't need to have kitchens in our houses because everyone is just ordering food as efficiently as they want. So it could be that indoor spaces entirely get redesigned. It could be that entire supply chains get redesigned and get highly optimized. So that to me is fantastic to think about.
Maybe I can also share some thoughts. So I to be honest, I think it's, at least for me, it's a bit hard to think how buildings or our cities will be in 10 years from now. But I think I'm quite confident that with this mixed reality and AR, because I mostly believe in AR, not so much in VR, in a couple of years, maybe 2 or 3, we will be able like to hallucinate and add content in our rooms that do not often offer any functionality, but are just there to please us, such as, for example, decoration pieces, or like you can, a very nice fancy sofa. I mean, you can be sitting on a very ugly sofa, but through your glasses, you see it as a fantastic sofa. So I think this will be one of the things that we're going to be seeing in a couple of years. And I'm wondering how doable it is to also replace some more core elements of a house, such as windows, for example. I mean, why do we have windows? Of course, for fresh air to come in. Yes, this is a functionality, but apart from that, we could have like smaller windows at different locations. Like my house in Greece, for example, is my parents' house is in front of the sea, right? So we have a very big balcony with glass doors. I mean, this is of course more expensive, but if you can hallucinate and see the sea in front of you. So I think for me, this will be the major thing that we will see probably in 2 or 3 years.
Perfect. So with that, I will stop here the panel discussion. I want to thank all our speakers online and in person for their valuable insights. I have enjoyed this thoroughly. There were many times that I wanted to speak, but I didn't. And I'm glad I did not, because I've heard so many different opinions that really also opened my mind more. So again, thank you so much for being here and for presenting also. So you're welcome to take a seat if you wanted. And I will be giving a few small concluded remarks. Will not take long because I know it's been a long day and everybody's tired. So we've had a variety of speakers today and a variety of themes that happened, and I couldn't be more pleased about how many different topics we touched upon. We touched upon rendering, we touched upon indoor scenes, we touched upon industrial settings, about the business aspect, about the academic aspect, and about their urgency for a more sustainable and resilient future. And all about the ability to understand better, to use robots and create systems that are actually really working in the real world out there. All this created a very spherical perspective of what I would expect today this workshop to be, which is also a bit of a general topic, right? Computer vision for the built environment. That is exactly what, in my eyes, at least this workshop today was able to deliver. We talked about very important aspects of policy, of data sharing, of the business models, And this just points out again that we are not, this specific domain of AC is not in isolation. We have many stakeholders involved. There are many important safety aspects of privacy, aspects of concerning how we live in those spaces. It's the security, the liability behind everything that we cannot just easily circumvent as we might do with a very in vitro data set in computer vision, right? So we saw that many times. Stakeholders and the ability to bring everything together, all the parameters, the complexity of the domain is what really puts us in a standstill a lot of the times. However, we also saw something, we heard something very important. I think Fernanda pointed that out, that right now, what is very important to our industry are things that will bring us a bit closer to doing our work a little bit less cumbersome. So we're looking at things that can automate a little bit of what we're doing today and let us solve the more complex things that we cannot really, don't have enough time to also spend on it. And this would help us achieve this global scale, sustainable future that we would like to see in the future, which comes a little bit in contradiction with what we usually do in computer vision, where we're trying to solve the hardest tasks, since this will bring us probably the biggest contributions and the biggest projects out there to be submitted to conferences. However, just keep in mind that even the smallest things in our domain could help so many people, have such a big impact out there. So I urge you to keep that in your mind. As I conclude this, I'm gonna tell you about two things that are coming up, at least from me, in this conference, as well as in the next computer vision conference, which is ICCV, in case you wanted to either stop by in this conference or join us in the next one. And I hope you will find interesting. Give me just a moment to share my screen so I can actually show you, just share very quickly a few things. One second. So the first thing I wanted to share is that we will have a demo presenting our new data set and benchmark on construction scenes. So we have captured several construction sites over time, and we have created a new spatial temporal benchmark, essentially to try to understand how our spaces change over time and how we can build robust computer vision methods that can address these large and drastic changes that we will be seeing and we are seeing in our built environment all the time. This specific work now focuses on spatial temporal registration. However, we are hoping in the future to extend it more into semantics and have started tackling some of these problems that we have heard here and there today during the workshop. So if you want it, you can stop by this Thursday, booth 4, demo 42, to also, we have a VR device ready for you to interact with the data if you wanted to experience them inside. So this is the first thing. And the second thing is that in ICCV, we are organizing the first computer vision aided architectural design workshop with some fellow colleagues from TU Delft. And we have, first of all, keynotes from, these are the confirmed keynotes we have from very exciting people from computer vision and from the architectural practice. And we are going to have also paper submissions. You can check out, the QR code takes you to the project page, the workshop page. In case you wanted to submit some paper with respect to rethinking computer vision tasks for architectural design, about deep learning data sets for architectural visual data and what that means, model architectures, or anything else that could fall under this specific topic. And also we will have a challenge that is about floor plan auto-completion, given essentially a graph with connectivity and a boundary. We would like to see what you can come up in terms of floor plans, and we will be using the Swiss dwelling data set. It's a huge data set in order to give you the training and testing sets. That is all that I wanted to say, and I will stop this promoting my work now to thank a lot my co-organizers. It's been 3 amazing years, and we will continue hopefully sharing even more in the next years to come. I really enjoyed it. It has been tough, an entire day of this, but I leave this day jet lagged, but very, very rich with everything I've heard from all of you today. Thank you for being here. And thank you to everyone online.